Welcome to Week 7 Advanced Machine Learning Algorithms. This week, first we'll start with Introduction to Ensemble Learning. Day 2, we'll be looking at bagging and random forests. Day 3, we'll be looking at boosting and gradient boosting. Day 4 will be Introduction to XGBoost. Day 5, we will cover Light GBM and CAD Boost. Day 6, we'll be handling imbalanced data. And for day 7, we'll do our ensemble learning project where we will be comparing models on a real data set. So let's get started with our week 7. Welcome to week 7, our day 1, Introduction to Ensemble Learning. Today, let's dive into first the concept of ensemble learning. Now, what is ensemble learning? Ensemble learning is a machine learning technique that combines the predictions of multiple models to produce a final output. The idea is that by aggregating the strengths of several models, the ensemble can achieve better performance than any individual model. Now, why does ensemble learning improve performance? First, it reduces variance. By averaging predictions, ensemble methods smooth out fluctuations caused by overfitting in individual models. It reduces the bias. Combining weak learners can lead to a more accurate prediction, compensating for individual model weaknesses. And then it improves robustness. Ensemble models are more resilient to noise in data compared to single models. Some of the applications include fraud detection, medical diagnosis, recommendation systems, and predictive analysis, as you probably already have guessed. Now, what are the different types of ensemble methods? First one is called as bagging or bootstrap aggregating. The concept here is you train multiple models independently on different subsets of data created through bootstrapping. It's random sampling with replacement. Now, this combines predictions by averaging, which is regression, or majority voting, which is classification. Now, example is random forest in this case. Next, the strengths of this is it reduces variance without increasing bias. Next is boosting. The concept here is it trains models sequentially where each model focuses on correcting the errors made by the previous ones. It combines predictions through weighted averaging or voting. Example here can be ADA boost, gradient boosting, XGBoost, and light GBM, which we'll probably be looking at it in future. Next, we have the strengths is reduces both bias and variance by focusing on hard to predict instances. Next one is stacking. The concept here, it combines predictions from multiple base models or different types using a meta model to learn how to best combine their outputs. The strengths here, it can utilize diverse model types to maximize performance. So these are the different types of ensemble methods that I'm going to talk about. But now, next, let's get into overview of commonly used ensemble methods. We have random forest, which we did last week, if you remember. It combines multiple decision trees using bagging. It reduces overfitting, common in individual decision trees. Gradient boosting sequentially builds models that minimize errors in the previous ones, suitable for both regression and classification tasks. We have ADA boost, which adjusts model weights based on performance, and it focuses on misclassified instances. We have XGBoost. It's optimized version of gradient boosting known for speed and accuracy. And we have voting classifier, which combines predictions of multiple models using majority voting or averaging. Now, based on this, let's jump into a hands-on exercise where the objective is to build a basic ensemble model combining predictions from linear regression, decision tree, and KNN to observe the impact on accuracy. The data set we'll be using here is the same iris data set to classify flowers into different species. So we'll follow a bunch of steps. I think we're going to go follow 4 different steps. Our step 1 will be first to load and pre-process the data set. So let's get started. It's a new file. Save as day 7 underscore exercise. And here first, let's go ahead and get the libraries. We need data sets from sklearn.dataset, and I am going to import the load iris. Next, from sklearn.model selection, I am going to import train, test, and split. Next, from sklearn.preprocessing, I am going to import standard scalar. Now let's go ahead and load the data set. For that, I'm going to say data equal to load iris. Next, we need the features and the target. So for that, it's straightforward, data.target. The data sets makes it easier for us to load the data. Next, let's go ahead and split the data set using the train test split, where we get x train, x test, y train, and y test. Again, this comes from train test split, and we'll pass x, the features, the target, test size equal to 0.2, and random state, my favorite number, 42. So I have that. Next, go ahead and scale. Some people ask me, why is 42 my favorite number? Is it my age or is it meaning of life? Now I'll let you decide that. Standard scalar, so scale features, standard feature, we're going to do that for train. We can say scalar dot fit underscore transform and pass it x underscore train. Next, for test, I'm going to do the same thing, scalar dot transform and pass x underscore test. So my features have been scaled. Our next step, step 2, is to train individual models. So we'll train the linear regression, decision tree, and KNN models separately. So for that, first I need them. So I'm going to say sklearn. Where is the logistic regression? That is available from linear model. And I am going to say import logistic regression. So I have my linear regression here. Next, from sklearn.tree, I will import, got it right, decision tree classifier. And next I need KNN, which is coming from sklearn.neighbors, which also again something that we have used before in one of the previous videos. Neighbors classifier. So perfect. So I have all my 3 different. Now let's train individual models. For that, I am going to say train individual models. My log model, give a underscore, looks better, equal to logistic regression. For my DT or a decision tree model, I'm going to say decision tree classifier. For my KNN model, I think I missed a L over there, equal to kneighbors classifier. Perfect. Now let's fit them with the data that we have. Log model dot fit, and I'm going to pass x underscore train, y underscore train. So this is pretty much common for all of them. So next, I want DT model. Next, KNN model. Okay, so that's perfect. So we trained individual models. Step 3 would be combine model into an ensemble. What we're going to do here is we're going to combine the predictions from the individual models using the majority voting for classification. So for that, I need some more libraries. Import numpy as np. We need from sklearn.ensemble. I need something called as the voting classifier, and from sklearn.metrics, I need accuracy score. Perfect. So I have all of them. available. So first thing is creating our voting classifier. So I'm going to say ensemble model. I'm going to say voting classifier, and the estimators that I'm going to use here include, you probably got it right, log underscore logistic regression is log model. For my decision underscore tree, I have dt underscore model. Perfect. And for my KNN, I have KNN model. Perfect. So all of them look good. Next, another thing that I want to do here is voting equal to hard voting, which means the majority voting is the one that wins. So keep it this way. Perfect. Next, let's go ahead and train the ensemble model. So I'm going to say train the ensemble model. To do that, I'm going to say ensemble model dot fit x train y train. So it's copies from the previous one, so that's good. But next is predict with ensemble. To do that, I'll say y underscore pred underscore ensemble. I need ensemble model dot predict and pass it x underscore test values. So this will do my prediction. And now let's go ahead and evaluate the accuracy. I'll say accuracy score or accuracy equal to accuracy score now, and pass it y underscore test and my predicted, which is y underscore pred ensemble. Next, let's print this out. I'm going to say f ensemble model accuracy is accuracy colon 0.2 f. Perfect. So this will print my accuracy of the ensemble model. Now if you want to compare, the final step is to compare the model performance. I can do that by adding the comparison for all of them. So I can say, let's start with saying evaluate individual models. I'm going to say y underscore pred underscore log equal to logistic model dot predict, and this one is x underscore test. I think this will stay the same for all of them. I'm going to say y underscore pred for decision trees is dt underscore model dot predict with this, and y underscore pred for knn equal to knn model dot predict. Perfect. Now let's go ahead and print all of them. So I'm going to move this below here, and I'm going to do 3 more for my others. Say logistic regression accuracy, which will be, I have not calculated that, so I'm going to say accuracy score y underscore test y underscore pred log. Right, so that's good. I'm going to take this and paste it for this and this. This one is decision tree accuracy. For this, we'll pass dt. Accuracy score is y test and y pred dt. Next one is my knn accuracy. Let's put it properly. K dash nn accuracy. Accuracy score is knn. Perfect. Y pred knn. And this one we already calculated, so we don't have to change anything for this. So let's go ahead and compare and run this. I'm a little excited for it. So let's go ahead and say Python day7 dot. So it looks like there's an error where it says missing one required positional argument x in this particular case. So let's go ahead and check it out. Right here we have scalar equal to scalar transform, and I see that I have not created this. So let's go back again, clear it out, run it. And there you go. We have the logistical regression accuracy is one. This is one. This is one. Ensemble model is also one. The reason is we are using a pretty solid data set of load iris. If so, that's why it is giving me perfect accuracy for all of them. But if you use a real life data set, you probably might see something different. But again, this is the way to kind of compare different models and see their accuracies, and also create an ensemble based on different models that you want and building into one single model from them. So I hope you are able to follow along and get this through. If you have any questions or had any issues with this, let me know and I'll get back to you. So, just to recap, today we got into learning and understanding the concept and importance of ensemble learning. We differentiated between bagging and boosting methods. We went and gained some hands on experience creating a basic ensemble using diverse models, and then we observed how ensemble learning improves model performance through aggregation. So, I hope this helps, and if you have any questions or have any follow up, let me know and I'll get back to you. Day 2, bagging and random forest. So, first, let's try to understand bagging, which is also called as bootstrap aggregating. Now, what is bagging? Bagging or bootstrap aggregating is an ensemble learning technique that trains multiple models on different subsets of the data created by random sampling with replacement, or also called as bootstrapping. The predictions of these models are then aggregated to make a final prediction using either regression, which is the average the predictions of individual models, or classification, where we use majority voting to determine the final class, which we have done earlier this week. Now, why use bagging? First, it reduces variance. Bagging smooths predictions by averaging them, reducing the effect of overfitting. It improves the robustness. By combining the predictions of multiple models, bagging creates a more stable and reliable ensemble. Now, applications is bagging is commonly used with decision trees which are prone to high variance. Now, let's talk about random forest. Now, what is random forest? Random forest is an ensemble learning method that builds multiple decision trees using bagging. It introduces an additional layer of randomness by selecting a random subset of features for each tree split. This makes random forest robust and reduces overfitting. Some of the key features of random forest include its bootstrap sampling. Each tree is trained on a randomly sampled subset of the data. Feature randomness: at each split, a random subset of features is considered, ensuring diversity among the trees. And prediction aggregation. In this method, we use regression for averaging the predictions of all trees, and classification to use the majority voting. Advantages of random forest include it handles both regression and classification tasks effectively. It also works well with high dimensional data, and it reduces overfitting compared to single decision trees. Now let's talk about the key parameters in random forest, which we used in the last, I think last week we used one of the project, which has number of trees, which are also called as n estimators, which is the number of decision trees in that particular forest. And large values reduce variance but increase the computational cost in this particular case. We also use the maximum depth, which is max underscore depth, which limits the depth of each tree to prevent overfitting. Its shallower trees generalize better but may underfit. Then we use the feature selection, which is max underscore feature, the number of features to consider when looking for the best split. Options include the square root, which is square root of total features, default for classification this is, and we use log 2, which is logarithmic of total features, and none is use all the features. That these are the parameters. We did one with none in the last week. Next, we have the minimum samples per leaf, which is min underscore samples underscore leaf, which kind of talks about minimum number of samples required in a leaf node. Next, it prevents overly complex trees by ensuring each leaf contains enough samples. Now, based on this, let's jump into a hands-on exercise where the objective is to train a random forest classifier on a data set, tune its parameters, and evaluate its performance. The dataset we'll be using here is we'll use the breast cancer dataset, which is a binary classification dataset to predict whether a tumor is malignant or benign. So we will follow a bunch of different steps. To start with, let's start with a new file. Call it a Python file, save it in my day2 underscore ex.py. Let's start with loading and pre-processing the data. Now, where does the data come from? It will come from sklearn.datasets, and I am going to import from there load under. If I don't type properly, it will not help me. Load breast cancer. Next, I'll say from sklearn.model selection, I will be importing train underscore test underscore split. Next, let's go ahead and load the data set. To do that, I'm going to say data equal to load breast cancer. Next, I'm going to use my features and target by using the shortcut data.data, and for targets, I'll say data.target. So I have those available. Next, I am going to split the data set with split the data set where we will get X train, X test, Y train, and Y test from train test split, and we can pass X, Y test size equal to 0.2 and random state equal to 42. Now, next thing is we display the data set information. Now here I am going to say print. First, let's say features that it has is comma data dot feature underscore names. Next, I will do print the classes that it has, which is data dot target underscore names. So let's go ahead and print these and check how they look like. I'm going to say Python day 2, and there you go. These are the features that it has, and for like mean radius for the tumor, mean texture, mean perimeter, mean area, a bunch of different features and classes. We have malignant or benign. Our step 2 is to train a random forest classifier with the data that we have. So to do that, first I need the random forest classifier. Now that I can get from sklearn.ensemble and import random forest classifier. Next, for metrics, I'm gonna get from sklearn.metrics. I will import accuracy score and classification report. Now, next step is to train the random forest classifier. So I'm going to go here and say train random forest. For that, I'll say rf underscore model equal to random forest classifier, and I'll give a random state of 42. Next, I'm going to say rf underscore model dot fit the data, which we have x underscore train and y underscore train. So once I fit the data, next thing is all about prediction. So let's go ahead and predict y underscore pred equal to rf underscore model dot predict function and pass it x underscore our test data to predict the fields. So once that is done, let's go ahead and finally evaluate the performance of this model. To do that, first I will get the accuracy is coming from accuracy score, pass it y underscore test and y underscore pred. Next I'll say print. This particular case, first is random forest accuracy is accuracy. Perfect. Next I want to say classification report. Now that will be multiple lines, so I am going to say /n classification report /n, And to get the classification report, I'll use the classification report function, and to that I'll pass the parameters y test and y thread. There you go, perfect. So let's go ahead and run this and check it out. And to clear this out, I'm gonna not display them anymore and run it. So there you go, we have a random forest accuracy very close to 1, and our classification report which shows bunch of different data. For a change, I think this model has better data as compared to others, and it gave us 0.98 instead of 1.0, but it tells us how well the model can predict based on the data that we have trained it with. Next, let's go ahead and tune some parameters and see if we can make it better. So we will go ahead and from sklearn dot model selection, I will import the grid search as CV, where we can give some hyperparameters. Now here we will define the hyperparameter grid. This also we did in the last day 7 of last week, where we are going to give a parameter grid equal to, inside this, the ones that I'm interested in is n estimators, and we'll give different values and see which one it picks up best. 50, 100 and 200 I will use for my max underscore depth. I will use either none, 10 or 20, and then we set features. So max features, as we mentioned, there's square root, there is what are those? We have square root, we have log 2, and we have none, which is all of them. So there you go. So these are our parameters grid. Now let's try to do a grid search and see which one is the best one. Grid search equal to grid CV, and inside this we'll have to give all the different functions or parameters, which is first is estimator. That is our random forest classifier with random state equal to 42. Next, I want to give the parameter grid, which is the parameter grid that I created. Next, it needs CV cross validation equal to 5, and I'll say scoring equal to, I'll use accuracy, and for number of jobs I'll say -1. Okay, perfect. And then I'll say grid underscore search and fit the data x underscore train, y underscore train, and then finally let's go ahead and display the best parameters and the score also. So I'm going to say print f of best parameters is grid underscore search dot best parameters. Perfect. I will also say print f of best cross validation accuracy is grid underscore search dot best score. Let's display these out. Let's go ahead, clear it out, run it. So it looks like it's saying that I need to provide log to a square root. I'm not sure what I'm doing wrong here. Maybe I need to provide it in curly brackets or something. But again, it worked, and what we have here is we can see the accuracy base 96, and then here 9626. Let's see if it's increased. It's actually reduced based on the parameters that are provided. Max depth none, max features it used square root, and n estimators it used 200, and the accuracy that it got is 0.962. So this is how you can train a random forest classifier on a dataset, tune its parameters, and evaluate its performance. The performance is not as good as compared to what we had. Maybe my values were not good and probably have to work more on getting a better grid here and give a better parameters to have a better performance. But again, this is the entire process of building a random forest classifier and tune its parameters and evaluating its performance. I hope you were able to follow along. If you have any questions, do let me know. And then just to go over the summary, we went and understood the concept of bagging and how it reduces variance in machine learning models. We learned the architecture of random forest and how they improve performance compared to the single decision trees. We gained hands-on experience tuning hyperparameters to optimize a random forest model, and we observed how random forest handle classification tasks effectively through feature randomness and bootstrap sampling. I hope it was helpful. If you have any questions or had any issues, let me know and I'll get back to you. Day 3, Boosting and Gradient Boosting. Today we're going to look at the concept of boosting first. What is boosting? Boosting is an ensemble technique that sequentially combines weak learners, which are models with performance slightly better than the random guessing, to form a strong learner. Now, each subsequent model focuses on correcting the errors made by the previous models. Now, how does boosting differ from bagging? Here is a table displaying that. So, the feature for bagging is approaches trains models independently on bootstrap subset, whereas boosting trains model sequentially to correct the errors. The purpose of bagging is to reduce variances by averaging predictions, whereas boosting reduces bias by focusing on difficult cases. Examples of bagging, we already saw one, random forest, yesterday, and for boosting we're going to look at gradient boosting, and then there's adder boost. Now let's look at gradient boosting in more detail. What is gradient boosting? Gradient boosting is a boosting algorithm that builds models sequentially by minimizing a loss function using gradient descent. It iteratively adds weak learners, usually decision trees, to improve overall model performance. Now, how does gradient boosting work? First, you initialize the model. You start with a simple model, often predicting the mean of the target variable. Then you compute the residuals. Calculate the difference, the residual between the actual and predicted values. Next, fit the weak learner. Train a weak model. Example can be a shallow decision tree to predict the residuals. Next, you update the prediction. You add the predictions of the weak learner to the overall model. Then repeat. Continue adding weak learners until the desired number of iterations or a stopping criteria is reached. Let's talk about the key parameters in gradient boosting. We have the learning rate, which determines the contribution of each weak learner. Its smaller values reduces overfitting but requires more iterations. Now we have number of estimators is the number of weak learners trees added sequentially. Larger values improve learning but increase also the computation time. And then we have regularization. Techniques like limiting the depth or adding penalties to prevent overfitting. Next, let's talk about understanding the key parameters. We have the learning rate or learning underscore rate. Lower, lower values improve model performance by reducing the overfitting but require more iterations of learning rate. Typical range that we use is 0.01 to 0.3. Number of estimators or n underscore estimators represents the number of trees added to the ensemble. Larger values can improve performance but it's risk overfitting. Next, we have tree depth or max underscore depth. It limits the complexity of individual tree, and in this case, shallower trees generalize better but might underfit. With all this information, let's jump into our hands-on exercise for today, where we will be training and evaluating a gradient boosting model on a dataset, tune key parameters, and compare its performance with random forest model. The dataset we'll be using is the same as last one, the breast cancer dataset, a binary classification task to predict whether a tumor is malignant or benign. So let's start with our step one, where we'll be loading and pre-processing the dataset. Go ahead, create a new file, save it as day 3 underscore exercise. Here I'm going to say from sklearn dot datasets. I need the dataset, so I'm going to say import load breast cancer dataset. From sklearn dot model selection, I will import the train test split. Now let's go ahead and first load the data set. So I'm going to say data equal to load breast cancer. Next, I'm going to say x comma y equal to data dot data and data dot target. That will get me my target. Now let's go ahead and split the data set. To do that, I'm going to use train test split, pass it the values of x, y, test size equal to 0.2 and random state equal to 42. That will give me x underscore train, x underscore test, y underscore train, and y underscore test. So I have my data set. Now let's go ahead and first display some data set information. So I can print the features which we already saw in the last video or yesterday. Data dot features underscore names, that will give me the names, different features that we have, and then I want to also see the target names, that will give me the classes, let's say in this particular case, and then let's go ahead and run it and check it out. Python day 3. There you go, we have our features and the classes available. Perfect. Our next step is to train a gradient boosting model. This time we train a gradient boosting model using scikit-learn's gradient boosting classifier and evaluate its performance. So for that, so I'm going to go ahead and from sklearn dot ensemble import the gradient boosting classifier. Next, sklearn dot metrics, we will, for evaluating, we are going to use accuracy score, and we'll also display the classification report just to compare with yesterday's data. So once I have that, next thing that I'll do is I'll train the gradient boosting model. To do that, I'm going to say gb underscore model equal to gradient boosting classifier, give it a random state of 42, gb underscore model dot fit, I'm going to fit x underscore train and y underscore train. Perfect. Now it's time to predict. So I'm going to say y underscore pred underscore gb equal to gb model dot predict and give it x underscore test data set. So once I'm done with that, now I can go ahead and evaluate performance of this model. I can say accuracy underscore gb equal to accuracy score and pass it y underscore test and y underscore pred gb. Let's go ahead and print these data out so we can check it out. I'm going to say gradient boosting accuracy is accuracy gb 0.2f. I want to see the entire thing, so just 2 decimal places is good, /n classification report /n comma classification report, and to this I'll pass the same parameters. Perfect. So that should do it. So let's go ahead and test this out before we tune the parameters. So I'm going to go here, clear, run it again, and we have our gradient boosting accuracy of 0.96, and this is the classification report that we have. Perfect. So let's go back and let's do the tune parameters step, where we'll experiment with different learning rates and number of estimators to optimize the model performance. So first I am going to say, let's define a hyperparameter grid. Also, I need that from my model selection, I would need the grid search CV. So I'm going to just do it there. So I'm going to say parameter grid equal to, I will be using first the learning underscore rate as I said. So I'm going to say try to use 0.01, 0.1. As I mentioned, we give from anywhere from 0.01 to 0.3 depending on what you prefer, and let it play with it right now. N underscore estimators is I will give the values between 50, 100 and 200. So let it decide, and then I'll give a max underscore depth. I'll give either use 3 trees, 5 or 7. So tell me which one is better. Now let's do a perform the grid search. To do that, first let's create the grid search variable, which will use my grid search CV, and it needs the parameter. First it needs the estimator, which is our gradient boosting classifier with a random state of 42. Next I have the param grid, which is param grid that we created. Next we need CV equal to 5. Next we need scoring equal to, I am going to use accuracy, and n underscore jobs equal to -1. And then finally I'll say grid search dot fit. I'll fit it with the data x underscore train and y underscore train. Perfect. So that's fit. Now next is, let's go ahead and display our best parameters and score. So to do that, I'll say print f of best parameters is grid underscore search dot best parameters. Next I'll say print f of best cross validation accuracy. What is the best one that it can provide us? Grid underscore search dot best underscore score equal to 0.2 f. So that's what it is. So next step is to compare the gradient boosting with random forest, but for now I'm going to save this and run it and see how it looks like. So we have our this best accuracy just by gradient boosting. Now let's, after the tuning of the hyperparameters, let's see what we get. It's going to take some time, and there you go. Learning rate is 0.1, max depth is 3, and n of estimators equal to 200 based on the data we provided, and the best cross validation accuracy it can give us based on these parameters is 0.96. Our next step, as I mentioned, is to compare the gradient boosting with random forest. So I am going to go ahead and from my ensemble, I'm going to also get random forest classifier. Next, I am going to train the random forest here. Say rf underscore model equal to random forest classifier, random state equal to 42. Next I'm going to say rf underscore model dot fit. I'll pass it x underscore train and y underscore train. Next, to predict, I will say y underscore pred of rf equal to rf dot model, rf underscore model, sorry, dot predict, and pass it x underscore test. Next, based on that, let's get the accuracy. So I will say, based on the data that we have, let's evaluate the performance. To do that, I'll say accuracy underscore rf equal to accuracy score y test versus what we got under y pred rf. Now let's go ahead and print our random forest accuracy, that is, oops, I can do it inside, accuracy rf 0.2 f. Now we already have the gradient forest boosting accuracies before, so we can just compare them. clear, run it again. So our gradient boosting accuracy is 0.96. Now after we do hyperparameters, we also found that the accuracy for that is 0.96. Now after doing, if I can type properly, that is, let's go one more time. It's going to take a little bit time. So again, gradient boosting accuracy is 0.96. After doing the tuning the parameters, we get 0.96, and with random forest accuracy, we're also getting 0.96. If I remove these, let's see to the decimal point how good they are. I'm going to just to have fun with it. So 0.95614 is the value here, 0.56. So, and that is without tuning the hyperparameter. Once we tune in the hyperparameter is 0.964, which is better than as compared to random forest 0.9649 versus 48. So random forest is still better as compared to the others that we have used here. So just to summarize, today we understood the concept of boosting and how gradient boosting builds sequential models. We learned the importance of tuning hyperparameters like learning rate and number of estimators, and then we gained hands-on experience training and optimizing a gradient boosting model. And finally, we compared the strengths and weaknesses of gradient boosting versus random forest. I hope you were able to follow along and get through this project. If you had any issues or errors that you saw, let me know and I can help you out with them. Day 4, Introduction to XGBoost. Let's go over first XGBoost of what is XGBoost. XGBoost, or also called as extreme gradient boosting, is an advanced implementation of the gradient boosting algorithm designed for speed and performance. It introduces various enhancements that make it faster, more efficient, and capable of handling complex datasets. Let's talk about improvements over traditional gradient boosting of how it helps. First, speed. Implements parallel processing to speed up computations. Handling missing data. Automatically handles missing values by learning optimal split directions. Regularization. Adds L1 lasso and L2 ridge regularization to reduce the overfitting. Custom loss functions. Allows users to define custom loss functions for specific needs. And tree pruning. Uses a max depth parameter to prune unnecessary branches, improving computational efficiency. Let's look at some of the key features of XGBoost. Handling missing data. Automatically assigns missing values to the branch that minimizes the loss function. It reduces the pre-processing steps for data sets with missing values. And regularization. Includes penalties for overly complex models, reducing the overfitting. Hyperparameters that are used are lambda, which is L2 regularization term, and alpha, which is the L1 regularization term, and parallel processing. It splits the calculations for tree construction across multiple cores, significantly improving your training time. Let's talk about the hyperparameters in XGBoost and how to tune them. So first, the key hyperparameters are learning rate, which is ETA, controls the contribution of each tree to the model. Typical range is 0.01 to 0.3. Next, we have a number of trees, which is n estimators, determines the number of boosting rounds. Larger values may improve performance but increase the computation time. Next, we have tree depth, which is max underscore depth. Limits the depth of trees, balancing bias and variance. Shallower trees generalize better, while deeper trees may overfit. Your subsample, a fraction of data used to train each tree. Helps reduce overfitting. Typically range is between 0.5 to 1.0. Then we have call sample by tree. Fraction of features used for each tree split. Typical range is 0.5 to 1.0. And finally, we have the regularization parameters, lambda and alpha, which control L2 and L1 regularization respectively. Now let's go ahead with a hands-on exercise for this, where we'll be training an XGBoost model on a data set tune hyperparameters using cross-validation and compare its performance with a gradient boost model. We'll be using the same dataset, the breast cancer dataset that we used earlier yesterday, which is a binary classification problem. So let's go ahead. First, this time, instead of starting a project, we'll start a project. Why not? Save it in day4_ex.py. But we'll go to terminal, make sure we're in the right folder, and here we will say pip install xgboost. It doesn't come by default, so you have to go ahead and install it. I've installed it earlier, so that's why it was pretty quick, but for you it might take some time if you're doing it first time. Now next, let's go ahead and get the Python imports. So I'm going to say import xgboost as xgb. Next, I'm going to say from sklearn dot datasets. I need that dataset on import load breast cancer. Next, I'm going to say sklearn dot model selection. I am going to import train test split, and for the grid of parameters or the grid search, I'm going to use grid search CV. Next, I'm going to say for matrix, I will import accuracy score and classification report. Perfect. So I have that. Next step is to load and pre-process the data set. So I am going to say load the data set, which is data equal to load breast cancer, and then x comma y equal to data dot data and data dot target for y respectively. Next, I'm going to go ahead and split the data set, and I'll get x train x underscore test y underscore train y underscore test equal to train test split x comma y comma test size equal to 0.2 and random state equal to 42. Next, I will go ahead and display dataset info. So for that, I'll say print f of features, which are data dot feature underscore names, and then I'll display the classes, which are f classes data dot target underscore names. Perfect. We've done this before, so I don't want to run it again. So I'm going to go to the next step, which is train an XGBoost model. So first, I'm going to go here and say convert data set to D matrix. Now this is the optimized data structure for XGBoost. The way we do it is we say dtrain equal to xgb dot D matrix. And this is first time I'm using these, so that's why they are not going to autocomplete. Xtrain and label equal to y underscore train. Next, I need dtest, which is xgb dot D matrix, and inside the function is x underscore test and label equal to y underscore test. Perfect. So that kind of creates my D matrix. Next, I will go ahead and train XGBoost model. Now to do that, I'll say first I need the parameters. Parameters are, I'm gonna move it up so it's clear. First is objective, and objective I specify, I say I want to do a binary logistic regression here. Next, I say the eval metric is in this case log loss. That's what I'm going to specify, log loss. So you can actually specify whichever you like for the evaluation metric. Next, I'm going to say max underscore depth that I want to use in this case is 3, and I can say ETA is 0.1. If you remember, ETA is the learning rate that we use, and that's what I mentioned here. Next, let's go ahead and take the xgb underscore model equal to xgb dot train, I'll pass the params to it. I pass the dtrain to it. I'll pass the number of underscore boost underscore rounds of how many rounds do I want of this XG boost equal to 100. More like iterations is 100 I want. Next I'll say go ahead and predict, and I'm going to say y underscore pred equal to xgb underscore model dot predict, pass it dtest which we created earlier, the dtest dataset greater than 0.5 as type int. So since it's a classification, I need 0 and 1, so that's why I'm mentioning that. Next, let's go ahead and finally evaluate the performance. To do that, I am going to say accuracy equal to accuracy score and pass it y underscore test and y underscore pred. So compare those. It looks like I pressed the cap or shift a little early. Y pred, and then now print. In this case, I am going to say xg boost accuracy is accuracy. Let's not use the point here because it doesn't give me the best results. Let's say /n classification report with this is /n comma classification report y underscore test and y underscore pred. Perfect. I think everything is good for now. Let's see. XG push is giving me warning, but already added the library. Let's hope it works. So let's clear it out, and I'm gonna say python day4 dot underscore ex. I have an error here which says xgb train. Something is wrong here. Let me look at it. XGB, where did I create it? Here. Oh yeah, I think I said number of boost rounds, not rounds, round equal to 100. That was the error. I think it does specify here. So I'm going to go ahead and run it again. And there you go. We have accuracy of 0.956. And this is a classification report based on the XGB boost. Pretty good. Almost all in above 90s. So that's a good table we have of the classification report. Our next step is to do hyperparameter tuning with cross validation. So for that, I'm going to go back here. I need the from XG boost. I need one more thing. I will import something called as, did I spell XG boost right? Yes, XG boost XGB classifier. That's what I need. So first, I'm going to go here and say define the hyperparameter grid. Same thing that we did earlier. Say param underscore grid, and here I will give the grid values, which are first one is the learning rate. That I want to specify to 0.01, 0.1, and 0.2. Next, I want to give the n underscore estimators, which I will give from 50, 100, 200. Next, I want to give the max depth, which either will be either 3, 5, or 7. Pick which is the best. Next, I can give the subsample. So that I will specify between 0.8 and 1.2 to pick the best one. Next one, I'm going to go for column sample by tree. This I will specify to be again 0.8 and 1.0. Here's this, which columns to use, and then I'm going to say initialize XG boost classifier. So do that. I say XGB underscore classifier or CLF equal to XGB classifier. It needs some parameters like user underscore label underscore encoder. I'll set that to false. Next we have eval underscore metric equal to equal to I'll say log loss, and then I'll have to give a random state for this. Random state, since it's first time I'm doing it, everything I have to hand type. Doesn't help me. I think user label encoder has been removed in the latest version, but we'll check it out when we run it. Next thing that I want to do is I want to perform the grid search based on the parameters that we've given. So I'm going to say grid underscore search equal to grid search CV. Give the estimator as xgb underscore classifier. Next I need the parameter grid, which is parameter grid. Next I need the cross validation of 5. Next I am going to say the scoring type that I want to use is accuracy. Next n jobs, I'll say n underscore jobs equal to -1. I'll keep that consistent as others that we've done till now. And then finally I'll say grid underscore search, and to this I'll fit my x underscore train and y underscore train. Save that. Now let's go ahead and display the best parameters and score. So I say print first one is best parameters grid underscore search dot best parameters is what I'll specify here. Next let's go ahead and print f of this one is best cross validation accuracy, which I'll mention grid underscore search dot best score, and I'll leave it as it is. Perfect. Now next is to compare the XGBoost with gradient boosting, but for now let's run this and check if some of my predictions are right or wrong. So here you go, user label encoder has been removed, so I can just remove that, clear it out. Let's run it again. So there you go, we have by XGBoost the accuracy is 0.95. The best cross validation based on the parameters that we've given is 0.97, much better than the actual accuracy, so that's good. And it picked up the best parameters as 0.8 for call sample, for learning rate 0.2, max depth is picked 5, and n estimator is 200, subsample is 0.8. Perfect. So I have that. Now the next step, as I mentioned, is to compare XGBoost with the gradient boosting. For that, first let's go ahead. Do I have ensemble? No. So I am going to say sk learn dot ensemble. I am going to import the gradient boosting classifier. Go at the bottom and train the gradient boosting model. To do that, I'll say GB model equal to gradient boosting classifier, give a random state of 42. Next I'll say GB underscore model dot fit with X underscore train and Y underscore train. So we have model train. Now let's go ahead and get the predictions. Underscore GB equal to GB model dot predict and give it the data set X of test. Now let's go ahead and evaluate the gradient boosting performance. To do that, I can say accuracy of GB equal to accuracy score and pass it y underscore test and y underscore pred of GB, and then I can now print the gradient boosting accuracy, pass it accuracy GB, Perfect. And then we can compare the results with the others. So let's go ahead. It's already clear. So I'm going to run the project. So our accuracy with XG boosting is 0.95614, with the best with after parameter tuning is 0.97. But if you look at gradient boosting as compared to XG boost, 0.56140350877193, exactly same as XG boost, even though it is supposed to be better than gradient boosting, but based on the data set, I think it's gives you exactly same number to the point. So perfect. So that kind of showed you how we can use XGBoost, how we can tune XGBoost model, and finally we compared with the gradient boosting. So just to summarize, we went and understood the key advantages of XGBoost over traditional gradient boosting. We learned how to train and evaluate a XGBoost model for binary classification. Also, we gained some experience tuning XGBoost hyperparameter using the grid search. And finally, we compared XGBoost with gradient boosting to understand the relative strength and weaknesses. Here, it turned out to be exactly pretty much same, but with hyperparameter tuning, XGBoost kind of blew it out the park and it did a pretty good job. If you have any problems or had any issues or have any questions, let me know in the messages and I'll get back to you. Day 5, Light GBM and Cat Boost. Let's start with Light GBM. Introduction to Light GBM. What is Light GBM? So Light GBM or Light Gradient Boost Machine is an efficient implementation of gradient boosting designed to handle large data sets and high dimensional data with speed and accuracy. Some of the key features of Light GBM are its histogram based splitting, which means it uses histograms to discretize continuous features, reducing memory usage and computation. Leaf-wise tree growth grows the tree by adding splits to the leaf with the highest loss, improving efficiency but potentially overfitting if not regularized. Support for GPU training. Accelerate training using GPU computation. Handling sparse data. Efficiently handles dataset with missing or sparse values. Let's look at some advantages of Light GBM. First, it's faster training than XGBoost, handles large datasets effectively, and reduces memory usage with histogram based splitting. Now, when to use Light GBM? When you have large datasets with numerical features, that's one. And next is the time sensitive task requiring fast training. Let's talk about overview of Cat Boost. Now, what is Cat Boost? Cat Boost is a gradient boosting library developed specifically to handle categorical features without the need for pre-processing like one hot encoding. The key features of Cat Boost include its native support for categorical data, uses statistical encoding for categorical features, preserving order and relationships. Ordered boosting reduces prediction bias by using a permutation based scheme to train models. Robust to overfitting implements built in regularization methods, and that's why no overfitting most of the times. Advantages are it eliminates the need for manual encoding of categorical data, reduces overfitting with robust boosting techniques, and easy to implement for datasets with many categorical features. When to use Cat Boost? When you have datasets with a high proportion of categorical features, when you have applications where overfitting is a concern, that's when we use Cat Boost. Now let's look at a comparison of XGBoost, Light GBM, and Cat Boost. Here is a table where it shows we saw the feature with speed, then XGBoost is moderate, Light GBM is fast, and Cat Boost is fast. When you have to handle categorical data, XGBoost requires encoding. Light GBM also requires encoding, whereas Cat Boost has native support. When you have memory usage, XGBoost is moderate and Cat Boost is moderate, Light GBM is low. For tuning complexity, XGBoost is moderate, Light GBM is high because it has leaf-wise growth, and Cat Boost is low. And best use cases for XGBoost is general purpose models LightGBM is large data sets, and CatBoost is categorically heavy data sets. Next, let's jump into our hands-on exercise where we will train and compare LightGBM, CatBoost, and XGBoost models on a dataset, focusing on their ability to handle large datasets and categorical data. We will be using the Titanic dataset for this example. So let's get started. First, I'm going to create a new file, save it in my day5 underscore exercise.py. Here, let's start with importing pandas as PD. Next, we need from sklearn dot model selection import train test split. Next, from sklearn dot preprocessing import label encoder. Now let's load the Titanic dataset and do that by giving this URL. Just to check it out, I am going to open this in Chrome. Here it is. It has passenger ID, survived, P class, name, sex, age, SIB-SP, parched, ticket, fire, cabin, and embark. These are different feeds that we have. So I am going to go ahead and make sure we read the CSV file from this URL. Next, let's go ahead and select our features and target. Since we don't care about everything, features I will pick, or X, you can give whatever name you want. I want to use, let's copy this, paste it here. I need P class. I want to use, remove this, sex. I'll use age. I'll use fair, and did I remove it? And I'll use embarked. So these are the ones that I need for my features. Okay, let's close this. Next, for my target, I will use the survived column. Okay, perfect. So I have that. Let's handle the missing values. Handle missing values. To do that, I usually have, I know that there's missing values in age. So for age, I'm going to use the new fill NA method, where I will fill age with the value of df of age dot median. That's the function, and then I will say in place equal to true. Same thing I'll do for embarked, because that also has some empty values. I will say embarked, and instead of median, I'll use mode 0. So perfect. So I have that. Next, let's go ahead and encode our categorical variables. So for that, I'm going to say label encoders. Initially, I will set it as empty. Next, I'm going to say for column in, because I know in sex we have male and female, and in embarked we have another categorical variable, where, so if you see the data set here, embarked has this SC. So for those, I am going to say LE equal to label encoder, initialize that. Next, I'm going to say DF, depending on which column it is, I will say LE dot fit underscore transform that particular column. Next, I'll say label underscore encoders for the column, use LE. Perfect. So I have that. Next, I am gonna split the data. So for that, I will say X equal to df of features and Y equal to df of target, because we've just created df and the features here and target, but we are putting in the data frame right now, putting in the variables target and features. Now let's go ahead and call the train test split method, where I'll pass the features, the target, and my test size equal to 0.2 and my random state equal to 42. This will give us x underscore train, x underscore test, y underscore train, and y underscore test. Perfect. So I have that. Now next, let's go ahead and print some information like, oops. First, I'll say training data shape. Let's print that out, how it looks like, x underscore train dot shape. Same thing I'm going to do for test data shape x test data shape is x test dot shape. Perfect. So this will complete a step one, which is load and pre-processing the data. So let's go ahead and see if everything is fine. I'm going to say Python day 5, run it, and I have my shape with 712 rows and 5 columns, 179 rows and 5 columns. Perfect. So I have that data. Next step is to train a light GBM model. So for doing that, I am going to go up here and import light GBM as LGB. Next, from sklearn dot metrics, import accuracy score. So these are the two things that I need. Now let's go at the bottom and first train the light GBM model, that is LGB underscore model equal to LGB dot LGB MC, I think that's the classifier, M classifier. So LGBM classifier is the class that I'm going to use. So I'm going to initialize that LGB underscore model dot fit. Inside this, I'm going to say x underscore train and y underscore train. So my model is trained. Now next, go ahead and predict and evaluate. So predict LGB underscore pred equal to LGB underscore model dot predict. I am going to say x underscore test, and now go ahead and print f light GBM accuracy is accuracy score y underscore test LGB underscore pred, and I'll say let's use 0.4f because 0.2f is not always perfect. Now go ahead and run this code, and here is my light accuracy so it has some warning like no further splits with the positive gain. So I don't care about that. Start training from this is where it started, and then it said no positive gain, so that's why it stopped, and it gave me a light GBM accuracy of 0.80. So that's my accuracy. So clear this out. Let's go ahead and now let's train a cat boost model. So for cat boost model, I am going to go ahead and say from cat boost import cat boost classifier. So we just get the classifier directly from here. Now let's go ahead, and next step is to train the cat boost model. To do that, I will first say cat underscore features equal to p class comma sex comma embarked. So what I'm doing is I'm specifying which ones are the categorical columns, because as I mentioned, it has a native implementation for categorical columns for encoding them and making sure you don't need to do it yourself. Say cat model equal to cat boost classifier cat underscore categorical features equal to categorical features that I've created above. Next, I'll say verbose equal to 0. So there you go. We have our model created here or initialized. Then I'll say cat model dot fit. So train it with the data x underscore train, comma y underscore train. Then finally, we'll go ahead and predict and evaluate. Now it's exactly same as this here. Just the different is instead of LGB, we'll see cat pred. We'll say cat model pass x test print cat boost accuracy is accuracy score y test, and instead of this I'm going to use cat display it out. Let's compare both of them for now, light GBM and cat boost. So I'm going to go here, clear, it's already cleared. Let's run it. And there you go. We have our light GBM accuracy of 0.8 and we have cat boost accuracy of 0.81. So cat boost accuracy is better than light GBM. That's what I would say right now. Let's go ahead and compare it with XG boost. So I am going to go ahead and say from XG boost import XGB classifier. So that's our XGBoost classifier. I'm going to come down and do the exactly same thing that I did with the others two. I'll say train XGBoost model. So I'll say XGB underscore model equal to XGB classifier, and I'll say use underscore label underscore encoder equal to false. Actually, this is not useful anymore. I'll say eval underscore metric equal to log loss. The use label encoder was used for the previous version, so we don't need that anymore in the latest version. Unless you have the older model, then older version of XGBoost, then you have to specify use label encoder to be false. XGB underscore model dot fit, say x underscore train and y underscore train. Next I'll say predict and evaluate. This is exactly same as the previous one. I'll take that data, move it here, and I'll say XGB, copy that is XGB model, predict this data, and this one is XG boost, accuracy is accuracy speeds, this one, and remove the cat and put it here. Go ahead, clear it out, run it again, and we have light and all three of them 80, 81, and 77. Now if you compare, cat boost has the best one for this particular data set, light GBM is second best, and the worst that we have here out of the three is XG boost is the third one with 0.77 accuracy. Next step is, let's go clear this out, is to experiment with handling categorical data in cat boost. So we already did some encoding, but what I'm going to do here is I'm going to show you train cat boost without encoding categorical features. So we already encoded earlier for the other systems to use, but what if I don't? So what I'm going to do is I'm going to say cat underscore model underscore native equal to cat boost classifier cat underscore features equal to sex and embark. These are the ones that we encoded. So I'm going to say these are the ones that I want to use, comma verbose equal to 0. Next I'm going to say cat underscore model underscore native, and this one I will fit with the data. I'll say x underscore train and y underscore train, and then I'll predict and evaluate with this native model. I'll say cat underscore preds underscore native equal to cat underscore model native, and this one I'll ask to predict and I'll pass x underscore test. Now let's evaluate and see how did it do. I'll say cat boost native accuracy is accuracy score, pass it y underscore test and cat Pred's native. And if you want to do that 0.4f, we can do that here. So that should take care of, oh, I think I forgot a closing bracket here. Perfect. So I have that. Let's look at the accuracy for this one. Run it again. Cat boost. And now it's giving me an error saying accuracy score. Did I spell something wrong? Oh, close this. Accuracy score y test cat Pred's native colon. Something is not closed properly here. Okay, so I guess I had it. Clear it out, run it again. 81, 80, 77, and 8156. So if you look at it, the cat boost accuracy was already good, 8101. Now it's 8156. It's become much better without doing encoding. So you don't have to do anything when you're using cat boost. Just use the data as it is, and it will work perfectly fine. So I hope you were able to follow along and get things done. Today, what we completed was we understood the strengths and limitations of Light GBM, Cat Boost, and XGBoost. Then we gained some practical experience training and evaluating models with these different frameworks. And then we learned how to handle categorical data effectively with Cat Boost. Finally, we developed the ability to compare and choose the best framework for a given data set. I hope you were able to follow along. If you have any problems, if you had any issues while implementing it, or if you have any questions, let me know in the messages and I'll get back to you. Day 6, handling imbalanced data. Now, before handling, let's look at some of the problems caused by imbalanced data in classification tasks. So first, what is imbalanced data? Imbalanced data refers to data sets where one class significantly outnumbers the others. For example, in a data set with 90% negatives and 10% positives, a classifier predicting all negatives could achieve 90% accuracy while performing poorly for the minority class which is predicting positives. Now let's look at some of the challenges with imbalanced data. First is bias towards the majority class. Machine learning models tend to prioritize the majority class due to its frequency. Next is misleading evaluation metrics. Metrics like accuracy can be misleading as they do not account for the class imbalance. Limited information for minority class. Insufficient samples for the minority class can lead to underfitting. And what are the applications with imbalanced data? We have fraud detection, medical diagnostic, and anomaly detection. So think about it, if you have imbalanced data in any of these, it will cause a lot of problems. So now let's look at some techniques to handle this imbalanced data. First, let's look at the different resampling technique options. First is oversampling. You increase the number of minority class samples by duplicating or synthesizing new samples. Example here is SMOTE, synthetic minority oversampling technique, which generates synthetic examples. Next is undersampling. Reduce the number of majority class samples to balance the data set. Risk here is to loss of valuable information from the majority class. Next problem that we can solve is algorithm solutions. One is class weights. Assign higher weights to the minority class during the model training. Many algorithms like logistic regression, random forest have built-in support for class weights. Next, anomaly detection models. You can treat the minority class as anomalies, focusing the model on detecting them. Next, let's talk about evaluation metrics for imbalanced data. So we have F1 score, which we can use for harmonic mean of precision recall, focusing on both false positives and false negatives. ROC-AUC measures the ability to distinguish between classes across various threshold values. And we have precision recall curve, which focuses on performance for the positive class. Now let's jump into a hands-on exercise. We will apply SMOTE to handle class imbalance, train a classifier, and evaluate its performance using metrics like ROC, AOC, and F1 score. For the dataset, we'll use the credit card fraud detection dataset, which is highly imbalanced, containing transactions classified as fraudulent, which are minority class, or non-fraudulent, which is majority class. This dataset is available from Google APIs. So I'm going to go ahead and jump into creating a new file and call it day6 underscore exercise.py, and we'll start with importing pandas as PD. Next, I will use sklearn.model selection and import train test split. So we're just going to do load and explore the data set for the first step. So let's go ahead and load the data set. The data set is available at this URL, https storage.google.apis.com/download.tensorflow.org/data/creditcard.csv. So you can download from there or use it directly from there by saying pd.read.csv and pass the URL here. Next, let's go ahead and explore this data set. So I'm going to say print. You can directly open it in a browser. That's one way of exploring it. Or you can just say dataset info, because you can get some basic information here in a tabular format. Print df.info. And then next thing that I need is class distribution /n. To show that, I will say print df, the class that we have here, dot value counts function. So I'm going to call that. Next, let's also split the data set and keep it ready. X equal to, usually we do df dot, I am going to drop columns equal to class, because that's the one that I want to use as target, which is y equal to df of class. Perfect. Next, let's go ahead, x underscore train, x underscore test, y underscore train, and y underscore test equal to train test split, and pass it the x y test size equal to 0.2 and random state equal to 42. Perfect. So I have that. Let's go ahead and run this and look at the data set first before we start to train a classifier on the original data set. So Python day6, and there you go. We have our data set. It might take some time because, as you can see, it has 284,000 rows. It's probably in MBs, this particular file. The memory usage is 67.4 MB, and these are all the different columns that are available here. And class is what I'm interested in, which is int64 at the end of it, which is our target. So we can see all the data set, all the data over here. Pretty much all of them have data. Looks like there's no empty data, so it's all clean. That's good. So now with that, let's go ahead and train a classifier on the original data set. So for this classifier, I'm going to use the random forest classifier. So I say sklearn.ensemble. I am going to import random forest from there classifier, and then for metrics, I'm going to say sklearn.metrics. I am going to import our classification report. I will get the ROC AUC score, because that's what we will be using, as I mentioned. So now next step is, let's go ahead and train the random forest. Now if you remember how we did this earlier, we said rf underscore model equal to random forest classifier. I will use a random state of 42. I will also use class weight equal to balanced. Okay, this will balance our the data set. Next, I'll say rf underscore model dot fit and x underscore train and y underscore train. Again, the reason I said balanced here is because we have a lot of no class versus class, like non-frauds versus fraud in the data set. So balanced makes sure that it's properly balances the data sets based on the input that we provide. Next, I'm going to go ahead and predict and evaluate. To do that, I'll say y underscore pred equal to rf model dot predict, and I'll give it x underscore test to it. Next, I'll say print /n classification report. This is on the original data set that we have /n, and print classification report. For classification report, I need two. This is y test and y pred as parameters. So that's good. Next, I will say ROC underscore AUC equal to ROC AUC score. Pass it y underscore test RF underscore model dot predict. So this thing needs the predict proba. That's what I'll have to provide here. X underscore test, and inside that I'm gonna pick colon to 1. So that's what I'm going to pick from there, and that's what I need as input. So let's print this f roc dash auc on the data set with the value. So I'm going to say here roc underscore auc point to f. Perfect. So I have that. Next thing I'll have to do is apply the smooth to handle the imbalance. So I'm going to run that right now. If you want to see this, I can run it because it's going to take some time. So I'm going to leave it there. And at the same time, I will go here and apply smooth. So from imb learn dot oversampling. So this is a separate library and I've not used it before. So that's why it's not showing me, not pre-filling it here. So now to apply smooth, I'll say apply smooth here. To do that, I'm going to say smooth equal to SMOTE smooth random state equal to 42. I'll give that seed as same 42. Next, I'm going to say x underscore resampled y underscore resampled equal to smooth dot fit underscore resample. I'll pass it x underscore train and y underscore train. Let's see if the code ran, and it did run, but it's not complete yet. It's still doing the analysis over here. So I'll give it some more time and come back. Next, I'm going to go ahead and display the new class distribution after I have sampled the data. So for that, I'm going to say print /n classification class distribution after smooth is /n print. I need pd dot series, pass it y resampled dot value counts. This will show me the difference based on what it was before this class distribution and now after the class distribution. So if you see here, we have our class distribution from before where it shows this data here. 0 is 28,000. As you see, it's very biased, it's not balanced. And here is our ROC AUC because it took some time, it ran, and finally we got the ROC AUC, which is 0.95 for this, which is pretty good. Now, after applying smooth, let's print this part. So I'm going to clear it out, run it again. I'm going to leave it and go back and do the what I'm going to do is I'm going to train a classifier on the resampled data now. So I am going to use the same random forest. I'm going to say train random forest on resampled data. Do that. Where is my previous one? Here. We use this RF model underscore smart. I'm going to say random forest classifier. I don't need to have to specify because it's resampled now. RF more fit, oops, sorry, underscore smart fit. And instead of this, I'll give X resampled and Y resampled. That's it. Now let's go ahead and predict. And so same thing what we did here. I'm going to predict and evaluate based on this. In this particular case, RF model, let's say this also smart, YPRED smart, RF model smart, predict X of test, print with this print report, classification report, let's say with smart is classification report Y test and YPRED smart. That's what I see. ROC AUC, let's calculate that also. Let's see what is the ROC AUC score. ROC AUC with smart is ROC AUC score, Y test, RF model, and this time smart, predict, proba, X test, good, and then ROC AUC with smart is ROC AUC smart. Perfect. So that's my final thing. Now, if you want to compare the results, we can compare separately, but we already have it here. So I'm not going to print more statement to compare. We'll just go up and down a couple of times to see this data values. I am going to save this, go back here, and here you'll probably see this was after I created the resample data. If you see the class now here, 200 and sorry, 227,451, and it was 284,315. So you can see clearly the difference. Now with the data, before it was 0.95, now with the smart, let's see what is the value. I'm going to run it and leave it for a little while until it completes. It took a little bit time, but finally we have our results here. So this is our initial class distribution where we have zeros bunch of times and ones, which are fraudulent charges at 492. But after the smart effect, we have 227,000 equal number of positives and negatives. So it added some synthetic data to it. And if you look at the ROC AUC is 0.95, and after smart the ROC AUC is 0.98, much better. And here is a classification report. If you look at that, it's a little bit different for different fields, but that's what you get after smart and before smart. So I hope you were able to follow along and get these where we were able to have a data set with lower recall and F1 score due to the class imbalance, and we applied smart and improved the recall and F1 score and addressed the imbalance, and we highlighted the importance of handling. If you see, handling the imbalanced data in improving the model's performance. So I hope you were able to follow along. But today we went and understood the challenges caused by this imbalanced data sets and their impact on machine learning models. We learned techniques like smart, oversampling, and undersampling to handle class imbalance. We gained proficiency in evaluating models for imbalanced dataset using F1 score and ROC AUC, and we observed how handling imbalance can significantly improve the performance of machine learning models. I hope you were able to follow along. If you had any questions or issues, let me know in the messages and I'll get back to you. Thanks. Welcome to day 7 and the last day of our week 7. And today we'll be looking at ensemble learning project, comparing models on a real data set. So we will be using the customer churn data set this time, and I've already downloaded it and put it in my folder. Here I have telco customer churn data set that is available, and you can download it from the website. Now, before that, let's go over some of the tools that we need to start. First, building and evaluating multiple ensemble models. Now, why compare ensemble models? Different ensemble techniques, example bagging, boosting, they excel in different scenarios. Comparing them helps identify the most effective model for a specific dataset or problem. Ensemble methods to consider are: first is bagging, which is random forest, reduces variance by averaging predictions from multiple independent models. Works well with high variance models like decision trees. Then we have boosting. Example is gradient boosting, XGBoost, and light GBM. It reduces bias by sequentially correcting errors from the previous models, effective for complex patterns and imbalanced data sets. Comparing bagging and boosting. So for bagging, it builds models independently using random subsets of data. It's robust against overfitting with strong base learners. Whereas boosting, it sequentially builds models focusing on hard to predict samples, requires careful tuning to prevent overfitting. Next, let's talk about model performance on balanced versus imbalanced data. Now, challenge with imbalanced data that we saw earlier is models may prioritize the majority class, leading to poor performance on the minority class. Evaluation metrics, we use accuracy, which may not reflect true performance for imbalanced datasets. F1 score balances precision and recall, focusing on the minority class, whereas ROC AUC evaluates the model's ability to distinguish between classes across different thresholds. Now, let's jump into our hands-on project, which is the ensemble learning and model comparison. Today's the objective is to train and compare multiple ensemble models on a real-world data set, analyzing their performance under balanced and imbalanced conditions. Dataset will be using the customer churn dataset, which predicts whether a customer will leave a service provider based on demographic and usage data. So I have the data already downloaded, which is our telco customer churn data, and it has that churn field at the end which says yes or no depending on when they will leave or not leave and their information. Now let's go ahead and first create a file, save it in our day 7 exercise. Next, first let's go ahead and import. So first we'll load and explore the data set as we've been doing. Pandas as PD. Next, let's load the data set, and my I don't have a URL here, so I'm going to say df.pd.readcsv, and the file name is, let's go ahead, get the file name, telco customer churn.csv. Now let's, from this data set, we already saw the data set, but let's display the data set info and preview some of that. So I am going to say print dataset info /n and print df.info. Next, I will say print /n class distribution /n and print df. One that I'm interested is churn dot value count. So we'll count how many yeses and how many no's are there. Next, I'm going to say print /n sample data /n df dot head. So we see first 5 rows from the set. So let's go ahead and say Python day 7, and here we go. We have no 5174, which is 5 times more or 4 times more than yes, which is 1869. I think it's 3 times more. Anyways, so, and the class distribution, these are different class info which talks about what are the different fields that are there. Churn is what I'm interested in, and if you look at the sample data, this is the sample data we have here. Perfect. So we have that. So next step is to pre-process the data set. So what I'm going to do is I'm going to handle missing values. Do we have any missing values? Looks like it's perfect, but still, if we had to handle the missing values and encode the categorical features, how do we do that? Next, we'll scale the numerical features for boosting the model. So I'm going to go here, and from sklearn, I will use the pre-processing inside there, and from there I will import a label encoder and standard scalar. So first, let's say if there were some values missing, handle missing values. So for example, if we had df of total charges, So that's a field over there, right? If I'm not wrong, total charges, which is also an object. So for that, I am saying pd dot to numeric. So I'm going to convert that. So total charges is an object, and that's why I want to make sure that it's not numeric anymore. Sorry, not object, and it's numeric. Df of total charges, comma, errors equal to, I'll use course. Okay, perfect. Next one, I'm going to say df of total charges dot fill na df of total charges dot median in place equal to true. I'm so used to using the old method. I know if I run this, it will probably give me a warning saying that I'm using the wrong format. So I'm going to say df dot, so the way it shows you here too, that call the method, and then inside the method you say that the column total charges is, and then give it the value that you want to give, which is this value here, and then specify in place equal to true. So if you do that, you will not see this warning. There you go, no warning. Perfect. Next I want to do is encode categorical variables. For that I'll say label underscore encoder equal to label encoder, and for column in df dot select underscore d types, inside there I'm going to say include equal to, I need object because it's a type object, dot columns. For these columns, what do I want to do? So for each column I'm going to say if column is not equal to churn, because I don't care about churn, then I'll say df column, whatever that column is, equal to label encoder, and label encoder dot fit transform df of column. There you go. So that will take care of the encoding. Next I will go ahead and encode the target variable, since we said we are not going to do that churn here. So I'm going to say target variable by saying df of churn equal to label encoder dot fit transform, and then df of churn is what I'll pass. So that's done. Now I'll say next scale the numerical features. So for scaling the numerical features, we'll use the standard scalar. So I'll say scalar equal to standard scalar. Numerical features that I'm interested in are, let's see from the list here, I'm going to take tenure. I am going to take, do we have monthly charges? Yes, monthly charges, and we'll take total charges. So these are the three that we'll take, and we'll say df of numerical features equal to scalar dot fit transform, and to it I'll say df of numerical features. Perfect. So that takes care of that. Now let's go ahead and split the data set. Split the data set by using x equal to df dot drop columns equal to churn. Let's see, df dot drop. Perfect. Next y, I mean when I say split, I mean features and target y equal to df of churn. Perfect. So I have that. Now that has been done, let's go and handle the imbalance. I mean, this is optional, but it's good to do. So I'm going to go ahead and so from imb learn dot over underscore sampling, I will import smart, and from sklearn dot model selection, I will import train test split so we can split the data set actually. I'm going to go here and say split the data set x underscore train, x underscore test, y underscore train, y underscore test equal to train test split, and to this give x, I'll give y, I'll give test size 0.2, I'll give random state equal to 42. So there you go, we have that. Now let's go ahead and apply smart to it. To do that, we've done this earlier this week. Say smart random underscore 42. Next I'll say x underscore train underscore resampled comma y underscore train underscore resampled equal to smart dot fit underscore resample. I pass it x underscore train comma y underscore train. So this is, as I say, smartified. Now, or resample, just to say in simple words, display class distribution after the smart. So now we have print slash n class distribution after smart, so we can compare, because we did before earlier we saw the class distribution was 5000 to 1800. So I am going to say smart slash n print pd dot, we get the series where we pass y underscore train resampled and get the value counts of those. If I run this now, clear it out, and you see 4138, 4138 equal numbers. So now the data is not imbalanced. Next step is to train the multiple ensemble methods models. So I am going to go here and get my models. So from, we'll get random forest from sklearn dot ensemble, import, I will get random forest classifier. I need xgb classifier, so that is from xg boost. I can import xgb classifier. Next I want from light light gbm, I need import light gbm, I need lgbm classifier, if I'm not wrong. From sklearn dot metrics, I need to import I need classification report, sklearn dot metrics classification report, and I need ROC AUC score. Perfect. Now let's go ahead and train using all these three different models. So first I'll say train random forest, then we will train xg boost, and then we will train light gbm. So let's get started. For this, I'm going to say rf underscore model equal to random forest classifier, random state equal to 42. Perfect. Rf underscore model dot fit, and to this I'll pass x train resampled and y train resample. Perfect. Y underscore pred underscore rf equal to, now to predict, rf model dot predict and pass x underscore test. Next I'll say ROC AUC score for RF equal to ROC AUC score y underscore test, pass RF underscore model dot, if you remember this, predict proba, and I'll pass x underscore test of colon comma 1. So I have that. That's perfect. Now to do the same thing 3 times. So instead of doing 3 times, I'm going to copy this, paste, and paste. Now for the next one, which is XGB, XGB, instead of random classifier, it is XGB classifier. Now I'll read the random state here because I need that for this too, but it needs one more, which is metric equal to log loss, okay, comma. So that's good. And now I'll say XGB model fit. I'll pass the same resample data. Next, instead of this, I'll pass ypred XGB and XGB model predict xtest. ROC for XGB is ROC score y RF model, not RF model, XGB proba x. Perfect. So this is exactly same. Next, same thing for this one. I'm going to use LGB, and here I am going to say LGBC classifier, and it needs the random state 42. Leave it as it is. Go ahead, remove this, remove this, remove this, remove this, and remove this. So let's just start again. LGB, LGB model fit, train perfect. We have Y LGB model predict, ROCUC LGB score is this, Y test LGB predict proba X test. Perfect. So I have all those things. Now to display the data, I'm gonna say classification reports. Let's create the classification reports first. Say print. First one is random forest report /n, comma, classification report, pass it y test and y pred RF, because this is the random forest predictions. Next, for XG boost, we are going to say /n, again classification report y underscore test, comma, y underscore pred, and this is XGB, so XGB. Next one is for light GBM report /n, comma, classification report to it passed y underscore test, y underscore pred LGB. Perfect. So all of 3 of them. Now let's display ROC AUC comparison. So for that, I'll say print. Let's create a header. I'm going to say ROC AUC scores /n. Next, I'll say print f of, forgot the bracket. First one is random forest ROC underscore AUC RF point to F. Let's make sure everything is properly closed. Second one and third one. So next one was XG boost. For that, it was XGB. Next one was light GBM. That was LGB. Perfect. So I have everything up and ready. Let's run this project and see all the comparison. And there you go. We have the ROC AUC scores for random forest 0.83, XG boost is 84, and LG light GBM is 0.84. And above here, we have the classification reports for first one is for our random forest, XG boost, and light GBM. And before that, as we saw the churn data here. Perfect. So everything worked out pretty fine, and I hope you were able to follow along. And if you look at the ROCAC course, is pretty good. So we went through first with random forest. We observe its ability to generalize with the bagging. Then XG boost, we highlight its performance on imbalanced data sets, and light GBM emphasizes its speed and efficiency on larger data sets. That's what we have learned from here. Now let's go ahead and summarize what we learned today. Today we learned how to pre-process and handle imbalanced data from machine learning tasks. We gained hands-on experience training and tuning multiple ensemble models. We compare bagging and boosting methods to understand their strengths and weaknesses. And finally, we evaluated model performance using appropriate metrics for imbalanced data sets. I hope you were able to follow along. And if you have any issues or have any questions, do let me know in my messages and I'll get back to you. Welcome to week 8, Model Tuning and Optimization. Our week will start with day 1 introducing to hyperparameter tuning. Day 2, we will look at grid search and random search. Day 3, we look at some advanced hyperparameter tuning with Bayesian optimization. Day 4, we'll be looking at regularization techniques for model optimization. Day 5, we'll be looking at cross-validation and model evaluation techniques. Day 6 will be about automated hyperparameter tuning with grid search CV and randomized search CV. And finally, day 7 will be our optimization project where we will be building and tuning a final model. So let's get started with week 8. Welcome to week 8, day 1, Introduction to Hyperparameter Tuning. First, let's go ahead and understand the difference between parameters and hyperparameters. So first, what are parameters? Parameters are values learned by a machine learning model during training. They are adjusted to minimize the loss function and optimize predictions. Examples of parameters include the coefficients in linear regression, also the weights and biases in neural networks. We've used some of them already, but we're going to use quite a lot in the coming few weeks. Now, what are hyperparameters? Hyperparameters are setting defined before training that influence how the model learns from data. They are not learned from the data, but instead control the training process. Examples can be the tree depth, maximum depth of decision trees, learning rate, step size for gradient descent, and number of estimators, number of trees in an ensemble model. And we have used quite of these hyperparameters in the last week. And now we will dive deep into more of these. Now let's talk about importance of tuning hyperparameters. Now why tune hyperparameters? First, it improves the model performance. It's optimal hyperparameters that help models generalize better, reducing overfitting and underfitting. Enhance efficiency. Proper tuning can reduce training time and computational resources. Adapt to problem specific needs. Tailoring hyperparameters ensures the model fits the dataset's characteristics. And these are some of the things that we have already noticed. Now let's talk about common hyperparameters in popular models. Now, based on the things that we have done, especially with decision trees and random forest, we know that we've used the max depth, which limits the depth of trees to avoid overfitting, min samples split, which is the minimum samples required to split an internal node, and number of estimators, which is total number of trees in a random forest. Now, gradient boosting models, if for example we used XGBoost and light GBM, we have learning rate, which determines the contribution of each tree. We also use subsample, which is the fraction of training data used to train each tree. And then we also used max depth, which limits the complexity of individual trees. Let's talk about neural networks. In neural networks, we have the learning rate, which is the step size for weight updates. We also use number of layers, which determines the depth of the network. And then we have batch size, which is number of samples per gradient update. Now, with all this knowledge, let's go and jump into a quick hands-on exercise where the objective is to train a model with default hyperparameters, evaluate its performance, and manually adjust a few hyperparameters to observe their impact on results. Now, the dataset we'll be using here is Iris dataset, which is an optimal dataset already, but we'll use it because it's a multi-class classification problem and it will be a good sample to walk through, but we will not be seeing the impact on the results with hyperparameter tuning because it's always optimal. So, but it gives you an idea or a guide on how to approach this problem. So step one is to load and explore the data set as usual. So I'm going to go ahead, create a new file, Python file, save it in my day one. I'm going to call it day one underscore samples or exercise one. And here, first, let's go ahead and get the data set. So I'm going to say from sklearn dot datasets, I want to import load iris. Next, I'm going to say from sklearn dot model selection, I want to import train test split. Also want to import pandas as PD. Now let's go ahead and load the data set. First, I'll say data equal to load iris, and then our features and target, I'm going to say data dot data and data dot target. Oops. Next, I will split the data set. Now to split, I'll get x underscore train, x underscore test, y underscore train, and y underscore test. Now this I get from train test split, and I can say x, y, test size equal to 0.2 and random state equal to 42. So once I have these, I'm going to go ahead and display some data set info, and for that I'll say print f feature names. If you already forgotten it, that's why it's always good to brush up on these, especially when you're working on a bunch of different data sets on a daily basis. Names. Next, I want the class names, and that is data dot target names. There you go. Save it. I'm going to run it here. Let's make sure I'm in the right folder. Python day one. And looks like I have a typo here. Feature names. Let's try it again. And there you go. We have our, let me clear it so we don't see that error. Here you go. Feature name, sepal length, sepal width, petal length, and petal width. Class names are Setosa, Versicolor, and Virginica. So those are our targets. Now let's go ahead with step 2, where we will train a model with some default hyperparameters. In this case, we'll train a random forest classifier with the default setting and evaluate its performance. I am going to say that first I need the random forest classifier. For that, I'm going to say sklearn dot ensemble import random forest classifier. From sklearn dot metrics, I can say import, I need accuracy score, classification report. So that's once I have that. Next, I am going to say train random forest with default hyperparameters. Also, I've seen that I've not used panda because I already have the data set locally, so I don't need that. If I need it, I'll add it again. I'll say rf underscore defaults default is equal to random forest classifier, and I'm going to use random state equal to 42. That's all I have to do here. And I'll say rf underscore default Now I will fit with x underscore train and y underscore train. Next, let's go ahead and predict and evaluate. To do that, I'll say y underscore predict underscore default equal to rf underscore default dot predict and pass it x underscore test. Next, I'll say accuracy for default equal to accuracy score and pass it y underscore test and y underscore predict default. So we have our things here. Now let's go ahead and print them. Say print default model accuracy is accuracy default 0.4f. Next, I'm going to say print /n classification report /n, and here I'll say classification report, and it needs the same y underscore test and y underscore predict default. So perfect. So this is our training a model with the default hyperparameters that we have. So let's go ahead and run it. It'll give me the feature names, and then it says default model accuracy is 1.2. It's pretty good. What if I use the breast cancer data? So this has 0.98, 0.7. So it's a little bit lower than the actual this one, the iris database. So I'm going to change it to this just to play with it. So I have that data, I have predicting here. Next step is to manually adjust the hyperparameters. Now we're using the default ones here. So let's go ahead and modify some key hyperparameters such as n estimators and max depth to observe their impact on the model performance. So I am going to say train random forest with adjusted hyperparameters rf underscore tuned equal to random forest classifier, and this I'm going to give the hyperparameters. First I'll set the n estimators equal to 200. I've already seen in last week that giving the maximum is better. You can increase the number of trees if you want. Max underscore depth equal to, I'll give 5, so that's the limit of the tree depth, and then random state, so it generates the same data every time I run it. Rf underscore tuned dot fit, and I'll fit x underscore train comma y underscore train. Now next, let's go ahead and predict and evaluate based on the hyperparameter setting. So I am going to say here y underscore pred underscore tuned equal to I'll say rf underscore tuned that you created above dot predict, and I'll pass x underscore test to it. Next, I'll go and say accuracy, not default this time, but tuned equal to accuracy score, give it y underscore test comma y underscore pred underscore tuned. Now let's go ahead and print the results. I'm going to say f of tuned model accuracy is accuracy tuned 0.4 f, and then I'll say print /n classification report /n is classification report, pass it y underscore test and y underscore pred tuned. That's good. It looks good. Everything is tuned, and now we can compare those results here and see how it looks like. So I'm going to save it. It's already cleared, so I'm going to run Python day 1 and make it a little bigger so we see the difference. So if you see, before it was 9649, after the tuning it's also 9649, and these are my different numbers for different parameters. I can go ahead and increase the number of 33 is the number of estimators. Let's see if it increases. 9649, I think that's the best it can go. So this is the actual process. First, you can use a particular model, or in this particular random forest classifier, train it, and then you can also tune the hyperparameters and test if it makes any difference. Sometimes it does, sometimes it doesn't. So I hope you were able to follow along, and if you have any questions or had any issues running this, let me know. So just to summarize, today we went and understood the difference between parameters and hyperparameters in machine learning models. We recognized the importance of hyperparameter tuning for optimizing model performance. We did some hands-on where we trained models with default and manually tuned the hyperparameters. And we learned how hyperparameter adjustment might influence key metrics like accuracy and classification report. In our case, we did not see that, but it does if you use some of the data that is available. But if you had any issues or problems and have any questions, let me know and I'll get back to you. Day 2, Grid Search and Random Search. Today, let's go ahead and first let me introduce you to Grid Search and Random Search. What is Grid Search? Grid Search is a method of hyperparameter tuning that systematically evaluates all possible combination of hyperparameter values within a specified grid. Now, how does it work? You define a range of values for each hyperparameter, train and evaluate the model on each combination of hyperparameter values, and select the combination that yields the best performance. And we've seen some of this in the earlier weeks, but we're going to go more deep into it today. Now, what is random search? Random search is an alternative method where hyperparameter combinations are sampled randomly from the specified ranges. Now, how does it work? You define ranges or distributions for each hyperparameter. Next, you randomly sample a specified number of combinations, and then finally, you train and evaluate the model for each sampled combination. Let's look at some of the pros and cons of each method. I've created a tabular method for it where we're going to look at features, grid search, and random search. For example, exhaustiveness in grid search evaluates all combinations. In random search, randomly samples combination. As per time efficiency, grid search is computationally expensive for large grids, whereas random search is faster for large parameter spaces. In case of exploration, grid search is limited to predefined grid, whereas random search explores more diverse ranges. The best use case for grid search is small parameter spaces, whereas for random search, it's large parameter spaces with time constraints. Next, let's look at the practical guideline on choosing the search ranges. What we do is first we start with a broad range. Use random search to explore large parameter spaces and identify promising ranges. Next, you refine with grid search. Narrow the search space based on random search results and perform exhaustive grid search for fine tuning. Finally, understand the model sensitivity. Some hyperparameters, example the learning rate, require fine granularity, while others, example the number of trees, can have coarser steps. Now, with this in mind, let's jump into our hands-on exercise where the objective is to implement both grid search and random search for hyperparameter tuning, compare their efficiency, and analyze the impact on the model performance. The dataset we'll be using again will be the iris dataset, which is the multi-class classification problem. So let's jump into and load and prepare the dataset. So I'm going to create a new file, save it as day2 underscore exercise. Here I'm going to from scikit-learn, I will get the data sets. As I mentioned, I'm going to use load iris. Now from sklearn dot model selection, I will import train test split. Let's go ahead and load the data set. Data equal to load iris. Next, I'll say features and target equal to data dot data and data dot target. So I have that. Let's go ahead and split the data set. To do that, I will use the train test split and get x underscore train, x underscore test, y underscore train, and y underscore test. Again, from train test split, I'll pass x, y, I will say test size equal to 0.2 and random state equal to 42. There you go. So I have that. Next, let's go ahead and display dataset info. Again, I'll go ahead and print f of feature names, that is data dot feature underscore names. Next, I'll say print f of class names. For that, I'll say data dot target names. So let's, to make sure that everything is perfect here, go here and say python day dat2. Okay, I think I misspelled it, dat2.ex, and I have my feature names and class names. So perfect. Next step is to implement a grid search. So we'll define a grid of hyperparameters for random forest model and perform exhaustive search using the grid search CV, which means I'll need to import first from sklearn dot ensemble. I will import the random forest classifier. Next, from model selection, I need the grid search CV. Just import it there along with the train test split. And then I need metrics. In this case, I need accuracy score. You guessed it right. Next step is to define here the hyperparameter grid with some random values. Param underscore grid equal to, inside this grid I'll use first n underscore estimators, and this I will say I want to do a search based on 50, 100, 150. Next, I want to say max depth I want to use is, in this case, I'll say none, maybe no depth, 5 or 10, whichever works best. Next, I'm going to say the minimum underscore samples to split is equal to, so either do 2, 5 or 10 and tell me how it turns out. So now to initialize this grid search, I will first move it up. Let's keep it so we can see that. I'll say grid underscore search equal to grid search CV, and to this it needs the estimator first. For estimator, I'm going to say random forest classifier, random state equal to 42. Next, it needs the parameter grid, param grid equal to param grid that we have created on line number 18. Next, cross validation, I'll set a value of 5. I'll say scoring that I need is accuracy, and then I'll say number of jobs to run equal to -1. Again, the n jobs, which is number of jobs to run in parallel, when I say -1, it means use all the processors. So if you have multi-processor machines, it's always faster. If you give numbers, it will use that many processors. So finally, let's go ahead and perform the grid search. To do that, I'm going to say grid underscore search dot fit, and I'll pass x underscore train and y underscore train to it. Now let's go ahead and evaluate the best model available for, evaluate the best options for this particular model, where I'm going to say best underscore grid underscore model equal to grid search dot best estimator. So what is the best estimator? I'll say y underscore pred underscore grid equal to best grid model dot predict by the values of x underscore test, and then accuracy score or accuracy of the grid equal to accuracy score, and I'll pass y underscore test and y underscore pred grid. Perfect. So finally, let's go ahead and let's look at the best. First, let's look at the best hyperparameters for the grid search. I'm going to say grid search because I'm going to use one more later. So it's easier to compare. And here I'm going to say grid search dot best params underscore. Perfect. And next I will say f of grid search accuracy with those best parameters is accuracy grid 0.4 f. Perfect. So let's run this and let's check if everything worked fine. I have my feature name, class names, best hyperparameters, max depth from the values that I have provided. It said none is the best. Minimum sample split is 2 is the best. N estimators 150 is the best. And grid accuracy score with all these parameters is 1.0, which is 100%. So perfect. Now clear this out. Go back here. Our next thing is to implement a random search. Now what we're going to do here is we define a parameter distribution for random search and evaluate its performance using the randomized search CV, and that we can get from, again here, randomized search CV. So now that we have randomized search CV, let's go ahead and define hyperparameter distributions. So to do that, I am going to use something similar that we used above here. And here I'm going to say, instead of parameter grid, I'm going to say parameter distributions. N estimators, I am going to say np dot range. So I am not going to give 50 to 200 and get 10 different values of those. For max depth, I'm going to say none, 5, 10, let's use 15. For minimum sample split, I'll use 2, 5, 10, and then give 20. You can always create a array like this. Now I'm using np, which means I need to import numpy as np, so that warning will go away. Next, I'm going to go ahead and initialize a random search. To do that, I'm going to say random underscore search equal to our randomized search CV. Now it needs a bunch of different parameters. Let's start with the estimator. Estimator equal to, I'm going to say random forest classifier, random state equal to 42, exactly same as before. Next, I'm going to say parameter distributions equal to param dist. Next, I will say n underscore iterations, how many iterations I wanted to run it for, like number of random combinations to try. I'll say 20. And then the cross validation is equal to, I'm going to set this to 5. Next, I am going to say scoring that I want to use is accuracy. Next is number of processors, so n of jobs equal to -1, which means use everything that you have, and then random state equal to 42. Perfect. So I have my random search done here. Now let's go ahead and perform the search. To perform the search, I'm going to say random search dot fit and pass it x underscore train and y underscore train. Perfect. So that will create our random search, and now let's go ahead and evaluate the best model. So I'm going to say best underscore random underscore model equal to random search dot best estimator. Then I'm going to say y underscore pred underscore random equal to best random model dot predict, and I'll pass x underscore test to it. Next, I will say accuracy of this random is accuracy of accuracy score and pass it y underscore test and y underscore pred random. Now let's go ahead and print this. I'm going to print saying f best hyperparameters for random search is random search dot best parameters. So that will give me the best parameters, something that we did same for grid. Next I'll say f of random search accuracy is accuracy of random 0.4f. Now it's going to give me 1.0 itself for this too, but if you have your real data set, you can try it out with them, and then we can compare here the grid search and the random search together. So I'm going to go here and go back and run this. So we have, this is for features, class names, best hyperparameters for grid search versus this. Now here the n estimators is 140. So if you see here, it picked 150 here because we gave it an option, but here we said pick from a range of items, and that's why it picked 140. Minimum sample split, it took 5, and max depth is none. And if you see, the grid search accuracy and random search accuracy both is 1.0, so it's 100%, so that's good. But again, if you have a real data set with your own numbers and all skewed numbers in there, it will be best to test it out, the grid search accuracy and the random search accuracy. So I hope you were able to follow along with this. If you have any issues implementing this, let me know and I'll get back to you. Just to summarize, today we went and understood the differences between grid search and random search for hyperparameter tuning. We learned how to define parameter grids and distributions for systematic and random exploration. We gained some practical experience implementing both methods and analyzing their efficiency, and we developed intuition for choosing appropriate ranges and tuning strategies. Now, if you are playing with this, let me know how it goes. If you have any problems or issues or have any questions, let me know in my messages and I'll get back to you. Day 3, Advanced Hyperparameter Tuning with Bayesian Optimization. First, let's go and see what is this Bayesian optimization. So here is an introduction to Bayesian optimization. First, what is Bayesian optimization? Bayesian optimization is an advanced method for hyperparameter tuning that balances exploration, which is searching for new regions, and exploitation, which is refining promising regions. Unlike grid or random search, which are blind to past evaluations, Bayesian optimization uses a probabilistic model to guide the search for optimal hyperparameters. Now, how does it work? We have a surrogate model which builds a probabilistic model, example a Gaussian process, of the objective function based on prior evaluations. Acquisition function. It balances exploration and exploitation by choosing the next hyperparameters to evaluate based on predicted performance and uncertainty. Then we have iterative refinement, which updates the surrogate model after each evaluation, refining the search. Now, why use Bayesian optimization? It's efficient for high dimensional and expensive to evaluate functions, and it reduces the number of evaluations required to find the near optimal hyperparameters. So let's jump into using libraries for Bayesian optimization. Some of the popular libraries that we use here are, first is HyperOpt, which simplifies Bayesian optimization for hyperparameter tuning. It works with fmin to minimize objective functions over a parameter space. We also have Optuna, which is a flexible and user-friendly library for hyperparameter optimization, and it supports dynamic search spaces and pruning of unpromising trials. Let's look at understanding exploration versus exploitation a little bit more. Now, what is exploration? It focuses on sampling hyperparameters from unexplored regions, and it's useful for identifying new areas of high potential. Whereas exploitation, on the other hand, focuses on refining the search around regions with known high performance, and it's useful for fine-tuning near optimal hyperparameters. Next, let's talk about Bayesian's optimization's advantage. It balances these approaches using the acquisition function to minimize unnecessary evaluations while improving the results. That's why it stands out better than the grid or random search. Now let's jump into a hands-on exercise implementing this. The objective here is to apply Bayesian optimization using Optuna to tune an XGBoost model and compare the results with grid search and random search. So our steps that we will follow is, first let's go ahead and create a new file, call it day3 underscore exercise. Now first we will go ahead and load and pre-process the dataset. The dataset that we will be using here is the breast cancer dataset from scikit-learn as an example. So let's go ahead and go sklearn dot datasets import load breast cancer. Next, from sklearn dot model selection, I will import the train test split. Next, from sklearn dot preprocessing, I will import standard scalar, and then I'll import pandas as PD. Now let's load the dataset. To load the dataset, I'm going to say data equal to load underscore breast cancer. Now the reason I'm do it over and over again every time is just for better practice, and if you're jumping in directly to this video, you can still follow along. And also another goal is for you to follow along and do it along with me, x comma y. But if you want to jump directly to the next steps, you can do that. Data comma data dot target. Next, I'm going to go ahead and split into training and test sets. So I'm going to say x underscore train, x underscore test, y underscore train, and y underscore test equal to train test split x comma y comma test size equal to 0.2 and random state equal to 42. Perfect. Now next, let's go ahead and standardize the features. So I'm going to say scalar equal to standard scalar. Initialize that. X underscore train equal to scalar dot fit underscore transform and pass it x underscore train. And for the testing set, x underscore test equal to scalar and just transform it with x underscore test. Perfect. So we have that. Now let's go ahead and print our training data shape. So we see how many items we have. X underscore train dot shape, and then also look at our test data shape. For that, I'll say x underscore test dot shape. Perfect. I'm going to run this. This is Python day3 underscore ex. There you go. We have our training data set with 455 rows, 30 columns, and our test data shape is 114 rows with 30 columns. Perfect. So now we have that ready. Let's go and define a baseline XGBoost model. So we will train a baseline XGBoost model to establish a performance benchmark. So for that, I'm going to go up first, and from XGBoost, I will import XGB classifier. Now, if you don't have XGBoost installed, you can always say pip install XGBoost and it will install it for you. From sklearn dot metrics, I will import accuracy score. Looks like I'm not using pandas, so I'm going to get rid of that. And here now I'll say train a baseline XGBoost model. To do that, I'm going to say baseline underscore model equal to XGB classifier and pass it. I'm going to say first evaluate the metric equal to log loss, and then random state equal to 42. So that kind of initializes that. Next, I'm going to say baseline underscore model and fit it with the data. I'll say x underscore train, or train the data, train it with the data, however you want to call it. Next, I will go ahead and evaluate the model. To do that, I'll say baseline underscore preds equal to, we'll use the baseline model and predict the x underscore test. Next, I'll say baseline underscore accuracy. I will use the accuracy score and say y underscore test comma baseline preds. So that's what I am doing here. Next, let's take and go ahead and take it and print this thing. Baseline xg boost accuracy is accuracy baseline accuracy 0.4 f. Perfect. Let's look at how it looks like right now without doing anything else. And baseline xg boost is 0.9561. Perfect. Now let's go ahead and apply the Bayesian optimization using something called as Optuna. If you don't have Optuna, you'll have to install that by saying pip install Optuna, but I think I already have installed, so I'm going to say import Optuna, and then from xg boost I will import, or I think I already imported the xgb classifier, and my accuracy is there. So Optuna is all I needed here. So once that is done, I'm going to go ahead and define first I'll define the objective function for Optuna that is required. So for that, I'll say define, I'll say objective and the trial data that is passed to it. Now we'll define the hyperparameter search space here. I'm going to say params equal to, now it needs a bunch of different things. First, it needs a n underscore estimators. You can look at the documentation for this if you're interested in. And I'm going to say trial dot, from the trial I'll say suggest underscore int values for n underscore estimators from 50 to 500. Next, I'm going to say I need max underscore depth. For this, I will do the same thing. Trial suggest, instead of n estimators, I'll say max depth. And this time max depth can be anywhere from 3 to 100. That's what I'll ask it to do. Next one is learning rate. And I'll say trial dot suggest. In this case, learning rate is float. So I'm going to say float. And this will go from anywhere from 0.01 to 0.3. Next I need to do is for subsample. For subsample, I'm going to say trial suggest float subsample, and subsample can go from 0.6 to anywhere to 1.0. Next, I want to do it for column sample underscore by tree suggest. In this case, it's float again, and this float can be same 0.6 to 1.0. Next is gamma. For gamma, I will say suggest and float again gamma from 0 to 5. So that's good. Next I need is alpha, reg underscore alpha is trial dot suggest, and reg alpha 0 to 10. So it needs 3 parameters, gamma, alpha, and lambda. So I'm going to say reg underscore lambda is reg lambda 0 to 10. So these are all floats. Perfect. So that's done. Now next step after this is to train XGBoost model with the suggested parameters from above. So I'm going to say model equal to XGB classifier. I'm going to say evaluate underscore metrics. I'm going to use the same thing, log loss, and then random state equal to 42. Same values that I always use, and then I'll say model dot fit x underscore train and y underscore train. So that's done. Next I will do is evaluate model on validation set. So this is where I'm going to say preds equal to model dot predict and pass x underscore test to it. Accuracy is equal to accuracy score and pass y underscore test comma preds. Then I'll return this accuracy. The thing that I forgot to add is this parameter. So XGB classifier, I need to train this with the parameter. So another thing that I have to add here is star params. This is where we pass the parameter to XG classifier. Now, once this is done, let's go ahead and go outside and create an Optuna study. That's what it's called, Optuna study. Study equal to, I'll say Optuna dot create underscore study. That's the function that they give us, and you can give a direction. I can say the direction is use maximize, and then study dot optimize. I'm going to say pass the objective, which is the function that we created, and n underscore trials equal to 50. So it will take this trials, add it as a parameter here, and run this, and it will give me the best parameters in the study best parameters. So to do that, I'm going to say best hyper parameters are print. So first I'll say give me the best hyper parameters from the study dot best underscore params. Next I'm going to say print the best accuracy based on those parameters. So we can compare study dot best underscore value. So there you go. That's all. Let's go ahead and clear this out and run it again. It's going to run through those 50 trials that I've specified. As you can see, numbers are increasing, and it's completed. Now it gave me the best hyperparameters for n estimators, 146, max depth 35, learning rate, this is the learning rate, subsample, call, gamma, alpha, lambda, and the best accuracy that comes is 9.964. And if you remember, the value that we got before was 0.9561, and now it's 9649. So you see, it kind of improved the accuracy after using this Bayesian optimization using Optuna library. Now next step is to compare this with grid search and random search. Is it any better? Sometimes it is, sometimes it's not. So I'm going to clear it out, and I am going to go ahead and here from model selection, I am going to get grid search CV to compare it with the grid search. So let's do the grid search first. I'm going to go ahead and define the parameter grid. To do that, I'm going to say param underscore grid. If you remember from what we've done before, we gave n estimators to be in between, let's say 100 200 and 300 is what I'm going to give, because I remember it was a little bit higher value that it likes. Max underscore depth is equal to, I'll give 3, 5, and 7. Next, for learning rate, I will give the values of 0.01, comma, I'll say 0.1 and 0.2. Pick which is the best one. And then I'll give subsample. In this particular case, I'll say 0.6, 0.8, and 1.0. So now once we have this, let's go ahead and train the XG boost with grid search. To do that, I'll say grid underscore search equal to grid, I'll call that function that we imported. Inside here, I'll say estimator equal to XGB classifier, and to this I'll say evaluate underscore metric equal to log loss. Next, I need to give the random state equal to 42. Now here we don't do the we don't give the parameters here, but in this it's a separate parameters grid equal to parameter grid. So it's a separate parameter that we give to this particular function. Next, I need to pass the scoring that I'm interested in is accuracy. I give the cross validation, which is this time let's reduce it to 3, and verbose equal to 1. So perfect. So I have all my data here for the grid. Now let's go ahead and run this, or fit the model grid search dot fit x underscore train. So train it with x train and y underscore train. So that's ready. Our grid search is ready. Now let's go ahead and look at best parameters and accuracy with this. And I'm going to say print grid search best parameters equal to grid search dot best parameters, and then for accuracy I'll say grid search best accuracy is grid search dot best score. Perfect. I'm going to give some slash and slash and slash in, so we see the difference between the two. And also, while we are at it, let's also implement the random search CV. It's almost same as this. So I'm going to define the parameter distribution for my parameter dist, and n estimators I'll give the values of 50, 100, 200, 300, and 400. For max depth, I'll give 3, 5, 7. Let's add one more to it, comma 9. Learning rate, I'll say 0.01. Let's add 0.05, 0.1, 0.2. Subsample, we have 0.6. Let's add 0.7, 0.8, 0.9. Why not? Right, and then let's also give call space call sample column sample underscore by tree. For this I'll use same numbers as this. There you go. So that's ready. Now let's go ahead and train the XG boost with this random search that we have imported. So to do that, I'm going to first start with random search parameter variable, and then say random search CV. The estimator that I want to use is XGB classifier, and I'll say eval underscore a metric equal to log loss, and then random search, or not search, random state equal to 42. Next parameter that we need is the distribution. So I'm going to say parameter distribution equal to param dist that we've created right above here. So that's what I've given there. Next, number of iterations that I want to run is, let's say, 50. Scoring equal to, I'll say, accuracy. Next, I need to give the CV, cross validation, give same number 3. Verbose equal to 1. Next, I want to say random state. Since it's a random search, I'll have to give a number 42. Random search dot fit, pass it x underscore train and y underscore train. Perfect. Now let's go ahead and print out the best parameters and accuracy for the random search. So I'm going to say print. Again, I'll give some space /n/n/n random search best parameters equal to random search dot best params. And then for the accuracy, random search best accuracy equal to random search dot best score. Perfect. So I have all the three ready right now. So let's go ahead and compare the results for all of them. Save it, go run here. And it's going to run, take some time, go through it. But I can see here the baseline is 0.9561. So I can take that and type it here. So this is my baseline XGBoost accuracy. Let's go all the way to the down. Now here, this is best accuracy with hyperparameters that we have given. 0.9649. Now where did we, oh, this is actually not, this is it best accuracy that we have printed? Yeah, here, study based on the boost on Optuna. That was the best accuracy. Now it's doing the grid search, and grid search best accuracy is this. So I'm going to go ahead and put it down here, 0.975. So with grid search, it's much better than the Optuna. So I'm going to say this is Optuna. And now it's doing the random search. So we'll probably be seeing the random search best accuracy next, which is this value 9758. 9758. So I think this is the winner here out of the 4 of them. So this is how you can kind of test different ones and use whichever is best. So first is default. This is as per Optuna, this is as per grid, and the final, the random search. So in our case, random search has the best accuracy, so we can use that model. But depending upon your data set that you have, you should use that that particular data set and check the accuracy and then use that model. Just to summarize, today we understood the importance of hyperparameter tuning in improving model performance. We gained practical experience with Bayesian optimization using Optuna, and we compared the traditional search methods, which are grid and random search, with Bayesian optimization. And we learned how to interpret and analyze the hyperparameter tuning results effectively to find out which is the best one to use for our use case. So if you have any problems or had any issues while implementing this or have any other questions, let me know in the messages and I'll get back to you. Day 4. Regularization techniques for model optimization. Let's start with understanding overfitting and underfitting. Even though we have done it so many times, let's dive deep into it. First, about overfitting. It occurs when a model learns the noise in the training data along with the patterns, leading to poor generalization on unseen data. Symptoms can be its high training accuracy but low test accuracy. It has large differences between training and validation losses. When does underfitting occur? It occurs when a model is too simple to capture the underlying patterns in the data. Symptoms can be low accuracy on both training and test sets. It's high bias in prediction. Let's talk about the regularization techniques. Regularization introduces a penalty term to the loss function during model training to prevent overfitting by discouraging overly complex models. We have the L1 regularization, also called as the lasso technique, which adds the absolute values of coefficients to the loss function. It encourages sparsity by setting some coefficients to 0, effectively selecting features. Next, we have L2 regularization, which is also called as the ridge technique, which adds the squared values of coefficient to the loss function. It shrinks coefficients towards 0 but does not set them to 0. And we have elastic net, which combines both L1 and L2 regularization. It's useful when there are correlated predictors and when feature selection is desired. Next, let's talk about the practical applications of regularization. First one is, of course, to prevent overfitting. It penalizes large coefficients, reducing model complexity. Another application is to handle multicollinearity, where ridge regularization is effective when predictors are highly correlated. Next application is feature selection. Lasso automatically performs feature selection by setting some coefficients to 0. Now, with this, let's jump into our hands-on exercise for today, where we will be applying lasso and ridge regularization on a linear regression model, compare the performance, and analyze the effects of coefficients. We'll be using the California housing dataset, which is built in. So let's go and get started with first step to load and explore the dataset. Create a new file, save it as day 4 underscore exercise. And here I'm going to say from sklearn dot datasets import I'll say fetch underscore California housing. Next I'm going to say sklearn dot model selection. I am going to import train test split. I think I might not need pandas or numpy, so let's go ahead and load the dataset. To load the dataset, I'm going to say California equal to fetch California housing. Next, I'm going to say X features and target equal to California dot data and California dot target. You can see I have not used data as I used to use before because I like the word California. Who doesn't? Next, I am going to say the feature names that we have here is California dot feature underscore names. Next, let's go ahead and split the data set. I can say X underscore train, X underscore test, Y underscore train, and Y underscore test equal to train test split X comma Y comma test size equal to 0.2 comma random state equal to 42. Probably I can sing a song with this now with the amount of times we have done this in the last 8 weeks. And next, let's go ahead and display data set info, where I will say print. First one is feature names. Now you see why I have created that feature names variable, because I can use it here. I can always have done that California.feature names, but sometimes it's better. /n, I'll say sample data /n, and I'm going to say PD. Okay, I do need pandas, so I'm going to say import pandas as PD, because I'm going to use the data frame X comma the columns that I'm interested is feature names dot head. Perfect. So this will show me some sample data. Let's go ahead and run it. I'm going to say Python day 4. Increase the size of this. And there you go. Feature names: medium income, house age, average rooms, average bedrooms, population, average occupation, latitude and longitude. and this is my sample data that I have from there. Next step is to train the linear regression model without regularization. So for that, first I will go ahead and from sklearn dot linear model import linear regression. Next, from sklearn dot metrics, I will import mean square error. So MSE is what we are using here. Next, I will go ahead and I mentioned train the linear regression model. For that, I need that model. I'll say linear regression model equal to linear regression. Next, I'm going to say lr dot model. Underscore model. I will fit and train it by x underscore train y underscore train. So I give the training data for it to train. Now let's go ahead and predict and evaluate. I'm going to say y underscore pred equal to lr dot model, lr underscore model dot predict x underscore test and mse underscore lr equal to mean square error y underscore test and y underscore pred. Let's go ahead and print these data sets. So I'm going to say first linear regression MSE with no regularization. Hope I spelled it wrong. All right, whatever, it doesn't matter. You got the point. MSE underscore LR. I'm going to say 0.2f. Display that. Next step, let's go ahead and print the coefficients. Now that is LR underscore model dot coefficients. Perfect. So I have that. Let's go ahead and test it out. I'm going to clear this out, run it again. Now my data linear regression model MSE is 0.56. Coefficients is, these are the coefficients that we have for this linear regression with no regularization. Next, let's go ahead and apply the ridge regularization. To do that, from my linear model, I will import ridge. So that's all that I need. And then I'll say train the ridge regression model. To do that, I'm going to say ridge underscore model equal to ridge. Now it needs a parameter of alpha, which I'll specify to 0.1. And then I'll say ridge model and then fit the data, which is x underscore train and y underscore train. Now let's go ahead and predict and evaluate. To do that, I'll say y underscore pred underscore ridge equal to ridge model dot predict and pass it x underscore test. Next, let's get the MSE for this ridge equal to mean square error, pass it y underscore test, and whatever we just got, y underscore pred of ridge. Now this will help us to first print the ridge regression MSE, which is MSE ridge and 0.2f. Perfect. The coefficients for this, let's print that also. I'm going to say coefficients, since it's in matrix /n ridge model dot coefficients. Now we can compare that. So we have too much data here. Let's clear it out and run it again. So this is our ridge regression. This is the linear regression MSE with no regularization 0.56. Even the ridge regression gave us 0.56, and the coefficients are displayed right over here. Next thing, let's go ahead and apply the lasso regression. Now lasso also I can get it from here, say lasso, and now I'm going to do the same thing. So I'm going to just copy it here. So I'll say lasso regression model. I will say this is lasso, and here I'm going to say lasso alpha equal to 0.1. Now lasso model fit x underscore train, y underscore train, perfect, print and evaluate. I'm going to say y predict lasso model predict x of test. MSE of lasso is mean square error, pass this, and lasso here, and this is lasso MSE underscore lasso and lasso model dot coefficients. So that's it. So let's go ahead and run this and compare all of them MSEs together and coefficients together. I'll go clear it out, run it. So there you go, 0.56, 0.56 with lasso regressions is 0.61. I can always try to see if there's any change by increasing this float value, and you'll see 0.5559, exact same, whereas this is 0.6135, but you'll see the coefficients over here. There might be some differences here and there between linear and ridge, because we are adding regularizations in both ridge and lasso. So I hope you were able to follow along and get this. If you had any issues in here, let me know and I'll get back to you. But what we did here was we got the outcomes based without regularization, with regularization, and with lasso regularization. And just to summarize, today we went and understood what overfitting and how regularization helps to mitigate it. We learned the differences between L1, lasso, L2, ridge, and elastic net regularization techniques. We gained hands-on experiencing applying the regularization techniques and comparing their effects. And finally, we developed the ability to choose appropriate regularization methods for different scenarios. So again, if you have any issues or questions, let me know. If you have any suggestions or recommendations or any questions in general, let me know in the messages and I'll get back to you. Day 5, cross-validation and model evaluation techniques. Today, we're going to look at or start with importance of cross-validation in model evaluation. So what is cross-validation? Cross-validation is a statistical method used to evaluate the performance of a model by partitioning the data into training and validation subsets multiple times. It helps ensure that the model's performance generalizes well to unseen data. Now, why use cross-validation? It prevents overfitting. By evaluating the model on multiple subsets, cross-validation provides a more robust measure of its performance. It's a reliable performance estimate. It reduces the variance of performance metrics compared to a single train test split, and it optimizes model selection, which helps in comparing and selecting the best model or hyperparameter configuration. Now let's talk about the types of cross-validation. We have k-fold cross-validation, which splits the dataset into k equal sized folds. Then it trains the model on k minus 1 folds and validates on the remaining fold. It repeats the process k times, ensuring each fold is used as a validation set once, and is best for general purpose datasets. Next, we have the stratified k-fold cross-validation, which ensures that each fold maintains the same class distribution as the original dataset. It's particularly useful for imbalanced datasets. It's best for classification tasks with imbalanced data. Now, we have leave one out cross validation, which is LOOCV, which uses a single data point as the validation set and the rest as the training set. It repeats the process for each data point. Pros, it maximizes the training data for each fold. And cons, as you can assume, it's computationally super expensive for large data sets. And it's best for small data sets where maximizing the training data is critical. Next, let's look at the practical guidance on cross validation. So for choose k based on a data set size, where k equal to 5 or k equal to 10 are commonly used for large data sets. You can use LOOCV for small data sets. Then you have stratification for imbalanced data. Always prefer stratified k-fold for imbalanced classification tasks to ensure the fair evaluation. And finally, combine with the hyperparameter tuning. Integrate cross-validation into grid or random search for robust hyperparameter tuning. With this in mind, let's jump into hands-on exercise where our objective is to evaluate a classification model using k-fold and stratified k-fold cross-validation and then compare the results to demonstrate the importance of stratification for imbalanced datasets. The dataset we'll be using here will be the credit card fraud detection dataset, which is available in the Google API's TensorFlow side as an imbalanced dataset. So let's go ahead and load and explore the dataset first. New file, Python file, save as day5_ex. Now here, first I'm going to say import pandas as PD. Next, I am going to go ahead and load the data set. First, I'll get the URL. It is https://storage.googleapis.com/download.tensorflow.org/data/creditcard.csv. You can download it from there or view it on your browser. Let's say df equal to pd.read the CSV file from the URL above. So now once we have that, I'm going to go ahead and display the dataset info. Let's say print dataset info and then print df.info so we can look at the information of why it's imbalanced. That actually can be found from here, which is the class distribution. So we can see how the distribution is between majority versus minority. So I'm going to say print df class dot value. The column name is also called class, so it's a little bit confusing here, but that's the fraud or non-fraud column. So I'll go to my terminal and say Python, my name of the project, day5. It's going to first download it. It has a lot of data, so it takes a little while. So I'll pause it here and come back. And there you go. Once it's downloaded, we have the class distribution here where you can see that non-fraud transactions is 284,315, whereas fraud transactions are 492. So you see, it's a highly imbalanced data set that we have. I'm going to clear it out, go back, and next, first step is to prepare the data. So I am going to go ahead and from sklearn.model selection, I will import train test split, go here and say define the features and target. Now to get the features, I am going to say df.drop columns equal to, I need to just drop one column, which is my target column. I'll say class, and next for my target, I just need to pick one, which is my class. So perfect, that we have it. Next, let's go ahead and split the data set. To split it, I'm going to say x_train, comma x_test, y_train, y_test equal to train test split, and to it I'll pass x, y, test size equal to 0.2, and my random state equal to 42. Save it. Done. Our next step is to implement the k-fold validation, cross validation here. So I'm going to go here and first from sklearn.ensemble, I need the random forest classifier. So I'm going to say import random forest classifier. Next, we need the cross validation score and k-fold that is available in sklearn.model selection. I think I already have model selection. So I can just say here cross val score, and I need k-fold. So get from there. Perfect. Next, let's go ahead and initialize k-fold first. For a k-fold, I'll say kf equal to k-fold, and I'll say number of splits that I want for this is 5. I want to shuffle the data, so I'm going to say shuffle equal to true, and then random state equal to 42. So that initializes your k-fold. Next, let's go ahead and train and evaluate the model using the random forest classifier. So I'm going to say rf underscore model equal to random forest classifier, random state equal to 42. Next, I'm going to say scores underscore k-fold equal to cross val score. So cross validation score function, I'll pass it rf model. We'll have to pass the model, we have to pass the training data set, we have to pass the y training data, x train, y train, and cv equal to, I'll pass a cross validation is k-fold, so I'm going to give kf here, and scoring equal to, I need accuracy for that, so that's why I specify accuracy. Once I'm done with this, let's go ahead and print and see our results. F k dash fold cross validation scores equal to our scores underscore k fold, that's where we can print it from, and then print f mean accuracy for k dash fold is, I can say scores k fold dot mean colon 0.2f. Don't want to see the extra decimals. And next step that we have to do, so this will print those out, but our next step that I want to do is I want to implement the stratified k-fold cross validation and then compare both of them together. So for that, from model selection, I will also call for stratified k-fold. Now I'm going to go here, first initialize the stratified k-fold. I will say skf equal to stratified k-fold, and to this I'm going to use the same number of splits as 5. I say shuffle equal to true and random state equal to 42. So everything, all the parameters are exactly same. Now let's go ahead and train and evaluate the model. For that, I'll say scores underscore stratified equal to cross validation score, pass it the model, rf model, I'll pass it x underscore train, I'll pass it y underscore train, I will pass the cross validation is skf that we've created above, and scoring equal to accuracy. So exactly same, but the CV is different here. Now let's go ahead and print the same thing, where instead of this, I'm going to say stratified k-fold validation scores, and this one is not k-fold but stratified, and then I can say mean of stratified k-fold, and here I can say stratified and get the mean. Now that I have everything together, I can go ahead and compare these values. So I'm going to go back here and run it. So it took a little bit time, and finally we have our results here. We have the information about the data set, the class distribution as I mentioned, and here is our data after using the k-fold cross validation scores, which provides accuracy scores across folds but may suffer from inconsistent class distribution from imbalanced data sets. It has a pretty good accuracy, as you can see, 0.93962, but as compared to stratified, it has 0.99967. So it's a little better when you use the stratified k-fold cross validation scores as compared to k-fold, especially for a imbalanced data set. And it maintains, the reason is why stratified k-fold cross-validation maintains class distribution across folds, leading to more reliable and consistent performance metrics. To summarize, today we went and understood the importance of cross validation for evaluating machine learning models. We looked at the differentiation between k fold, stratified k fold, and leave one out cross validation. We gained some practical experience in implementing the k fold and stratified k fold cross validation, and we learned how to choose the appropriate cross validation method for different datasets and tasks. So, if you have any questions or had any issues implementing this, let me know and I'll get back to you. Day 6, Automated Hyperparameter Tuning with Grid Search CV and Randomized Search CV. Here we're going to start with using Grid Search CV and Randomized Search CV from Scikit-learn. So what is Grid Search CV? Grid Search CV performs an exhaustive search over a specified parameter grid. It trains and evaluates a model for every combination of hyperparameters in the grid using cross-validation. Next, what is randomized search CV? Randomized search CV selects a fixed number of random combinations from a parameter distribution. It is faster than grid search CV for a large hyperparameter spaces while still providing a good results. Let's talk about the key features. For first, I want to talk about automates the hyperparameter tuning. It combines model training, evaluation, and hyperparameter search into a single step. Another feature is cross-validation integration. It ensures robust performance metrics by using cross-validation. And it also does result interpretation. Provides the best hyperparameter combination and associated metrics. Let's talk about how to integrate cross-validation with hyperparameter tuning. First, cross-validation, it ensures that the hyperparameters selected generalize well to unseen data. The benefits of this is it reduces overfitting to the training dataset and it provides robust estimates of model performance. Next, let's talk about interpreting results and selecting the best model. So best parameters is access the optimal hyperparameter combination using dot best params underscore attribute. Next, you have the best estimator. You can retrieve the model trained with the best hyperparameter using the dot best underscore estimator underscore. And you can get the performance metrics. You can use the dot best score underscore to evaluate the performance of the best hyperparameters. Let's use all this inside our hands-on exercise where the objective is to use grid search CV and randomized search CV to tune hyperparameters of gradient boosting and support vector machine models and compare the results. For the dataset, we'll be using the iris dataset, a multi-class classification problem. And to start with, let's create a new file. I'm going to call it day6 underscore ex. And inside here, our first step is to load and prepare the dataset. So for that, let's get the dataset sklearn.datasets import load iris. You can use your own dataset if you want to, but all you have to do is change these things. sklearn.model selection, and I will import from there train test split. So let's first load the dataset. To load the dataset, I'm going to say data equal to load iris. Next, I'll say x, the features, and the target y equal to data dot data. So that will assign my x, and for my targets, I say data dot target, which will be assigned to y. Now let's go ahead and split the data set. To do that, I'm gonna need x train, x test, y train, and y test. Now this can be fetched from train test split, which will split x, y, test size of 0.2 and random state equal to 42. There you go. Next, let's go ahead and print data set loaded and split successfully. I am just going to print that for now. I'm not going to display anything, but you have now loaded and prepared the dataset. Now, next step, which is part one of the entire thing, is to do the grid search CV with gradient boosting. So first, for that, let's go ahead and from sklearn.ensemble, I will import gradient boosting classifier, and from the model selection I will get the grid search CV. I can also get the randomized search CV already, since it's in the same class. So next I will go ahead and define my parameter grid. The parameter grid will be called parameter underscore grid equal to, inside this, let's start with n underscore estimators, which I'll give the values of 50, 100 and 150. Next I need the learning rate. Let's say learning underscore rate. For that I'll say 0 0.01, 0 0.1, 0 0.2. Next I need the max depth of the trees, max underscore depth. For that I'll say 3, 5, 7. Perfect. I have that. Next thing is, now let's go ahead and initialize the grid. Initialize the grid search. So for that, before even initializing grid search, let's initialize the grid search CV. So for that, I'll say grid underscore search equal to grid search CV. To that, I'll give the estimator that I'm going to use, and for that I have gradient boosting classifier, random state equal to 42. Next, I'll give the parameter grid for it, which is parameter grid. Next, I'll give the scoring, which I want to do with accuracy. Next, I want to say cross validation equal to 5, and number of processors is use all the processors that are available by setting -1. Now let's go ahead and perform the grid search. So I can do the grid search by fitting x underscore train and y underscore train. So this will perform my grid search. Next, I'm going to say get the best parameters and score. So for that, I'll say best underscore params underscore grid equal to grid search dot best parameters. Next, I want to get the best score underscore grid, that will be grid search dot best score. If I want, I can print them out. Best parameters for grid search CV are best parameters grid. Next, I'm going to say print f best cross validation accuracy for grid search CV is best underscore score grid, and I can say 0.4 f. So that's our first part. Next, let's go and evaluate the best model on the test data. So I am going to, from metrics, do I have metrics? No. From sklearn dot metrics, I will import accuracy score and classification report. So now let's get the best model. Get the best model. To do that, I can say best grid underscore model equal to grid search dot best estimator. Next, I'll say predict and evaluate based on that model. I can say y underscore pred underscore grid equal to best underscore grade underscore model. I want to predict and I pass the data set x underscore test, and I'll get the accuracy of this grid by calling the accuracy score y underscore test and use that y pred that we just got from the grid. Now let's say print test accuracy for grid search CV is accuracy grid 0.4f, and I'll print /n the classification report /n is my classification report, and to it I'll pass y underscore test and y underscore pred grid. Perfect. So I have everything available here. Now the second part of it, which is the randomized search CV with support vector machine. To do that, I am going to first go ahead and from sklearn I.svm, because we want the support vector machine that I can import from here as svc. Next, I want from model selection, I've already done randomized search CV. I also might need numpy for some operations. I'm going to say numpy as np. Okay, so now I'm going to go ahead and first define the parameter distributions. Now, why do we have numpy is the question that you're asking. Now, this is, I want to create a parameter distribution here with our first element, which is c, as np dot log space, and then here this is the reason why I'm using numpy from -3 to 3, and I need 10 elements, so that's what I have. Next I need is the kernel. For the kernel, I am going to say either use linear or you use RBF, or we can use polynomial, or you can use sigmoid. So use one of these as kernel. And then for gamma, I want to use either scale or we can do auto. So these are my parameters for distribution. Now let's go ahead and initialize the randomized search CV. To do that, I'm going to say random underscore search equal to randomized search CV, and to that I'll pass the estimator. In this case I have the SVC, that's what I want to use. Random state equal to 42. I'm going to say parameter distributions equal to whatever I created above, parameter distributions. Next, I want to say how many iterations I want to run. Let's run 20. I think it might be too much. This is number of parameter combinations to try, but why not? Scoring equal to accuracy, cross validation equal to 5. Number of jobs or number of processes that I want to use is -1, which means all of them. Random underscore state equal to 42. Perfect. So I have this. Next step is to perform randomized search, which is to train the model. So I'm going to say random search dot fit, pass x underscore train and y underscore train. So this will give us the best parameter. So let's go ahead and get the best parameters and score from this. To do that, I'm going to say best parameters. We did grid before. I'm going to do now random equal to random search dot best parameters. Next, I need the best underscore score, not grid but random search dot best score. Perfect. So I have both of them. Now let's go ahead and print first best parameters for randomized search CV, which is best underscore params underscore random. Perfect. Next I'll go say print best cross validation accuracy for randomized search CV is best score random 0.4f. Is it same as what we did before for this? Yes, 0.4f, 0.4f. Okay, perfect. So I've done that. Now we can go ahead and evaluate the best model on the test data that we have. To do that, I'm going to first say get the best model. I'm going to say best random underscore model equal to random search dot best estimator. So this will give me the best model that is trained with the data that we have. Next, let's go ahead and say predict and evaluate. I'm going to say y underscore pred underscore random equal to best best random model dot predict. Make sure you don't select the wrong one, or else you'll have the same answer. X test accuracy underscore random is accuracy score y underscore test and whatever y underscore pred random that I just got. Perfect. Now let's go ahead and print f test accuracy for randomized search CV is accuracy random 0.4f. Perfect. Last /n classification report /n is classification report. Use the y test and y pred random. Perfect. Now we can go ahead and compare all these items together and see which one is the best. So now go ahead, save it and say python day6.ex. It's going to say data set loaded and split here, which was our first output right over here. Lots of lines of code here. Line number 16. Next, it's going to give me the best parameters for grid CV, which was printed right here. And it said learning rate is 0.1 based on the data that is set. Max depth 3 and estimators 50. Best cross validation score is 0.95 here, 0.9583 for the randomized search CV. So you see the difference right away, 95 versus 9583. So in this case, the best one that we can use is here. But if you look at the accuracy here, is 0.9667, whereas the test accuracy with grid search CV is 1. So again, depending on which data set you're providing, what you're giving it, grid search CV provides high accuracy by evaluating all the hyperparameter combinations, but is slower for larger parameter grids, whereas randomized search CV achieves comparable accuracy with fewer evaluations, offering faster results for large hyperparameter spaces. So they both have their pros and cons, but depending on what you want to use, you can use either or. And I hope you are able to follow along and get this output. If not, let me know and I'll get back to you. So just to summarize, today we learned how to use grid search CV and randomized search CV for automated hyperparameter tuning. We understood how cross-validation integrates with hyperparameter search for robust evaluation. We developed the ability to interpret the results, select the best model, and compare the tuning strategies. And we finally gained hands-on experience tuning both gradient boosting and support vector machine models. So if you had any issues while implementing this or have any questions, let me know and I'll get back to you. Welcome to our day 7, the last day of this particular week. So today we are going to look at our optimization project where we'll be building and tuning a final model. So first, let's start with applying all the learned tuning and optimization techniques. So let's look at the comprehensive list of model optimization. We have data preprocessing, where we ensure data is clean, scaled, and encoded appropriately. Then we do feature engineering, which is derive new features and select the most important ones. Then we follow regularization, where we avoid overfitting by penalizing complex models. Next, we jump into the cross validation, where we use techniques like K-fold or stratified K-fold for robust performance metrics. And finally, we look into hyperparameter tuning. We use methods like grid search CV, randomized search CV, or even Bayesian optimization for this. Next, let's look at evaluating and interpreting the model performance. For performance metrics, we use for classification, we use accuracy, precision, recall, F1 score, and ROC AUC. For regression, we use mean square error, MSE, or mean absolute error, MAE, or R square. And importance of interpretability, we use feature importance and coefficient analysis for transparency. So I hope you were able to follow along this entire week and understand all these different concepts. So now with that, let's jump into our hands-on project where the objective is to build, tune, optimize a machine learning model using a structured process and evaluates its performance comprehensively. The dataset we'll be using will be the customer churn dataset that we have used before, a classification problem to predict whether customers will churn. So I already have that available in my folder. It's called Telco Customer Churn. This is the dataset. It has all the different fields about the customer, and at the end, will the customer churn, yes or no? That's what we are trying to predict with our dataset or train the model on that. So first step again is to load and explore the dataset. Now start a new file, save it as day 7 underscore exercise. And here, first, let's start with import pandas as PD. Then I'll load the data set. For that, I'll say data frame equal to PD dot read CSV, and I'll give the name right here. Then let's go ahead and display the data set info. For that, first I'll say print dataset info /n. Make it look pretty. Print df.info, display the info. Next, I'm going to say I want to see the class distribution /n class distribution /n, and I'll say print df of churn, as we saw, that's the last column, dot value counts. So that will give me the class distribution of how many will churn and how many will not, and see if it's a unbalanced data set. /n sample data. Let's also see some sample data for this, and I'll say for that I want to see df dot head. Perfect. Let's go ahead and run this. There you go. Make sure that we have proper alignment, because Python doesn't like if you don't align your code properly. Let's say Python day 7 underscore exercise, run it, and here's our data set with all the different columns. Churn is what we are interested in, and if you see the class distribution, no is 5174, yes is 1869. It's unbalanced, but not that much, but it is unbalanced data set where this is 3 times more than this value here. And we have our sample data, which displays customer ID, gender, senior citizen, dot dot dot, monthly charges, total charges, and churn. So we have 21 columns and 5 rows to be displayed right here. Next step is to pre-process the data. We will handle the missing values and encode categorical. So in this particular case, I don't see any missing value, but if you are using a data set that has missing values, so you'll have to do that. And we also do encode the categorical variables. And finally, we'll scale the numerical features. So let's go ahead and right here, I'm going to say from sklearn dot pre-processing, I will import label encoder and I will import standard scalar. Once I have that, I am going to handle the first is missing values. Now to handle the missing values, I am going to, let's pick a couple of columns. I'm going to pick total charges. Let's go here, total charges. And to this, I will say pd dot to numeric and df of total charges, comma, I'll pass errors equal to course. Okay, so there you go. So that will take care of the errors. And next I'm going to say df of total charges dot fill. Okay, so this is changed. I always use the older method. I'm going to say fill na, and to this I'll first have to select the column which is total charges. The value that I want to assign to this is df of total charges dot median, and then I'll say in place equal to true. So there you go. So we have assigned, we filled the if there's any data that is missing, it will be filled. And then I'll say encode the categorical variables. To do that, I will say label underscore encoder. I'll create a label encoder, and that is label encoder that we have imported. And then I'll say for column in df dot select for column in df dot select underscore d types, I will say include equal to, if it's object, which means it's categorical, dot columns. Then I will check if the column is not equal to, I'm not interested in churn, so that I will ignore here. I'll say df of column equal to label encoder dot fit transform df of column. There you go. That'll take care of all of them. So this will encode the categorical parameters variables. Now next I'm going to go ahead and encode the target variable. So df of churn, I will say label encoder dot fit transform, and this one I'll say df of churn. There you go. So that will take care of churn, my target variable. Now let's go ahead and scale the numerical features. So they are uniform. So for that I'll say scalar equal to standard scalar. Standard scalar, and I will say next is numerical underscore features that I'm interested in is, let's pick some. So from here I'm gonna pick tenure, I'm gonna pick the monthly charges, which is float, and I'm gonna, since I have total charges, I have changed it, so I'm gonna use total charges here. That will complete converted to numeric. df of now numerical features equal to scalar dot fit underscore transform df of numerical features. So this should scale all the numerical features. Now let's go ahead and get my features and target that I can say by saying x equal to df dot drop. I want the entire set except I am not interested in churn. So that's what I'll specify here, and y equal to, I'll say that I am interested in churn alone. Perfect. So this takes care of pre-processing the data. Next thing we'll do is train, test, split, and initialize the model evaluation. So that's our next step. So for that, I'm going to go here. I don't have model selection. sklearn dot model selection. I will import from there our favorite one, which is train, test, split. Next, from sklearn dot ensemble, I will import the random forest classifier, and for metrics sklearn dot metrics, I will import accuracy score classification report. Next, let's go ahead and split this data set. So I'm going to go here and say split data set, and for that I'll need xtrain, xtest, ytrain, and ytest as my variables, which will be filled by trend test split x comma y comma test size equal to 0.2 comma random state equal to 42. Let's look at it. Perfect. Next, I am going to go ahead and train the initial model. To do that, I'll say rf underscore model equal to random forest classifier random state equal to 42. I'll say rf underscore model dot fit x underscore train and y underscore train. Now once I have trained that, I'm going to go ahead and evaluate initial model, where we'll add y underscore pred equal to rf underscore model dot predict, and then here I'll pass x underscore test to this and get my accuracy for the initial model, which I'll say accuracy score, and to it, did I spell? Yes. I'll give y underscore test and y underscore pred. Perfect. So I have evaluated, or I got all the data. So now let's go ahead and print stuff out. I'll say initial model accuracy is accuracy initial 0.4 f. Next, I'll say print /n classification report /n. In this particular case, I'll call the classification report function and pass y test and y underscore pred that we just got. Perfect. So that should take care of that. Now that we have trained, test, and split, and also initial model evaluation, let's go ahead and do the hyperparameter tuning with the randomized search CV. So for that, from my model selection, I would need randomized search CV. I also need, for creating random values, numpy as np. Now I'm going to go ahead, as you remember, first thing is to define the parameter grid. My parameters with distributed parameters equal to, I'm going to say first I need n estimators. np dot range, to it pass 50, 200, and 50 to 210 of these. Next, I'm going to say my max underscore depth is either none, or use 5, or use 10, or use 15. Next, I'm gonna set the minimum samples split, that can be 2, 5, 10, 20. Next, I will use my minimum underscore samples underscore leaf 1, 2, and 4. Perfect. So I have my parameter grid. Now next I'm going to go ahead and initialize my randomized search CV. To do that, I'm going to say random underscore search, create a variable, and say randomized search CV. To this, I need a lot of different parameters that it needs. One is estimator, is we said that we'll use the random forest classifier. Use that. Random state equal to 42. Next, I need the parameters distributions, which is I've just created just now. So I'm going to use that, which is created right here. That's what I'm using here. Next, number of iterations that I want to run. I want to run 20 iterations. This is the number of parameter combinations to try. That is CV equal to 5 or cross validation. I will say scoring equal to accuracy, and I'll say jobs, which is processors. Now you can always, when I'm typing here, it shows me what they are, gives me descriptions, what are the different values that are there. So n of jobs, as I said, is the number of processors that I'm using, which will kind of be specified. When I select this, it should show, but I'm setting -1, which means all the processor, and random state equal to, so it talks about what random state is, how to use it. It has all the different documentation right over there, equal to 42. So that's my initialization of random search CV. Next, I am going to go ahead and perform my randomized search. To do that, I'll say random search dot fit, easy enough, x underscore train and y underscore train. So this will run that. It will take some time, and then finally get the best parameters from the list that we have created. I'm going to say best underscore params equal to random search dot best params. Then I'm going to say print f of best parameters on randomized search CV is the best parameter that I just got above. Perfect. So I'm going to print that out. Now, our next step is to evaluate the tuned model. So for that, let's train the best model available, which is the best model. Let's pick it up. Random search dot best, out of all the estimators that you have, give me the best estimator. Now I'm going to say predict and evaluate that. To do that, I'm going to say y underscore pred underscore tuned equal to best model that we just got. From that, predict the values from xtest. Now let's check the accuracy. I'm going to say accuracy tuned equal to accuracy score y underscore test and y underscore pred tuned. Now based on that, now let's go ahead and say f of tuned model accuracy is accuracy tuned 0.4f. Next, let's get the classification report. /n classification report for the tuned model is /n comma classification report. Now you know what it needs, y underscore test and y underscore pred tuned. So this will give me the classification report. And now just one more step, to use the cross validation for final performance metrics. So from model selection itself, I am going to pick cross val score, and here just 2 more lines of code, I promise. So I evaluate the also not counting comments as code, using cross validation, and here I am going to say CV underscore scores equal to cross val scores. I'm going to use my best model that I got, pass it x, y, cross validation is 5, and scoring is accuracy. Now let's print it out. That's all. I'll say cross validation accuracy scores is CV underscore scores, and then I'll print my, I know I said 2 lines of code, but this is just print statement. Come on. Validation accuracy equal to CV underscore scores dot mean, and I'll say 0.4f, hopefully be 1.0. So let's go ahead, and from all the code that we have written, let's go ahead and see the output clear. So there we go. We have initially the information, the class distribution, the sample data, and then our initial model. Where'd you go? Initial model accuracy is 0.79. It's pretty low, but if you look at the classification report, it's kind of between 0.49 to 0.1, so it's kind of distributed. Now, best parameters are, if you use an estimator 60, minimum split of 20, minimum sample split, minimum sample leaf of 4, max depth 15. Our tuned model accuracy goes from 0.7977 to 0.8084. Next, we have our classification report for that. And if you look at the cross validation accuracy scores, I have 0.80, 0.80, and the mean cross validation accuracy is 0.7997. And these are the different values. If you look at them, they're pretty good. So that's how you can first create initial model with baseline accuracy and performance metrics. Then we tuned the model and improved the accuracy and classification metrics and hyper training parameters. And cross validation helped us with a robust performance metrics to validate generalization. I hope you were able to follow along, and let me know how it goes. So just to summarize, today we applied end-to-end optimization techniques, including pre-processing, feature engineering, and hyperparameter tuning. We used randomized search CV to find the optimal hyperparameters efficiently. Then we evaluated model performance using cross-validation for robust metrics. And finally, we developed a high-performing machine learning model suitable for production. Let me know how it went. If you have any questions about this, or if you had any issues while implementing this, let me know in my messages and I'll get back to you. Welcome to week 9, Neural Networks and Deep Learning Fundamentals. This week, day 1 will cover introduction to deep learning and neural networks. Day 2 will be looking at forward propagation and activation functions. Day 3, we will cover loss functions and back propagation. Day 4 will cover gradient descent and optimization techniques. And on day 5, we'll go over building neural networks with TensorFlow and Keras. Followed by day 6, where we'll be looking at building neural networks with PyTorch. We'll be looking at our neural network project, which will be image classification on Cypher 10. So let's get started with week 9. Welcome to the week 9, and today on day 1, we're going to look at introduction to deep learning and neural networks. Let's start with what is deep learning, and let's look at some of the differences between machine learning and deep learning. So first, what is deep learning? Deep learning is a subset of machine learning that uses artificial neural networks, or ANNs, with multiple layers, which deep architectures, to model and learn complex patterns in the data. Some of the key features include it automatically extracts relevant features from data, eliminating need for manual feature engineering. So whatever we did before, we don't need it. It's automatically done for you. So why did we do it? Just to understand the basics of it. Let's look at machine learning versus deep learning. So for example, we can compare features and see how it applies in machine learning and deep learning. So for example, feature engineering in machine learning is manual feature selection, whereas in deep learning, it's automatic feature extraction. For as compared to algorithms, machine learning has linear regression, SVMs, etc., whereas in deep learning, we have neural networks. For data independency feature, machine learning works well with small data sets, whereas deep learning requires large data sets. And for computation, it's computationally less intensive in machine learning, whereas in deep learning, it requires GPUs and TPUs for training. So some of the exercises that we will be doing might take much longer than usual to run if you are running on a simple machine. But if you have access to some of the GPU, TPUs machines online, cloud, you can probably run much faster. So let's go ahead and look at the overview of artificial neural networks or ANNs. The structure of a neural network has three layers. First is the input layer, which accepts input data features. And then we have hidden layers, which performs computations to extract patterns. And then on the top, we have output layer, which produces predictions or classifications. Some of the key components include we have neurons, which are the basic units of computation that take input, apply weights and biases, and produce outputs using an activation function. Then we have the weights and biases. Weights determine the importance of each input, whereas bias shifts the output of the activation function. And finally, what is activation function? It adds non-linearity to the model. Example, we have ReLU, sigmoid, tanh, and we're going to talk about these in future. Now, how neural networks work. So first, we have the forward propagation, where data flows through the network to generate predictions. Then we have loss calculation, where it compares predictions with actual labels to compute the error. And then finally, it does back propagation, where it adjusts weights and biases using gradient descent to minimize the loss. Let's look at some of the applications of deep learning. We're going to look at different domains and their use cases. First, in the computer vision domain, we have image classification, which is recognizing objects in images. Next, we have object detection. Example can be the autonomous vehicles. Next domain is natural language processing or NLP. There, we have text generation, example GPT models. You have used ChatGPT and others. We have sentiment analysis, which kind of tells if a particular text is positive, negative, or neutral. In the healthcare field, we have disease diagnosis. Example can be identifying tumors in X rays. And another is drug discovery. Next, we have speech processing. In there, we have speech to text systems. Examples can be virtual assistants. And we have voice recognition. So based on all these, let's jump into hands-on exercise where we will familiarize ourselves with common data sets in deep learning and set up an environment to work with TensorFlow and or PyTorch. We're going to use both. So I'm going to first show TensorFlow and then we're going to jump into PyTorch. So first step is to explore common data sets. We have MNIST, which is handwritten digit data set, 28 by 28 grayscale images and 10 different classes. We have Cypher 10, which is 60,000 32 by 32 color images across 10 different classes. And we have ImageNet, which is a large data set for image classification with millions of labeled images. So we're starting pretty heavy on day one. So try to follow along with whatever I'm doing and pause wherever needed. So let's go ahead and start. I'm going to start a new file, Python, and save it in my day one underscore exercise. So let's start with getting some data from TensorFlow. So from TensorFlow dot keras dot datasets, import MNIST and Cypher 10. These are the two libraries that we're going to import. Now let's go ahead and load MNIST first. Now to load this, I am going to use our same type of method. Just follow along and we're going to explain later in more detail. Xtrain underscore MNIST, Y train underscore MNIST. So this is one tuple. And then I have another tuple where I have X test underscore MNIST and Y underscore test underscore MNIST equal to MNIST dot load underscore data. This is a function that is available inside MNIST where we can load the data and to training and testing modules. So now that we have it, let's look at how the data looks like. So I'm going to say f of MNIST data set train equal to x underscore train MNIST dot shape. So checking how big, how many rows, how many columns it has. And for test, let's see, x underscore test MNIST dot shape. I'll go a little slow just so that you can catch up with, because all these are new functions that we have. Now similarly for loading cipher 10, I'm going to say x underscore train underscore cipher, comma y underscore train underscore cipher, comma x underscore test underscore cipher and y underscore test underscore cipher. Now this again from my cipher library, I can just say load underscore data. Now we have this. I am going to go ahead and cipher dash 10 data set, I'll say train data set equal to x underscore train cipher dot shape, and for test I have x underscore test underscore cipher dot shape. So I hope you got this. So again, for TensorFlow, you might have to open your terminal and install pip install TensorFlow. It might take some time. I already have it available, so that's why it went very quickly, but try to install it before you run it, or if you see any other issues, just install those libraries and it will be available for you. Now let's go ahead and run this. So I have this day underscore ex. So I think I forgot to put day 1, but I'm going to go ahead and say python day exercise.py. It's going to take some time because the data sets are really big, and as you can see, MNIST data set for training modules, we have 60,000 rows and 10,000 rows for this. Again, for Cypher, we have 50,000. So these are the images, actually, if you think about it. 60,000 20 by 28 by 28 images, 10,000 28 by 28 images, 50,000 32 by 32 by 3, and then 10,000 32 by 32 by 3. As I mentioned, these are MNIST are handwritten digit data sets, which are 28 by 28 grayscale images with 10 classes, whereas Cypher 10 is total 60,000 images with 32 by 32 color images. That's why 50,000 10,000, whereas this is 70,000 images. So I hope you got this working. Our second step is to set up a deep learning environment. So again, make sure that you run this pip install TensorFlow or it will not work for you. Now next step is I'm going to go here and, or let's go up here. I'm going to say import TensorFlow as TF, and next I am going to define a basic dense layer. So a layer is defined something like this. We can say TF dot keras dot layers dot dense, and then I can say units equal to 10 and activation equal to ReLU. So I have that. Next I'm going to go print, say f tensor flow layer, I'll say layer. So that's it. So let's save this, and next I am going to run this quickly so we see this layer. I'm going to go ahead and say python day and exercise, and it will give me again the data sets, and it will say TensorFlow layer dense layer built equal to false. So I have that layer displayed here. Perfect. Our next option is, what if I want to use PyTorch? In that case, I am going to go ahead and say pip install torch, that's what is used for PyTorch, and I need torch vision, which has all the libraries that we need to use. So it will take some time, but for me it's faster because I've already installed. And then I am going to go ahead and import torch here, that is PyTorch, and next I need some libraries from there. So I'm going to say import from torch dot I'm going to use NN, torch NN module, which has all the layers and information on that, so I can create a layer using that. So for that I am going to say define a basic dense layer in PyTorch. To do that I'm going to say layer equal to NN dot linear in feature equal to in features equal to 10 and out features equal to 5. Perfect. And then I can go ahead and print f of PyTorch layer is layer. So this will show me the PyTorch layer. Let's go ahead and run it, and oops, not this. Go ahead and run my Python, and your output should look exactly same as mine, which shows the data sets, TensorFlow layer and PyTorch layer. So once you have this, let's go ahead and visualize the data set samples here. So that's the last step. So I'm going to go ahead. First, I'm going to import matplotlib.pyplot as plt for visualization. Now I want to first visualize my MNIST sample. So for that I'm going to say plot.im show, and inside this I'll pass x train, and I'll use my MNIST data set at index 0, and I'm going to say cmap equal to, let's use grayscale for this, and then I'll give a title to this. Title I'll say f MNIST label with y underscore train underscore MNIST of element 0. That's what I'm displaying. Next let's say plt dot show. So of that I can do the same thing for let's visualize cipher dot 10 sample plt dot im show x underscore train, and I'll use cipher at index 0, and plot dot title is my data that it is, which is cipher dash 10 label is y underscore train underscore cipher of 0. So what I'm pretty much doing is, like, that index 0 of train, we have the actual images, whereas in y train it tells me which image it is. So that's what I'm doing in both the cases. You'll see what I mean by when I run it. So I hope you were able to get all these things running, and you should be at the point where I am, where it will show you the MNIST dataset, Cypher dataset, show you the TensorFlow layer, show you that you could build a PyTorch layer, and then here is my dataset. It picked a number, so as I mentioned, it's handwritten numbers. For in this case, it's number 5. I can see it, and from the label I can say that it is right. And for my PyTorch, it shows a label here, and it looks like it's a number 6 here. It says label is 6. That's what it's labeled as. So that's the Cypher 10 dataset. So I hope you were able to get all these things out here. If not, this is where you probably contact me or look up what's going on. If you have any issues or it shows up any errors here, let me know and I can get back to you quickly. So this will help you build your setup for the rest of the videos that we'll be looking at this week. So just to summarize today, we understood some of the core differences between machine learning and deep learning, and how deep learning belongs to machine learning. We learned the structure and components of artificial neural networks, or ANNs. We gained insight into the wide-ranging applications of deep learning across different domains, and we developed some foundational skills to explore datasets and set up a deep learning environment. I hope you were able to follow along, and if you have any issues or have any questions, let me know in my messages and I'll get back to you. Day 2. Today, we'll dive into one of the topics that we learned yesterday, which is forward propagation and activation functions. So, first, let's deep dive into understanding forward propagation. So, what is forward propagation? Forward propagation is the process by which input data flows through the layers of a neural network to produce an output. It has input layer, which accepts input features and passes them to the next layer. Next, we have the hidden layers, which compute weighted sums of inputs, applies biases, and passes the result through activation functions. Then we have the output layer, which produces predictions typically using an activation function suitable for the task. So let's look at steps in forward propagation. First, you compute the weighted sum. The formula for that is z equal to w times x plus b, where w is weights, x are the inputs, and b is the bias. Then you apply activation function, which is a equal to sigma of z, where sigma is the activation function. Then you repeat this for each layer. Outputs of one layer becomes inputs to the next. It's pretty straightforward, right? Again, you don't have to worry about it because there's functions available that will do this for you. You just have to understand the basics. Next, let's talk about some common activation functions. For activation functions, we have the sigmoid. The use case for this is binary classification in the output layer. Its ranges is from 0 to 1, and limitation, it can suffer from vanishing gradients for large positive/negative z's. Next, we have the tan h, which is also called as hyperbolic tangent. The range for this is from -1 to 1, and the use case is its hidden layers where zero centered outputs are preferred. The limitations for this are also prone to vanishing gradients, just like sigmoid. Then we have ReLU, which is rectified linear unit. It ranges from 0 to infinity, and the use cases are mostly commonly used in hidden layers due to simplicity and efficiency. The limitation of this is can suffer from the dying ReLU problem, which neurons are stuck at 0. Then we have softmax. Softmax produces probabilities summing to 1, and the use case for this, it's a multi-class classification in the output layer. Now, how do you choose which activation function do you want? So for depending on the layer, so example, if you're using in layer type hidden layers, then ReLU or tanh is the recommendation activation function. In output, for binary data, you use sigmoid. For output in multi-class, use softmax. And output where regression is applied, you use none or linear. So let's jump into an hands-on exercise where we will be implementing forward propagation for a simple neural network in Python and experiment with different activation functions. So let's go ahead and open a new file. I'm going to say day 2 underscore exercise. Now here, first, let's go ahead and import our favorite library numpy as np. Next, let's define activation functions here. So let's see how do we build these activation functions or the definition. So definition for sigmoid, which takes an input of z, is, I'll just return directly, 1 divided by 1 plus exponential value of minus z. So that's how you define a sigmoid function. So just it's always going to be the same. This is the actual formula for it. 1 divided by 1 plus np, which is numpy.exp minus z. Next, let's do the hyperbolic tan, which is tan h, and it takes z as input. I'm going to return np dot tan h. So as I mentioned, you don't have to remember the formulas or use cases. They're all available for you in NumPy. Next, I'm going to use ReLU. For ReLU, you return np dot maximum, and that's here maximum 0 to z. That's the formula for ReLU, and that's the function that you use, maximum. Next, we have softmax. Now for softmax, the way you define this is exp of z equal to, this is a little bit complicated, where you say np.exp. This is the numerical, for numerical stability we do this, z minus np dot max of z. So that will give me exponential of z, and then I will return exp underscore z divide by exp underscore z dot sum of axis equal to 0 and keep dims equal to true. So this is the function. Now this is the formula for softmax. So these will never change, so you can use them, and in future we'll probably use some shorter methods of doing this. Now let's go ahead and implement the forward pass function. So I am going to say forward pass function in comment here, so we know what we are doing. The definition of forward pass underscore pass takes x, takes the weights, as I mentioned, all the different things that it will take, biases, and it needs an activation function underscore function. So this is how you define a forward pass. Now in here we need z, which is np dot dot, so multiplication of weights, as I mentioned in the formulas for forward pass, is w times x plus b, which is biases. So that's how we do it. Next, we need the value of a, which is activation function of the z above, and that's what we will return. Perfect. So that's our forward pass. Next, let's give some example inputs. In this case, I will say x equal to, let's create an array from np array, and I'll give the values inside here as 0.5, just to keep it simple, and 0.8 looks like, close it before, okay, there you go. These are my input features. Now I need my weights. For weights, I'm going to create an np of array again, and inside this I will give 0.2 comma 0.4 and 0.6 and 0.1. So these are my different weights that I'm using. Now for biases, I will say np dot array, and here I'm going to say 0.1 and 0.2. So these are my biases. So I have my input features, I have my weights and my biases. So once we have this, let's go ahead and perform the forward pass with different activation functions that we have defined above. So let's get all the activation that we have. So what are the different activations we have? For sigmoid, I have the sigmoid function, right? Next, for tan h, I have the tan h function that I've created above all these functions. Next, for ReLU, I have ReLU. There you go. Next, for softmax, I have softmax function above. So these are my different activation functions. Now for, I'm going to say, go through this activation items. So I'm going to say name comma function in, so this is the name, this is the function, in activations dot items. So I am looping through or iterating through each and every item here, and I'm saying output of those equal to forward pass, passing the x, passing weights, passing biases, and passing the function, which is the activation function it needs. And I'm going to say print f of, depending on the name, like which activation function I'm using, say activation output. So let's say sigmoid activation output is, go to new line and say whatever the output is slash n. So it will go one at a time and display us the output. So let's go ahead, save it, and let me run it here. Python day2 exercise.py, and there you go. We have the sigmoid activation output, we have tanh activation output, ReLU activation output, and softmax activation output here. Now, what is the fun in just looking at numbers when you can visualize them? So I'm going to go ahead and import matplotlib.pyplot. I always like to import, I keep my imports on the top, but just for now, I'm going to use it here just so we can go in flow. And I am going to define range of inputs here. Let's say z equal to np dot linspace minus 10, 10, and 100. So I'm trying to visualize the activation functions here. So for that, let's go ahead and say, let's plot activation functions. So I'm going to say plot dot figure size, come on, fig size equal to 12 comma 8. I think big enough for us to see. plt dot plot, and I'll give the value of z that I've above, and I'll, for y, I'll use sigmoid.z for the first one. I'll say label equal to sigmoid. Next, I'm going to do it for one tanh, ReLU, and activation, tanh and ReLU. So next, I'm going to say plot tanh, label equal to tanh. Next, I'll use ReLU of z and label equal to ReLU. And my last one is softmax. Label equal to softmax. So I have all the 4 plots here. Next, let's go say plot dot title, and for the title, I'll give activation functions. Next, I will say for X label, I will use input is Z, and for Y label, I'll say it's output. Next, I'll show the legend because I've given labels to everyone. So show that legend. If you want to see a grid, I can also display a grid and say that display it true, and finally show the plot. So save it. Now I'm going to go ahead, clear it out, and run it. And there you go. We have all our 4 sigmoid, we have tanh, ReLU, and softmax all displayed over here as per our code here. And if you do not see something similar to this, depending on your data range that you've given here, just let me know. If you see something different, please send me in my message. If you see any errors, do let me know and I'll get back to you as soon as possible. So from this, what we have done is we have gotten the forward pass where we observed how weights, biases, and activation functions influence the output of a neural network. We looked at different activation function behavior. We visualized and compared the characteristics of common activation functions. And based on this, you can choose the appropriate activation function for different layers and tasks that you will be working on. So just to summarize, today we understood the forward propagation process in a neural network. We gained knowledge of commonly used activation functions and their mathematical formulas. We developed an intuition for selecting activation function based on the task requirements, and finally gained some practical experience implementing and experimenting with forward propagation and activation functions. If you had any problems while implementing this, let me know. If you have any other questions, do get back to me on my messages and I'll get back to you as soon as possible. Day 3, loss functions and back propagation. Yesterday we looked at forward propagation. Today we're going to look at both loss functions and backpropagation. So first, let's understand loss functions. What are loss functions? Loss functions quantify the difference between the predicted output of a model and the actual target value. They guide the training process by providing a metric to minimize during optimization. What is their role in neural networks? First is error measurement. They evaluate the accuracy of predictions, and they also give feedback for optimization, where provides gradients for weight updates via backpropagation. Now let's look at some of the common types of loss functions first. We have mean squared error MSE, commonly used for regression tasks, and it penalizes larger errors more heavily than the smaller ones. Then we have cross entropy loss, which is used for classification tasks, and it measures the difference between true labels and the predicted probabilities. Next, let's look at introduction to backpropagation. What is backpropagation? Backpropagation is the process of computing gradients for each weight and bias in a neural network, enabling optimization algorithms like gradient descent to minimize the loss function. The steps involved in backpropagation are: first is a forward pass where we compute the output and loss for the current weights. Then is the backward pass, which calculates the gradient of the loss with respect to each parameter. And then is a weight update, where we use the gradients to update parameters. Some of the key concepts include: we have the gradient, which is the rate of change of the loss with respect to a parameter. We have gradient descent, which is an optimization algorithm that minimizes the loss by updating parameters in the direction of the negative gradient. And we have been through gradient descent before in earlier weeks. Now, with this back of our head, let's start with hands-on exercise where we will be implementing a basic loss function. We'll calculate the gradients manually and visualize the effects of different loss functions. So let's go ahead, start with a new file, call it day3 underscore exercise.py. Start with import numpy as np. Then let's get the mean square error MSE loss. Oops. The way to define this function is I'm going to say MSE, define MSE underscore loss y underscore true and y underscore predicted values. That's what it takes as input, and this will return NP. So MSE is nothing but mean of y underscore true minus y underscore pred squared 2. So that's how we define MSE loss. So once we have that, next let's go ahead and do the binary cross entropy or BCE loss function. To define this, I'm going to say binary cross entropy loss. Again, it takes the same y underscore true and takes y underscore pred as input parameters, and it does some manipulation with y underscore pred where you can clip y underscore pred. This is like preventing log of 0, that's why we do this, and we give 1 e raised to minus 15, 1 minus 1 e minus 15. So this is how you define the y pred, where you prevent log of 0. Next, I'm going to return minus np dot mean of y of true times np dot log of y pred. So now you see why we did that preventing log of 0 in the previous step, because of this. And then we say 1 minus y of true, let me show you this, times we say np dot log 1 minus y of pred. make sure it's displayed properly. So this is the actual formula for BCE loss, which is binary cross entropy. Now let's take some example data. Y of true equal to, I'm going to create an array for this data, where I will say the true values that we got was 1, 0, 1, and 1. Now the predicted value that were created for these were, let's say, np dot array, and for the first one is 0.9. I'll keep it as close to the values above as possible, 0.8 and 0.7. So if you see 1011, predicted value is 0.9, 0.2, 0.8, and 0.7. So now let's do the calculation of loss here. I'm going to say MSE equal to MSE loss, and to this I'll pass y underscore true values and y underscore pred values. Same thing for BCE. I will say binary cross entropy function that we created, and we'll pass y true and y pred. There you go. So that's calculates the loss, and let's display this out so we can see what these values are. MSE loss is MSE, and I'll say 0.4 f. Want to see the entire number for binary cross entropy loss. I will say BCE 0.4 f. So let's go ahead and look at these. I'm going to say Python day 3 underscore exercise, and here we go. We have MSE loss of 0.04 and binary cross entropy loss of 0.22. That's how you calculate the loss functions. Now let's go ahead and calculate the gradients manually. So what I'm going to do is I'm going to create a derivative of MSE loss. This function I'll call it DF MSE gradient, and this will take the same values y true and y pred as input, and this will return back 2 times. This is the formula for that, y underscore pred minus y underscore true divided by the length of y underscore true. So this is the formula for MSE gradient. Next, let's create a derivative of BCE loss. To do that, I'm going to go move up a little bit, and I'll say DEF BCE gradient. This also takes the same parameters, and the formula for this is again to prevent division by 0. I am going to make sure y pred equal to np dot first clip y underscore pred to 1 e minus 15 and 1 minus 1 e minus 15. Let's see if I got everything right. Yes, that's the formula to prevent division by 0, and then I will return y underscore pred minus y underscore true divided by y underscore pred times 1 minus y of pred. There you go. So that's the formula for BCE gradient. So I have that. Now let's go ahead and calculate the gradients. So I'm going to say gradient of MSE equal to MSE gradient, and I'll pass the same y true and y pred that we have initialized right here, the example data we have. Similarly for BCE, I will call the BCE gradient function, and here I'll pass y true and y pred. Let's go ahead and print this out to check MSE gradient, which is grad underscore MSE, and similarly BCE gradient is grad underscore BC. Let's look at these. And there you go. We have binary cross entropy loss, MSE gradients, MSE loss here. We have MSE gradients is minus 0.05, 0.1, minus 0.1, and minus 0.15. For BC gradients, we have these are the values depending on the inputs that we have provided. If you look at them, they're very close to the values there. Perfect. So this is how you calculate the loss and the gradients. Now let's go ahead and visualize these effects on the of loss function. So let's go ahead and draw some graphs. To do that, import matplotlib dot pyplot as plt. Oops. Next, I am going to go ahead and define my predictions and true labels. So for predictions, I will say np dot linspace and say 0 to 100 of them. True label true underscore label equal to 1, which is the fixed label that we are setting here. Next, I am going to go ahead and compute the losses. To compute the losses, I'm going to say MSE losses equal to true label minus p squared for p in predictions. So for all these predictions, I'm getting the MSE losses. Then next, I'm going to say BCE losses equal to, in this case, minus true label times np dot log of max of p comma 1e minus 15 minus 1 minus true label times np dot log of max, again 1 minus p this time, comma 1e minus 15 for p in predictions. Okay, I hope I got the formula right. Minus true label times np log max p 1e minus 15 minus 1 minus true label np log max 1 minus p 1e minus 15 for p in prediction. So perfect, looks good to me. Let's go ahead and do the plot now. So I'm going to say plot for this is plt dot figure, where I will specify the fig size equal to 10,6. So how big my plot needs to be, or my graph is to be, dot plot. First, let's do predictions, and then next to it MSE losses, and then label here I will specify as MSE loss. Next, for my predictions along with BCE losses, label equal to binary cross entropy loss. I like to have my full name displayed. plt dot title, I will say loss functions comparison, and then plt dot, I mean, based on the numbers that you have seen, you probably already have it in your mind of how it looks like, but it's always good to see it in graph. Y label is loss, plt dot legend, plt dot create a grid, and plt dot show. So this will plot our graph. We clear it out, run it again, and there you go. Here is a prediction from 0 to 1 for both binary cross entropy and for MSE loss. This is exactly what I expected, and that's what we get. Let me know if you were able to follow along and get through this exercise. If you have any questions, do let me know in messages and I'll get back to you. So just to summarize, today we gained a foundational understanding of loss functions and their role in training neural networks. We learned the mathematical formulations and applications of MSE and cross entropy loss. We developed an understanding of back propagation and gradient calculation, and finally, we gained some practical experience implementing these loss functions and manually calculating the gradients. We'll not have to do this, but this is a good exercise to understand how all these works in the background. If you have any questions or had any issues implementing these, let me know and I'll get back to you. Welcome to day 4. Today we're going to look at gradient descent and optimization techniques. I know we have already done gradient descent before, but this will be a good deep dive into gradient descent and learn more on the optimization techniques. So let's look at gradient descent and its variants. So again, just to refresh, what is a gradient descent? Gradient descent is an optimization algorithm used to minimize the loss function by iteratively adjusting the model's parameter in the direction of the negative gradient. The variants that exist of gradient descent include the batch gradient descent that uses the entire data set to compute gradients at each step. The pros for this is its accurate gradients, and cons is computationally expensive for large data sets. Next, we have the stochastic gradient descent or SGD, which updates the parameters using one data point at a time. The pros is its faster updates, but the cons is its high variance in updates can lead to oscillations. Next, we have the mini batch gradient descent, which updates parameters using a small subset or batch of the dataset. Its pros is it combines the efficiency of SGD with the stability of batch gradient descent. Next, let's talk about advanced optimization techniques. We have ADA grade, which adapts learning rates for each parameter by scaling inversely with the sum of gradient squared. The pros is it's suitable for sparse data. The cons is its learning rate decreases too aggressively over time. Next, we have the RMS prop, which modifies ADA grade by using an exponentially weighted moving average of squared gradients. The pros is it addresses ADA grade's aggressive learning rate decay, works well for non-convex problems. Next, we have ADAM, adaptive moment estimation. It combines momentum and RMS prop to adapt learning rates for each parameter. The pros is it works well in practice for most problems and computationally very efficient. Now let's talk about the importance of learning rate and choosing the right optimizer. As per learning rate, it determines the step size for parameter updates. If it's too high, may overshoot the minimum or cause divergence. If it's too low, it leads to slow convergence. Now, as per choosing the right optimizer, for SGD, it works well for simple convex problems. ADAM, it generally performs well across different tasks, and RMS prop often preferred for RNNs and sequence-based tasks. So, understanding all these, let's jump into a hands-on exercise where the objective is to implement gradient descent to update model weights and experiment with different optimizers using TensorFlow and or we're going to look at both TensorFlow and PyTorch. So first, let's generate a small data set. So I'm going to go new file python day4_ex. Here, let's start with import numpy as np. Next, I am going to import matplotlib.pyplot as plt. Next, I am going to generate some data. For this, I am going to say, and let's set the random seed. So every time I run this randomizer, it gives me the same data set, same random data, 2 times np dot random dot rand 100 comma 1. Next, I'll for my target, I'm going to say 4 plus 3 times x plus np dot random dot randn 100 comma 1. So I have my basic data with the features and targets. Now let's go ahead and visualize this data. I'm going to say plt dot scatter just to see how the data looks like. Color equal to blue. Next, I'm going to say plt dot, give a little bit title. I'm going to say just generated data set. Next, let's use the X label to say it's X. Plt dot Y label is Y. So my features and my target, show the grid and plt dot show. Perfect. Let's go ahead and run this. It's Python day 4 exercise, and there's my plot data with the generated data that we have, X and Y. It's a pretty linear data set that we have. That's good. Next step is to implement the gradient descent. So let's go ahead and I'm going to move it up. Initialize the parameters. So I'm going to use different parameters. N equal to 100. This is the number of samples that we have. We need theta, which is np dot random dot randn 2, 1. This is we did some random initialization. Next, I am going to do learning underscore rate equal to, let's set to 0.1, and iteration. Now again, if this is all new to you, we have already covered it in first few weeks, just to cover the basics on gradient descent. Next, we'll add some bias term to X. To do that, I'm going to say X underscore B equal to NP dot C underscore NP dot, let's add ones to it, M comma 1, and then comma X, apply to X. So what I'm doing is I'm adding an X0 equal to 1 to each instance in this particular case. So once I'm done with that, let's go ahead, and this is okay. I think there you go, better. Now gradient descent. So do that, I am going to say for iteration in range of our iterations. How many iterations do we have? If you look up here, we have 1000 iterations. So for each one of them, what's going to happen is I'm going to create gradients, which is 2 upon m times x underscore the bias x term that we have dot transform matrix of that, multiply that with x underscore b dot multiply that with theta minus y. This is the actual formula for that. Now to get the theta, what I'm going to do is I'm going to decrement theta based on the gradient that we have using learning rate and multiply that with gradients. So that will give me my gradient descent, and that I can print it out saying optimized parameters theta slash n comma theta. So let's see how that looks like. I'm gonna comment out the visualization for now so I can see just this thing here. I'm gonna clear it out, run it again, and there you go. We have the optimized theta from 4 and 2. So that's our optimized theta based on the random data that we have generated. Now let's go ahead and experiment with TensorFlow optimizers of how to use that. So for implementing TensorFlow, I need to first import TensorFlow as TF. So now that I have TensorFlow, let's prepare the data based on what we have generated earlier. I'm going to say x underscore tensor equal to TF dot constant. That's my TensorFlow function, and it needs x, and I'll say d type equal to TF dot float of 32. It needs to be in float 32 format. Next, I'm going to say y underscore tensor TF constant, and I'm going to say y d type TF dot float 32. Perfect. Next, I am going to define the model. I'm going to create a linear model and pass it TF dot module, and in here First, let's write the initializer method. Initializer, pass self to it. And the way to do it is I'm going to assign the weights and biases to this. So I'm going to say weights equal to tf dot variable tf dot random dot normal around 1. So that will give me my weights. I'll also use the bias, which is tf dot variable, and to this I'll assign tf dot random random dot normal, and again around 1. Perfect. So I have my weights and bias initialized in my initialization function. Next, let's do the call function, and to this I'm going to pass self and x, and here I am going to return self dot weights, these weights times x plus self dot okay, I think need to make sure that I don't have typos. Self dot bias. Perfect. So I have that. Now I can define the loss function here. Now to define the loss function, I'm going to use the MSC loss that we implemented earlier this week. Y underscore true and y underscore predict. Now inside this, I will return TensorFlow dot reduce mean tf dot square of y underscore true minus y underscore pred. So this TensorFlow gives us I use y underscore, gives us this library reduce mean, which lets us easily calculate the MSC loss function. Now next, let's train this with S. So we're training this with stochastic gradient descent here. We're going to say model equal to linear model, or model that we've created. And then I'm going to say optimizer equal to tf dot optimizer. Oops, it doesn't show me optimizer. There you go. Underscore optimizers. Nope, it's optimizers dot sgd. And then I'll say learning rate equal to 0.1. There you go. So that should work. Next thing is, now let's go through each and every iterations. So run through different iterations. We have not defined any iterations here, but I'm going to say in the range of 100, I'll open tf dot gradient tape as tape y underscore pred here equal to model, and pass x underscore tensor to that. Next, I'm going to say loss equal to MSC loss, and pass it y underscore tensor and y underscore pred values that we have. Next, I'll get the gradients equal to tape dot gradients, tape dot gradients gradient, and it needs loss. I think it needs model dot weights and biases, right? So model, so those are initializer functions, and that I'll call and pass these values. Next, I'm going to do optimizer dot apply underscore gradients. The gradients that I'm going to apply is, first I'm going to use a zip function to put gradients and model dot weights and model dot bias. I hope I don't have any, doesn't look like that I have any issues here. If sometimes I do typos, so that's kind of causes issues. Now I'm going to check every 10 epochs or 10 rounds. So we'll stop here every 10 times totally, because we have 100 total epochs. I'm going to say epoch, depending on what the epoch number is. So it will be 10, 20, 30, 40, 50 until 100. Loss is loss dot numpy. So I can probably see it in a float format. There you go. So that's what I'm going to print out. So let's run this and check how it looks like. I don't need gradient descent, but I'll keep that and clear this out, run it. It's going to run through that in a second. And there you go. For every single epochs, if you see, initially the loss was 91, but as and when it goes closer, it came down, and it made sure that it reduces at every single epoch. More and more you run it closer to 0, it will go to, because it's gradient descent is this. So it goes from 91 to 0 here. Perfect. Next, we're going to do experiment with the PyTorch optimizers. So to do the something similar, I am going to go ahead and import torch. I can go ahead and comment this out. Import torch dot nn as nn. Next, I need another module from there, which is torch dot optimizer as optim. This is called optim. Now let's go ahead and prepare the data. So for this, I'm going to say x underscore torch equal to torch dot tensor, and to this I'll pass x comma data type equal to torch dot float 32. There you go. So that's my x torch. For my y data, y torch, converting that into PyTorch format. There you go. Perfect. Next, I'm going to go ahead and define the model. This model will be very close to what we did here, but I'm going to call it something different. Torch, and then here we need to pass PyTorch module, which is nn.module self, and then here, instead of doing this, inside the initializer function, I can directly call the super and say linear model torch self dot underscore underscore init. So it has that function, so I can directly call that. Perfect. And then I can say self dot linear equal to nn dot linear, and then pass it values of 1 comma 1. Perfect. Next, I don't need the call function. I will create another function here, call it forward, pass itself and x. In here I will return self dot linear of value x that is passed to me. Perfect. So that's our model definition over here. Next, I'm going to say model underscore torch equal to linear model torch. So I'm going to initialize that model that I've created above. Next, let's define the loss function and optimizer, both of them together here. So for my loss function, I'm going to say criterion equal to nn dot msc loss. That's what I'm going to do. For optimizer, I am going to say optim dot atom, and I'll pass model underscore torch dot parameters, and I'm going to say lr equal to 0.1. Now let's go ahead and train the model. So I'm going to say train model. Now to train the model, let's run through the same epoch, same kind of function in range of 100. I am going to say optimizer dot 0 underscore grad outputs equal to model underscore torch, and pass it x underscore torch. Loss equal to criterion, and to that I'll pass outputs and y torch. Perfect. So that will give me my loss. And now let's go loss and backward propagation. So that you just have to call loss dot backward, and optimizer, I will say dot step. So next step on the optimizer. And here again, if uh, epoch, just to display the values, mod 10 equal to 0, then I'll say print f, depending on which epoch it is, epoch, the loss dot items 0.4 f. Perfect. And this is not capital, this is small based on the loss. Perfect. So I have this. Now go ahead and let's go and run this part. Clear this out, run it. Oh, looks like I said items. Okay, let's do item. Perfect. Clear, run it again. And there you go. We have our loss function 70, 40, 20, 80 gradually decreasing to almost 1 here, 0.9. So that's perfect. So we kind of saw how we can experiment with optimizers like HGD and Adam to understand their impact on the training. Use a TensorFlow. Using TensorFlow and PyTorch was a benefit of how you can do all these things pretty quickly and easily with these frameworks that are available. So I hope you are able to follow along. If you have any issues or questions, do let me know. But just to recap, today we went and understood the mechanics of gradient descent and its variants. We learned advanced optimization techniques like Adam, RMS prop, and their use cases. We did some hands-on exercises implementing optimizers in both TensorFlow and PyTorch, and we developed intuition for selecting learning rates and optimizers for different problems. If you had any issues or have any questions, do let me know in the messages and I'll get back to you. Day 5, Building Neural Networks with TensorFlow and Keras. Today, we're going to go over first introduction to TensorFlow and Keras for deep learning. What is TensorFlow? TensorFlow is an open source library for numerical computation and machine learning. It provides tools for building and training deep learning models. What is Keras? Keras is a high level API integrated with TensorFlow that simplifies the process of creating and training neural networks. Now let's look at some of the key features of Keras. It's user friendly, it's intuitive syntax for rapid prototyping, modular, which is building blocks for defining layers, optimizers, and loss function. And as per integration goes, it's compatible with TensorFlow and scalable deep learning tasks. Let's look at defining layers, models, and compiling networks in Keras. So first, let's look at defining layers. Layers are the building blocks of neural networks. Common types include, we have dense, which is fully connected layers, and where each neuron is connected to every neuron in the previous layer. Then we have the dropout layers. It randomly drops connections to prevent overfitting. Then we have the activation layers, which applies activation functions to introduce non-linearity. Now let's go ahead and build models. Keras supports two primary ways to define models. One is sequential API, which is a linear stack of layers. And then we have the functional API, which is more flexible and allows for complex architectures. Next, talk about compiling a model. This specifies optimizer, which is algorithm to update weights. Examples are Adam or HGD. Then loss function. This is a metric to minimize during training. Example can be cross entropy. And then we have metrics for additional performance measures. Example can be accuracy. Next, let's talk about training, evaluating, and saving a model. Now, for training, you can fit the model to data using model.fit. For evaluation, you can test the model on unseen data using model.evaluate function. And for saving and loading, you can save a trained model using model.save and reload it with keras.models.load model. With all this knowledge, let's jump into our hands-on exercise where the objective is to build, train, evaluate, and save a simple neural network to classify digits from the MNIST dataset. So, our step one is create a file first, save it as day5 underscore exercise, and here we'll load and pre-process the MNIST dataset. So I'm going to import TensorFlow as TF. Next, I am going to take from TensorFlow dot keras dot datasets. I am going to import MNIST dataset. Oops. Next, I am going to go from TensorFlow dot keras dot utils. I am going to import to underscore categorical. So these are the libraries that I need. Now let's go ahead and load the MNIST dataset. Load MNIST dataset. To do that, I will have x underscore train, y underscore train. We'll have another tuple of x underscore test, y underscore test equal to, go to MNIST and say load the data. So this will load my data in these parameters, these variables here. And now once I have that, let's go ahead and normalize the data. X underscore train equal to x underscore train dot reshape that from -1 to 28. These are the size of the images. 1 dot as type float of 32 divided by 255.0. Same thing I'm going to do with my x test data. I'll take the x test data, reshape it -1 28 28 as type float of 32, because the whatever data we get, I have rows and then slash 28 by 28 image size, and that's what I'm converting into as type float 32 and have that available. Next, let's add the one hot encode the labels. So we have y underscore train. These are the labels that tell you what numbers they are, which are returned. So I'm going to convert that to categorical. Whatever y train we have, 10, and then same thing for y test. So there you go. So it's converted now. So we have encoded the labels. Now let's go ahead and print and see how does it look like. Training data shape is x underscore train dot shape, test data shape, test dot shape. Just let's to confirm, let's go ahead and run python day5 underscore ex dot py. It will download that data set, and it looks like I have misspelled utils. Clear it out, run it again, and we have the data set. Now we have it in proper 60,000 2021, 10,000 2021 for the test data shape. So we have everything that we need. Next thing that we need to do is define a neural network. So I am going to take something from the models that are available. So first let's get we need the sequential model from TensorFlow dot keras dot models. I want to import sequential. Now this module contains tools for building neural network models, and sequential is a linear stack of layers. It allows you to add one layer at a time, going from input to output sequentially, and that's what we are going to use. Next, I'm going to say from TensorFlow dot keras dot layers, I want to import dense. Now this so from TensorFlow keras layers, which provides building blocks for layers in a neural network, we are importing dense, which is a fully connected layer where each neuron is connected to every neuron in the previous layer. So that's what dense does. Next, I'm going to use flatten. Now, flatten is something that flattens a multi-dimensional input into a single vector for fully connected layers. So that's why I'm using flatten. Conv 2D. Now, this is a 2D convolutional layer that applies filters to the input image to extract features. So that's why I'm using that. Next one I'm going to use is max pooling 2D. Max pooling 2D reduces the spatial dimensions of the input while retaining the important features, so it's used for downsampling. And then finally, I will use dropout. This is a regularization technique to randomly set a fraction of the input units to 0 during training, preventing like overfitting. So now I'm going to go here and first let's create the model. So I'm going to say or build the model. So for model, I'm going to say model equal to sequential. Now this initializes a sequential model. Layers will be added sequentially here. So I am going to create a subset. Okay, there you go. The first thing that I want to add conv 2D, which is the 2D convolutional layer. So I'm going to say conv 2D, and then I need to pass 32, which is number of filters. These are learnable feature detectors. Next parameter that it takes is 3 by 3. Now this is the filter kernel size, meaning each filter is a 3 by 3 matrix. Next I want is activation equal to ReLU. So here I'm setting activation equal to ReLU, which means it applies the rectified linear unit ReLU activation function, which sets negative values to 0, introducing non-linearity. And I am going to say input underscore shape equal to 28, 28, 1. So this specifies the shape of the input image, which is 28 by 28 pixels with one channel, which is the grayscale, which is what we have created above. So that's what I'm specifying here. Now next, oops, I think comma. Next I want to do is use the max pooling 2D and pass it to comma 2. What I'm doing here is I am saying to add a max pooling 2D layer with 2 by 2 pool size, meaning it reduces each 2 by 2 block in the input to a single maximum value. This reduces the spatial dimensions by half. Next, I'm going to flatten everything. This pretty much adds a flatten layer to convert the 2D feature map output of the previous layer into a 1D vector. Necessary for this is necessary for connecting convolutional layers to fully connected layers. So now that we have that, I'm going to use a dense layer 128 comma activation equal to ReLU. Here I am adding a dense layer with 128 neurons, and I'm setting activation equal to ReLU, which applies the ReLU activation function. Finally, I'll say dropout 0.5. What this does is it adds a dropout layer. 0.5 is the fraction of neurons to randomly drop during training, helps prevent overfitting. And actually, this is the final step. Dense 10 comma activation equal to softmax, output layer for the classification. So this adds the final output layer. 10 neurons is corresponds to the 10 output classes, example digits 0 to 9. If this because we are using the MNIST data set, which have 10 different digits, that's what we are using here. And activation softmax outputs a probability distribution across those 10 different classes. So finally, let's go ahead and display model architecture. This I can do by saying model dot summary. This displays the model architecture showing each layer type, output shape, and the number of parameters, also total number of trainable and non-trainable parameters in the model. So that's what this does. Let's go ahead and run this just to play around with it. I'm going to go here, run it, and there you go. it did all the things and it gave me my layer definition here. If you see con 2D, max pooling 2D, flattened, dense, dropout, and dense one, and it showed you all the output shape from it and gave you different parameters numbers here. Total parameters is these many parameters are used. Trainable parameters are these, non-train. So it gives you a summary of the entire model that we have created. Now let's go ahead and compile the model. So I'm going to say compile the model, and then I'm going to say model dot compile. Now what do I need to pass to this? I need to use optimizer. Which optimizer I want to use is Adam optimizer. I want to, for loss, I want to use categorical and cross entropy. Next, for metrics, I want to use accuracy. Perfect. So that will compile my model. And now let's go ahead and train the model. That's our next step. Train the model. So I'm going to say history equal to model dot fit, and inside here I'm going to pass x underscore train, y underscore train, also other parameters, how many epochs I want to train it for. I'm going to say 10 epochs. Batch size I want to use equal to I'll say batch size of 32, and then validation split that I want to do is 2080, so 0.2. So I'm going to set here. So this will train the model. Next, let's go ahead and evaluate the model. To evaluate the model, I am going to say evaluate first the model. For that, I can just get the test loss. I can get test accuracy of this model by calling a function called as model dot evaluate. So with the TensorFlow, we don't have to do all the other things that we used to do before. It's pretty straightforward. We just call model dot evaluate, and I can print now test accuracy is test underscore accuracy 0.4f. Perfect. Now let's go and save the model. Let's see how we can save this model and also reload this model if you ever want to reload this trained model. So once you're done training, it's always a good idea to save it so you don't have to go through this step again and again. I'm going to call this mnist underscore classifier dot h5. That's how I'm going to save this model as. Now if you want to load this model ever again in some other code, so let's say you train this and now you want to use it somewhere, you can just say from TensorFlow dot Keras, so you don't have to do this training every single time. I mean, that's how it works. Once you train the model, you load it into your application and you make sure that, okay, let me fix import load model, and then you use this model over and over again in your production application. Loaded model equal to load model. I'm going to give the name that I saved it as. Okay, next I am going to verify loaded model's performance. That's another thing that you have to kind of cross check if the loss and accuracy is same as what we got earlier, because it's the same model. Evaluate x underscore test and y underscore test, because that's the data set that I have. I'm going to say print f loaded model accuracy is 0.4f. Oops, sorry. Need to first give the accuracy 0.4f. Perfect. That's the entire code that we have here. So let's go ahead and run it. Clear it out. Run it all over again. So we'll see the summary. We'll see all the things that you've done here step at a time. So my summary, now it's going here again here, and it's going to run through 10 different cycles to train the model. So I'm going to give it a little pause and come back to it once it's done. So it took some time and we went through all the 10 epochs. And as you can see, every single time the loss is changing here for each and every iteration. We have the accuracy changing and getting better every single time. And our test accuracy finally is 0.9871. And then it saved the model. And then I loaded the model again. If you open this particular folder, we'll see that we have the MNIST classifier H5 saved here. It's around 8.4 MB size, and then I loaded that model and then tested the accuracy. It's still the same thing, 0.871, because I'm giving the same data to it. So that, there you go. This is how you can create a model, train a model, evaluate, and then finally save it into your hard disk. And then next time when you're working on a project, you can load it directly from there, or you can also serve it on cloud and then write some APIs around it to use this particular model. So just to summarize, today we understood how to define and compile a neural network in Keras. We learned to pre-process data for deep learning models, and we gained experience in training, evaluating, and saving a deep learning model. Finally, we developed some practical skills in working with MNIST dataset for image classification. I hope it was helpful and you were able to follow along. If you had any issues in installing or writing this code, if you have any other questions or any suggestions, let me know in the messages and I'll get back to you. Day 6. Building neural networks with PyTorch. Yesterday we did something similar with Keras. Let's see how you can do this with PyTorch today. First, let's go ahead and introduce PyTorch and its core components. Now, what is PyTorch? PyTorch is an open source deep learning framework that provides flexibility and dynamic computation for building and training machine learning models. Some of the core components of PyTorch include we have tensors, which is multidimensional arrays, similar to NumPy arrays and with GPU support for accelerated computation. We have AutoGrad, which are automatic differentiation engine that computes gradients for optimization. And then we have Torch NN module, which we've used already, which provides tools to define and train neural networks with layers, activation functions, and loss function. Let's talk about building a neural network in PyTorch. The steps that we will follow is first we'll define the model. We use torch nn.module to create a neural network with layers and forward propagation. Next, we're going to define the loss function. We'll use built-in loss functions like cross entropy loss. Then we'll define the optimizer. We'll use optimizers like SGD or Adam for weight updates. Next, let's talk about training, evaluating, and saving a model in PyTorch. For training, we will use forward pass to compute predictions. Next, we're going to compute loss and gradients using backpropagation. And then we will update the weights using an optimizer. For evaluation, we'll test the model on unseen data and calculate metrics like accuracy. Finally, saving and loading. We'll save the model's parameters using torch.save and load them using torch.load. Now let's jump into our hands-on exercise where our objective is to build, train, and evaluate and save a neural network for MNIST digit classification using PyTorch. So our step 1 is to load and pre-process the MNIST dataset. For that, I'm going to go ahead, create a new file, save it as day6_ex, and here first let me import Torch. This is the core PyTorch library for tensor operations and deep learning. Next, I'm going to say from Torch Vision, I am going to import datasets and transforms. So here, Torch Vision.datasets provides popular datasets like MNIST, which we'll be using, and also it has Cypher10 if you want to use. The Torch Vision transforms provide transformations for pre-processing data, example converting to tensor and normalizing. And finally, we'll use from torch.utils.data import data loader. So this data loader is a utility to handle data batching shuffling and loading in parallel. So next, let's go ahead and define our transformations. So I'm going to say transformation equal to transforms dot compose, and here I will say transforms dot to tensor. That's the function that I'll call. And next I'll say transforms dot normalize, and I'll pass the value 0.5 comma 2 comma 0.5 comma. So what I'm doing here, so the transform.compose, it combines a list of transformations to be applied sequentially. So first I convert by calling the to tensor, I'm converting image data into PyTorch tensors, which scales pixel values to 0 to 1. Next, I am normalizing tensor data to have a mean of 0.5 and a standard deviation of 0.5 for better training stability. And that's what this 0.5, 0.5 is here. Now, next step is to load the data sets. So I'm going to go ahead and say load data sets. I need the training data set equal to data sets dot mnist root equal to dot slash data train equal to true transform equal to transform that we created above, and download equal to true. So here let's make sure, okay, this is, I've saved it as transformation. I don't know why. Transform is what I wanted to save it as. Perfect. So there you go. So what I'm doing here is I'm downloading the mnist data set. Root equal to dot slash data is the directory to store the data set. So it will create a folder called as data and save it there. Train equal to true or false, which specifies whether to load the training or testing set. And transform equal to transfer applies the defined transformations to the data set. And download equal to true, it downloads the data set if not already present. So next thing is same, this is for the training data set. Now I'm going to say next for test data set mnist root equal to dot data, and here not for training, it's for testing, so I'm going to say false, and download equal to true. Perfect. So that's what I'm going to say here. Our next step is to create the data loaders. So I'm going to say create data loaders. Now I'm going to create a train loader equal to data loader. I have that imported. So I'm going to say train data set is what I'm going to pass it. Say batch size equal to 32 and shuffle equal to true. So what I'm doing here is the data loader function loads data in batches for training and testing. So when I say batch size equal to 32 is the number of samples per batch. Shuffle equal to true, it shuffles the training data to ensure randomness. So if I set shuffle equal to false, which is in my test loader, data loader, I'm going to give the test data set, and I think make sure that there's no typo. Batch size 32, shuffle equal to false. It keeps the test data in order for evaluation. So that's what it does here. Next, let's go ahead and print our training data size to see how does it look like. This will be length of train underscore data set. Similarly, I can do the same thing for test data set, where I'm saying test data set length. I'm going to go ahead and open my terminal, and I'll say Python day 6 underscore exercise, run it. And since it's not been downloaded, it's downloading it first time, and it's going to save in my .data folder. And it says training data size is 60,000 and test data size is equal to 10,000. If it can't find the data set, it'll try the next one and try to download it from there. So you don't have to worry about that. I'm going to clear it out. If I run it again, You see, it doesn't download it again because it's already downloaded it. I can open this and check the data folder, and you'll see the MNIST dataset is available right here. Perfect. I'll close this, go back here, go back to our coding. Our next step is to define the neural network. So to define the neural network, what I'm going to do is I am going to go ahead and first import torch.nn as nn. Next, I will import torch.nn.functional as f. So this torch.nn module provides classes and functions for building and defining neural networks. It contains predefined building blocks like layers, loss functions, activation functions, and more. The alias nn is used for convenience to access these components more easily. And then I'm doing the same thing for functional, where this module kind of contains functions for operations that can be applied directly without defining them as layers. These are stateless functions, meaning they don't have parameters that need to be learned, like weights or biases. And it's commonly used for applying activation functions or loss computation directly. And we'll probably see how we are going to use them in the following code. So go ahead and first, let's say here I am going to define the model. For this, I'm going to create a class called as neural network, and I'll pass nn.module to it. So nn module, what it does is it creates the base class. It's the base class for all PyTorch models, and that's what I'm doing here. And then I am going to override the or define the initializer method init underscore self. Now here I am going to call the super method first, which is neural network, and pass self object and call the initializer method of that init underscore. That's how we call that. Next thing that I'll do is I will say the flatten function or flatten layer equal to nn dot flatten. So this flattens the 2D image 28 by 28 into 1D vector. So that's why we're using this. Next, I'm going to say self dot fc1 equal to nn dot linear. This is my first layer. So I'm going to say linear 28 times 28 comma 128. So this is what I'm creating is input size is in this particular case is 784, which is the 1-day vector from my flatten. So I am saying that flatten that into a size of 128. That's what I'm doing here. Next, I'm going to say self dot fc2 equal to my second layer. I am saying linear 128 comma 64. So whatever the input that comes from this 128, I am changing that to an output size of 64. Next, I am going to create another hidden layer, and I'm going to say nn dot linear, and the 64 I'm going to convert that into 10. So this is an output size in 10 for 10 different classes that we have for numbers. Next, we're going to define, as I mentioned, the forward class. So I'm going to say forward function. So say self comma x in here. So this is for forward pass, where I am going to say x equal to self dot flatten, whatever that function above is, and pass x to it. Next, I'm going to say x equal to f dot ReLU. As I mentioned, f is used for all the different activation functions. So first I'm going to say self dot fc1 of x. Next, I'm going to say ReLU self dot fc2 of x. Then x equal to self dot fc3, the output layer, x, and then return the value of x. So this f dot ReLU, it applies ReLU activation to introduce non-linearity in this particular case. And finally, we'll go ahead and initialize the model. I'm going to say model equal to neural network, and if I want, I can print the model, but we'll probably see this later. So this is your entire code to define the neural network. Now the next thing is we are going to go and define the loss function and the optimizer. So for that, I am going to say, as I mentioned, define loss function and optimizer. For this, I will say the criterion equal to nn dot cross entropy loss and optimizer equal to torch dot optim dot, as I mentioned, SGD or Adam is what I'm going to use. So I'm going to use Adam this time, and I'm going to say model dot parameters. I'll pass the first the parameter, which is model dot parameters, and LR learning rate equal to 0.001. So what I've done here is the criterion is the loss function where I'm using cross entropy for multi-class classification, and which because we have 10 different outputs here. Optimizer, we are specifying Adam optimizer for updating model weights, and learning rate I'm specifying it to 0.001. Next step is to train the model. So for training the model, I'm going to create a function. We'll call it training loop. Let's move it all the way to the top. Say function, and I'll say train underscore model, and the parameter that it needs is it needs model, it needs the train loader, it needs criterion. I'm going to just copy this. I need optimizer, and I need epochs. If I've not specified an epochs, I'll just run it for 5. That's what I'll set as default. And I'll say model dot train here first. Model dot train puts the model in the training mode. Now I can run the epochs. Run epoch in range of epochs. Yes, there you go. Now what I'm going to do is I am going to put a running loss, create a variable called as running loss equal to 0.0, and then once I have that set, I am going to say for images comma labels in train loader, because that's where my training data is. So this iterates through batches of the training data, and first I'm going to go and do the zero gradients where I'm going to say optimizer, I want to do a 0 underscore grad. This resets all the gradients first. Next I'm going to say, so for each and every image it will go ahead and do that. Next is forward pass, where I'm going to say outputs from this forward pass equal to model images. So this performs a forward pass, as I mentioned. Next I have loss equal to, this will calculate the loss. I'm going to use the criterion and pass it outputs and labels. Next I want to do the backward pass and optimize. So I will, let me write that, backward pass and optimize. Oops, caps lock got on, and optimize. So here I'm going to say loss dot backward. So this will compute the gradients for back propagation, and then finally I'll say, not finally but optimizer dot step. This will update the model parameters, and then now the running loss that I've created above, I'm going to increment that to loss dot this particular item, and then I can print here, just for display purposes, our epoch is epoch plus 1, increment that to 1, and loss is running loss that we are incrementing, divide by length of train loader 0.4 f. So running loss distracts the loss for each epoch and updates it, and then finally we do this. Now we have this. Now let's run this, because This is just a function. So I'm going to go outside and I'll say train the model. And now I'll pass all the parameters that we already have. We have model, we have the train loader, we have criterion, we have optimizer, and epoch. I will, and let's just see one more, epoch equal to 5. I'll leave it the default of 5 times. So this will train the model for 5 epochs. So once that is done, our next step is to evaluate the model. So I'm going to go, before even running it, let's write the code to do the evaluation loop. Again, I'll write a function. I'm going to say evaluation underscore model, or evaluate underscore model, and this needs our model and it needs our test loader. Now here, to evaluate it, I'll say model dot eval. Oops. Just like model dot train, model dot eval puts the model in the evaluation mode. Next, I'm going to create some variables, correct equal to 0 and total. I'll tell you why these are in a second. Total equal to 0. Now with torch dot no underscore grad. So this disables gradient computation for efficiency. And with that on, I am going to go over the images and label in my test loader. And I'll first calculate the outputs, which is model of images. Next, I will say underscore comma. I will get the predicted. The first one is because it gives me 2 different parameters and I don't care about the first one. So that's why I've used underscore max outputs dot data comma 1. This will get me the class with the highest probability. So that's what I want. Next, I'm going to say total plus equal to labels dot size. So I'm going to save that for this particular iteration. And then correct plus equal to predicted equal to labels. If it's right predicted, I am going to say sum dot item. Keep on adding them. So that's why I am incrementing it. Next, let's go ahead and print f of test accuracy. Oops. 100 times correct divide by total 0.2f. So that will give me my percentage value. That's why I multiplied with 100. And finally, let's go ahead and evaluate the model, pass the model and the test loader. Perfect. So I've passed those. So that will, now we can do save also, but yeah, let's go ahead and save first before even doing the next step. So as I mentioned, it's always better to save the model and see how we can save it. So I'm going to say torch dot save. So there's a built-in function as I mentioned, and I can say model dot state underscore dect. That's where my model is available. I'm going to say the model name is mnest underscore model dot pth. Since it's PyTorch, I'm going to save it as pth. And if you want to reload the model, again, the loaded underscore model equal to neural network. I'll initialize that, and I'm going to say loaded underscore model dot load underscore state underscore dect, and I can just use torch dot load and whatever I've saved it as .pth file. Perfect. So that's how you can load it. Now if you want to verify it, verify the loaded model performance just to make sure that it's fine. You can always call the evaluated and then get the loaded model and use the same test loader to test it out. So that's does take care of it. Now, if you want to experiment with model structure and the learning rate, you can always update the optimizer. I'm going to just write this code, but I'm not going to run it. Optimizer with a new learning rate. You can just say optimizer equal to torch dot optim dot atom and pass model dot parameters. That's what we did earlier. And learning rate equal to, this time I want to increase one more decimal, 0.0001, and then I can say train underscore model, pass it the model, pass the train loader, and then we need criterion, and then we pass the optimizer for epochs. I'll keep it the default 5, and then you can evaluate the model again and call that model comma test loader. Now if you want to try this out, you can try it out, but I am not going to run this because this will work, of course, because we have this earlier too. So I'm going to save this, go back and clear it out and run it again. Oh, looks like I have an error. Instead of nn.module with a capital M, I am using a small m. Perfect. Let's go clear it out, run it again. And there you go. We have the training data size, test data size, neural network, and now it's going through the epochs and printing it out. It's going to take some time to display all the epochs, so I'm going to just pause it here and then come once it's done and and talk about the output. I realized we only ran it for 5 epochs, so it didn't take much time. We were almost done. But as you can see here, it gave me the loss for the 5 epochs. It gave me the test accuracy of 96.92. And after I saved, I mean, it's giving me a warning for whatever I'm loading and saving and loading, but that's fine. You can ignore that. And once I load it, I see the test accuracy is exactly same as because it's the same model that I'm saving. And if I open this particular folder, you'll probably see that I have the MNIST model right here saved. I have my data from MNIST right here. So this is perfect. I hope you have the same experience here. If you don't, if there was an error or issue that is an error, not a warning, let me know in the comments and I'll get back to you. But just to summarize, today we went and understood PyTorch's core components, the tensors, AutoGrad, and NN module. We gained hands-on experience building and training a neural network in PyTorch, and we learned how to evaluate and save PyTorch models effectively. And finally, we developed intuition for experimenting with model architectures and hyperparameters. So if you have any problems or issues or have any questions, do let me know and I'll get back to you. Day 7. Neural network project. Now that we are end of this week, let's do a final project where we are going to do image classification on a Cypher 10. Now this might need a lot of processing power on your computers, so make sure you're prepared for this. The first thing that we want to dive into is applying learned concepts to a more complex project. So that's why we're using Cypher 10. Now why Cypher 10? Cypher 10 is a challenging benchmark dataset for image classification. It contains 60,000 32 by 32 color images across 10 classes. Example, it has airplane, cars, birds, dogs. So unlike the MNIST, Cypher 10 involves more complex patterns and requires robust neural network architecture. Let's talk about building and optimizing a neural network for image classification. The key steps is first pre-process the dataset for training, example normalization and one-hot encoding. Next, we're going to define a neural network with convolutional layers for feature extraction. And then we optimize the network using techniques like learning rate adjustment and dropout. Let's talk about analyzing the model performance and experimenting with hyperparameters. We'll do performance analysis where we evaluate accuracy and loss curves during training. Then we use the test set metrics to measure the generalization. For experimentation, we'll try different activation functions, example ReLU or TANH, and we'll test optimizers like SGD, ADAM, and RMS prop. Next, adjust the learning rate and regularization techniques, example dropout and weight decay. So with all this, let's jump into a hands-on project where the objective is to build, train, and optimize a neural network for Cipher 10 image classification, experimenting with hyperparameters to improve the performance. So first, let's go ahead, create a new file, save it, as day 7 underscore exercise. So let's go ahead and import TensorFlow as TF. Next, I am going to say from TensorFlow dot keras dot datasets, I am going to import the Cipher 10 dataset. Now from TensorFlow.keras.utils, I will import to categorical. This will make sure my data is okay. I think looks like TensorFlow. Okay, rest of them is fine. They're just giving me warnings right now, but that's fine. You can ignore them. They are available. Next, I'm going to go ahead and load the Cipher 10 dataset. That I can do by saying xtrain my tuples y underscore train comma x underscore test comma y underscore test will have Cipher 10 dot load underscore data. So that will load my data into this particular these variables. Next step is to normalize pixel values to 0, 1. So I am going to say x train equal to x underscore train dot as type, and I will convert that into float 32 because that's what it needs, divide by 255.0. I will do the same thing for my test data set. So I'm going to say test as type float 32 divided by 255. Perfect. Next thing is we're going to go and do one hot encoding the target values, target labels. So to do that, I am going to say y train equal to 2. As I mentioned, this has all different types of target values, like it can be bird, plane, dogs, all that stuff. So I'm going to say move them to 10 different classes. Same thing I'm going to do for test to categorical y test 10. So perfect. Now I can go ahead and print saying my training data shape equal to x underscore train dot shape comma y underscore train dot shape. So that's my training data. Same thing I can say for testing data shape. I'll say x underscore test y underscore test and give the shape for that. Now I'm not going to print this out because I know the shape of these. So I'm going to just jump into my next step, which is to define a baseline neural network. So for that, I am going to go to TensorFlow dot keras, and from keras I have models where I'm going to import the sequential, which were used earlier. As I mentioned, these use the different layers in a sequential order, so that's why we use sequential. Next, I'm going to say TensorFlow dot keras dot layers. For creating my different layers, convolutional layer first, so I'm going to use con2d. For my max pooling, I will use max pooling 2d. Next, I need for flatten, I'm going to call flatten. I'll use dense, and I will use dropout. These are all the libraries available, and we've gone through this earlier this week. So if you want to catch up with that, you can look at my previous video. Next, let's go ahead and define the baseline model. To do that, I'm going to say model equal to sequential, and here inside this I'm going to say con 2D, my 32, it's 3 by 3 matrix sizes, activation equal to ReLU. Next I have the input shape. The images that are available is of 32 comma 32 size by 3 layers. So that's what I'm going to set here. Next I'm going to say max pooling 2D. To this I'll say I want to convert that into 2 comma 2. Perfect. Next again I'm going to use convolutional layers 2D, and this time I'm going to say 64 comma 3 by 3. I'm going to use activation equal to ReLU again, and my next layer is max pooling 2D again. For those bits I'm 2 by 2. Once I have this, now I can flatten it, and once I flatten it, now I can use a dense layer, pass it 128, because flatten will give me 128. So that's my input, and I'm going to say activation that I want to use is ReLU, and then I will use dropout 0.5. So I'm going to optimize it to, and then finally my dense layer, which is my output layer, is activation equal to, always use softmax for the output layer. Perfect. Looks good. Everything looks clean. No problems, no errors. Looks good. Now I'm going to go ahead and compile this model. So I'll say model dot compile and pass it optimizer equal to Adam, and loss equal to, as we mentioned, we are going to use categorical underscore cross entropy, and metrics that I am interested in this particular case is, as always, accuracy. So that will compile our model. Now let's go ahead and display the model summary in a nicer table. So I'm going to say model dot summary. That will summarize my model. Perfect. Now that I have the model available, next step is to train the baseline model. So to do that, I am going to create a history parameter variable model dot fit, and to this I'll put all the data. We have xtrain, we have ytrain, next we have the validation underscore split, which is 0.2. Next, the number of epochs that I want to run it for is, let's say, 10. It might take some time. Batch size that I want to specify is equal to, let's increase the batch size from 32 to 64. Verbose equal to 1. So it will take some time to do this training. So next, once the training is done, let's evaluate the baseline model. So I'm going to say loss comma accuracy equal to model dot evaluate and pass it x underscore test, y underscore test, and verbose equal to 0, and that will give me my data. So I can print that out. I'm going to say baseline model test accuracy is accuracy and 0.4 f. Perfect. So that will evaluate and give me my baseline model. Now next, we want to experiment with the hyperparameters. We can experiment with the number of filters and kernel size. We can try to increase the number of filters that we have used to or change the kernel size by 5 by 5. We can adjust the dropout rate from 0.5 to 0.3 or 0.7. we can do learning rate adjustment by using learning rate schedulers or different optimizers like SGD or RMS prop. Let's define an improved model. So I'm going to go ahead, before even running this, I'm going to write the code so we can run everything together. Improved model. So I am going to use that same model that we have here, call it improved model, and done. No, that's just kidding. So here I am going to use 64 3 by 3, sorry, instead of 3 by 3, let's increase this to 5 by 5. Activation equal to value, input shape is 32 32 3, max pooling size 2 comma 2, count td. Now I'll increase this to 128, and here also 5 comma 5, activation value, max pooling 2 by 2, flatten dense, I'm going to increase that to 256, activation equal to value, dropout I'll keep the same, no problem, dense equal to 10, activation softmax. Now once I have this completed, I am going to compile the improved model with a learning rate scheduler. So for that, I am going to create optimizer equal to tf dot keras dot optimizers dot atom, and I am going to give it a learning rate equal to 0.001. I'm going to say improved model dot compile, and to this compile I'll pass the optimizer, which is my optimizer that I've just defined above, loss equal to categorical underscore cross entropy, and then metrics equal to, if you remember what we've used, accuracy before, so I'm going to use accuracy. So if you look at this one and the one that you've done here, before we said optimizer is Adam, but here we're saying Keras, and we are giving a learning rate of 0.001 and defining our and compiling our model. Now that that's done, let's train the improved model. So use the same code, but I am going to call it, improved underscore history model, or improved model dot fit xtrain ytrain validation split 0.2 epochs. Let's increase to 20. Batch size 64, verbose 1. This is going to take a much more time and much more memory, so you'll have to be patient once you run this. And then I'm going to evaluate the improved model. I'm going to say improved underscore loss and improved underscore accuracy equal to improved model dot evaluate what is this, evaluate, okay, and I'll pass it our values, which is x underscore test, y underscore test, and verbose equal to 0, same parameter that we gave earlier. And then now I can go ahead and print the same thing. Where is it? This is baseline model. Now we have improved model test accuracy, and this is improved accuracy, improved accuracy dot 4f. So that's perfect. Now if you want to do one couple of more things, is we can go ahead and visualize the entire training progress. So for that I can import matplotlib dot pyplot as plt. Now this is not required, but it's up to you if you want to do this. Now plot training and validation accuracy. So of course I like graphs, so that's why I'm doing this. And to this, I'm going to pass my improved history dot history, and I can say inside that I like to see the accuracy, and my label here equal to training accuracy. Next, I can do the same thing, plot improved history. I'm going to use val underscore accuracy. That's another parameter in here. And this is my validation accuracy. That's what this is. I'm going to give a title to my plot, and I'll call it accuracy over multiple epochs. And I think we're running it for 20 epochs. plt.x label, I will use x axis to show epochs, and I will show the y label to show my accuracy. Next, I'm going to say show me the legend, and finally I'll say plot.show. Perfect. Now I'm going to do the plot the training and validation loss too. I can do that by, let's copy this here, and this one I'm going to say plot training and validation loss, plot improved history loss. I can say training loss, improved history val underscore loss, and that is my validation loss. And this is loss over epochs, loss, legend, and show. So let's go ahead with everything completed. Let's go ahead and run this. Python, say day 7 ex.py, and it's going to go through each and every step from starting. And I think I have mistyped somewhere TensorFlow. Perfect. Clear it out, run it again. Looks like I have another error here where I have misspelled the shape. It happens all the time. Shape. Let's see if I am doing it since I copy paste. I'll have the error types. Perfect. Let's hope no more errors. Let's run it one more time. Third time is the charm. And there you go. We have the summary, but it gave me an error here saying that model.fit, it says unexpected keyword argument validation split. Okay, looks like again another typo. Validation split equal to 0.2. Let's make sure that I don't have the same. Okay, let's run it one more time. I have one more error, another typo. Accuracy, let's make sure this is only once. Okay, perfect. Clear it out, run it again. Half of the problems usually is my typos, where I have to rerun my code most of the times. Now it's running for my 10 epochs, so I'm going to pause it here and then come back and show you the results. So it took some time, but as you can see here, it went through my first 10 iterations for my model initially, and right over here, it gave me the baseline model test accuracy of 0.6910. Also, it went through the 20 epochs for the improved model that we created, and we got a test accuracy of 0.7110. As you can see, it's improved. And then finally, our plots where it shows our epochs, which are 20 epochs, and the accuracy, as you can see here, it keeps on increasing above and above the training accuracy. The validation accuracy is right here. I'm going to close this, and it will show me the loss of epochs. So if you see over time, the training loss is reducing because it's getting better and better. And same thing for validation loss here. I'm going to close this, and I hope you were able to get the same output as I do. And if you had any questions or errors or issues other than the typos that I've been doing, I think it should be pretty good. But let me know, how does it go? So just to summarize, today we applied concept from previous lessons to tackle a more complex data set. We built and optimized a neural network for image classification. We gained experience in tuning hyperparameters and analyzing the model performance, and we developed skills for experimenting with model architecture and setting to improve the results. And we created the improved model. I hope you were able to follow along. If you have any questions or if you had any issues, let me know in the messages and I'll get back to you. Welcome to week 10, Convolutional Neural Networks or CNNs. Here, on day 1, we'll be looking at Introduction to Convolutional Neural Networks. Day 2, we'll cover convolutional layers and filters. On day 3, we'll be looking at pooling layers and dimensionality reduction. Day 4 will cover building CNN architectures with Keras and TensorFlow. Day 5 we'll be looking at building CNN architectures with PyTorch. Day 6 we'll be looking at regularization and data augmentation for CNNs. And finally, for day 7 we'll be doing our CNN project, which will be an image classification on Fashion MNIST or Cypher 10. So let's get started with week 10. Welcome back to week 10, where our first day we're going to look at Introduction to Convolutional Neural Networks. Let's first dive into overview of CNNs or convolutional neural networks and their role in image processing. Now first, let's cover what are convolutional neural networks or CNNs. CNNs are a specialized type of neural networks designed for processing structured grid data such as images. They are particularly effective for image-related tasks like classification, object detection, and segmentation. Why CNNs for image processing? Spatial hierarchies. CNNs capture spatial and hierarchical patterns in images. Convolutional layers extract features like edges, textures, and complex structures. Also, parameter efficiency. Unlike fully connected networks, CNNs use fewer parameters due to shared weights, reducing computation and memory requirements. Next, let's look at the CNN architecture. Some of the key components of a CNN are convolutional layers. They perform convolutional operations to extract features. Then it has kernel or filter, which is a small matrix, example 3 by 3, that slides over the input images to detect patterns. And then we have the output. The feature maps highlighting specific patterns in the input. Next, we have the pooling layers. They downsample feature maps to reduce dimensions and computation. The types are max pooling, which takes the maximum value in a region, and average pooling, that takes the average value in a region. Fully connected layers. They combine extracted features for final prediction and act as a classifier in the network. The basic CNN workflow is you pass the input image, it goes through the convolution, next activation, then pooling, then fully connected layer, and then you get the output. So some of the key advantages of CNN over the fully connected network for images are: first one is the translation invariance, where CNNs can detect patterns irrespective of their position in the image. Reduced parameters. Shared weights and local connectivity make CNNs computationally efficient. Automatic feature extraction. CNNs learn to identify meaningful patterns like edges, shapes, and textures directly from data. With all this in mind, let's jump into our hands-on exercise where the objective is to visualize images in a dataset, explore their pixel data, and set up an environment for building CNNs using TensorFlow and PyTorch. So first step is to visualize images in a dataset. So I'm going to go ahead and create a new file, not a Jupyter notebook. Try again, Python file. Save this file. In week 10, day 1, I'm going to call it day 1 underscore exercise. First, let's go ahead and, since we are plotting, I'm going to get matplotlib.pyplot as PLT. Since this is our first video of the week, I'm going to go each and every line in detail. So this imports the PyPlot module from Matplotlib, which is used for creating visualizations such as charts and plots, and that's why we are using it. And then next, I'm going to say from Torch Vision, import datasets and transforms. So what I'm doing here is this thing imports datasets and transforms from the Torch Vision library. Datasets provides access to the popular datasets like Cypher10, which we are going to use, or MNIST and others. Transforms contains utilities to pre-process and transform image data, such as converting images to tensors. So now let's go ahead and load our dataset. I'm going to say transform equal to transforms dot to tensor. There you go. So this line here defines a transformation to convert images from the dataset into PyTorch tensors. This is necessary for using the data in PyTorch models. Next, I'm going to say train underscore dataset equal to datasets. This is what we picked up above, but I am going to use Cypher10 root equal to dot slash data. And again, I'm going to explain as soon as I write this. First step is to write this code. Train equal to true, transform equal to transform that I created above, and then download equal to true. So we have seen this before, but I'm going to go over this one more time. This loads the Cypher10 dataset. Now the Cypher10 is called Cypher10 because it kind of classifies all the images into 10 different things from 0 to 9. 0 is for airplane, 1 is for automobile, 2 is for bird, then cat, then deer, dog, frog, horse, ship, and truck. You can Google that thing and you can find the different parts. But here, what I'm doing is I am saying that I want a Cypher10 root dot slash data where specifies the directory where the dataset will be stored. Train equal to true loads the training split of the dataset. Transform equal to transform. This applies the transformation to tensor to the images, and download equal to true says that download the dataset if it's not already present in the specified directory. I don't have this data, so it will download the first time. Next, I'm going to go ahead and visualize sample images. To do that, I'm going to say fig and axis. These are the two variables that get pulled in from plt dot subplots 1, 5, fixed size equal to 12, 3. I know we have worked with some of these things, but what does this all stand? This creates a figure with 1 row and 5 columns of subplots for displaying images. The fixed size defines the size of the figure, which is 12 by 3. So it will be 12 inches wide and 3 inches in height. So that's what we'll get as an output. Now, next I'm going to go ahead and run a for loop for I in range of 5. I'm going to say image, label equal to, I'm going to pick my train data set and get the ith element from these 5 images that I'm getting. Axis of I. So this line, what it does is it loops through the first 5 images in the training data set, and for each image retrieves the image, and which has the image variable has the image data, and the label is the corresponding label to that particular image. So next I'm going to go and say axis I dot im show, and inside that say image dot permute 1, 2, 0. So in this particular line, what I'm saying is I'm displaying the image using imShow. That's a function that shows inside that function. I'm calling the permute method, which reorders the dimensions from channels, height, and width to height, width, and channels. So usually it's 0, 1, 2, but I'm saying 1, 2, 0 because I want to change from. I want to move the channels to the end. Height I'm going to move to the first, and then width I want to move to second. So this kind of moves them around and accordingly gets me my data. Next thing I'm going to do is axis of I dot axis. I'm going to set this to off. So here I am saying that hide the axis for a cleaner display of the image. Don't show the axis in the graph. Next, I'm going to say axis of I dot set underscore title f of label and label. So in this particular case, I'm saying that set the title of each subplot to the label of the image. So that will make sure that it will show us what category does it come into. And then I can say plot dot show. If I run this now, let's go ahead. I'm going to say Python day one underscore exercise.py. First, it's going to download the images. So I'm going to let it download and come back to it once it's ready. It might take a little bit time. But until then, we can go ahead and explore the pixel data. So for that, I need first of all import numpy as np, and then I'll say display pixel values for, let's do it for the first image. Now here I am going to say image comma get me the data image. Oops, there you go, the images are showing up, but I'm going to just complete this first. Image comma label equal to train data set. From that I want the element 0, and then I'm going to say print f of label equal to label, whatever that label is for the first element. I'm going to say print f of image shape equal to image dot shape. Next I'm going to say print pixel values, and then I'll print the image. So what I'm doing here is this displays the pixel values for the first image. Image comma label line number 19 train dataset retrieves the first image and its label from the training dataset. Next, I print the label of the first image. Next, I am printing the shape of the image tensor, typically 3 by 32 by 32 for cipher 10. That's what is used, representing 3 different channels and 32 by 32 pixels. And then finally, I am saying print the pixel values, and I print the tensor representation of the pixel image values here. So let's go and look at the output. Here is our plot where we have 5 different images. The first one looks like a frog, which, as I mentioned, belongs to label 6. So that's the 6th element. Then this looks like a truck and this looks like a truck. So these are both trucks which belong to label 9. That's the last one. And label 4 is, I think it's deer. So that looks like a little bit of deer. I don't know if it's deer or cow, but it's one of them. And then this one is automobile, which is 1. So this looks like it was able to display. Now for the next part that we have here, of course, if I open my folder, I will see that I have this data folder which all the cipher 10 images inside here. It's probably a big file. If you look at just the zip file, is 170 MB. And then I have my day one. This is my code. So I am going to go ahead, clear this, and run it one more time. This time it will not download because I have already downloaded the files. And I'm going to close this. So it shows me the image label 6. This is for the first one, which was, I think, frog. And image shape, this is the image shape. And this is the pixel values. This is how the tensor looks like. And this is the image representation in tensor. Our next step is to set up an environment for building CNNs. So we'll be setting up for both TensorFlow and for PyTorch. So first, let's go ahead and I'm going to clear this out. Make sure you have TensorFlow installed. It doesn't hurt to run Tensor, if I can spell it right, TensorFlow. If you've already installed it, it'll be pretty quick. So I'm going to clear that out. So that kind of has my TensorFlow. Now, if I want to, I can go ahead and comment these things out. I don't need that. And to just to run a basic TensorFlow application, I'm going to say TensorFlow as TF. Next, I am going to say I'm going to define a simple CNN model. To create this model, I am going to say model equal to TensorFlow dot keras dot sequential. I have not imported that yet, so that's why it's not showing up. But this is because I can just have them on, so then it might not give me a warning. Next, I need inside here tf dot keras. So again, let's go over each line. This one imports the TensorFlow library for building and training deep learning models. This one here, what I'm doing is I am defining a simple convolutional network, neural network, a CNN, where first I need to create a layer. So this is a sequential model, which means each layer is run one at a time in sequential order. So first layer is, as I mentioned in CNN, should be con2d 32 comma. So I'm going to give all these parameters and then we can explain over them. 3 by 3 comma activation equal to I'll use ReLU activation, and then I'll say image shape underscore shape equal to 32 by 32 by 3. Next is my next layer. So first layer is con2d, which is a convolutional layer with 32 filters. That's why 32 the number, a 3 by 3 kernel, and a ReLU activation for the image that we have. So that's what is my first layer. That is what I'm defining there. My next layer, tf dot keras dot layers dot max pooling 2d. Now this one I can just pass 2 by 2. So this is a max pooling 2D layer with 2 by 2 pooling window to reduce the spatial dimensions of the previous input. Next, I'm going to flatten. So for that, I can say tf dot keras dot layers dot flatten. This function, it flattens the 2D feature maps into a 1D vector for fully connected layers. So that's, we have that. And then finally, I'm going to call the dense function. For the fully connected layers with 128 neurons, we need to run this 128 comma. So dense goes by, again, since I've not done the import of layers, I have to write the entire thing here. tf dot keras dot layer dense, and this is a fully connected layers with 128 neurons. A ReLU activation equal to ReLU. This is that layer. Okay, let's make sure this comma, extra comma is removed. And then finally I would make another dense layer. So I'm going to copy this, and in this one I am going to say I need one with 10 neurons, which is for the 10 different classification units we have in Cypher 10, and I am going to use softmax this time activation for classification in this particular case. So I have my model created. Once I have my model ready, next thing is to compile the model. Now to compile the model, I'll run model dot compile function, and I'm going to use optimizer equal to Adam. I will say loss equal to sparse underscore categorical underscore cross entropy, and then I need metrics equal to, I'll set that to, can use multiple ones, but I'm going to just use accuracy for this one. So this is your model.compile function. What this does is this again compiles the model, but the configurations configures the model with optimizer of Adam, which uses the Adam optimizer for training. loss equal to sparse categorical cross entropy, specifies the loss function for the multi-class classification, and matrix is equal to accuracy, tracks accuracy during the training. So that's what this does. Now I can go ahead and say after this that my TensorFlow CNN model is ready. Let's go ahead and run this. Oops, not Python day one. It's going to just jump directly to that, and looks like con2D image shape. Did I spell it wrong? It's input shape. That's why. Clear. Run it again. And it says TensorFlow CNN model is ready. It says that when using sequential model, prefer using input shape object as the first layer in the model instead. So instead of passing is to the con2D, it says use input layer, but this is fine too. Just a warning. Next, I'm going to go ahead and show you how to do this for PyTorch. For PyTorch, make sure that you have Torch and Torch Vision installed. So I'm going to run this pip install again. Pip install Torch and Torch Vision. So I have already installed that, so it should be there. So I don't have to worry about them. Next, I'm going to go ahead here and write the code for first. I'm going to import torch.nn as nn. Now this will import the nn module from PyTorch, which provides tools for building neural networks. So once that is done, let's go ahead and define a simple CNN model. To do that, I'm going to start with class simple CNN and pass it nn.module. Now I'm going to go over each and every line as I mentioned, because we'll be repeating this quite a lot, so I don't want to repeat this again and again. So pay close attention. So this code here defines a simple CNN model. I'm creating a class here which will define my module. And first thing, I'll go ahead and initialize this and write the initializer for this particular class. I'll pass the self object. This is the basic definition of initializer, where first I'm going to call the super class with the same simple CNN and pass self to it and say dot underscore underscore init, call that function. So first call the super. Next is I'm going to say self dot convolutional first layer equal to nn dot conv 2D. This is same as what we did for TensorFlow, but in PyTorch we're going to get it from nn. So nn dot conv 2D 3 comma 32 comma kernel size equal to 3 comma activation equal to value. Now this is more featured for our Python coding, so that's why it's made much more simpler, where what's happening is we're creating a convolutional layer with 3 input channels, 32 filters and a 3x3 kernel. So it's pretty straightforward as compared to what we did. We kind of had to spell everything out in TensorFlow, but in PyTorch it's much more easier. Next I'm going to say self dot pool equal to nn dot max pool 2D, and I'll pass 2 comma 2. Again, same as what we did with TensorFlow. We created a max pooling layer with a 2x2 pooling window. Next I'm going to say self dot fc1. This is nn dot linear, and I'm going to pass here 32 times 15 times 15 comma 128. So here we are creating a fully connected layer, transforming it from 32 times 15 times 15 into 128. And again, I'm going to use one more fully connected layer and call it fc2 equal to nn dot linear 128 comma 10. So what it does is now it's converting the input size to the output size. We're transforming 128 neurons and 10 classes. That's what's happening here. So that kind of takes us to the next point, which is creating the forward function self comma x. Now this defines the forward pass, where we'll have to first say x equal to f dot ReLU self dot conv1 of x. So this applies convolution con1 and ReLU activation. Next, I need to apply the max pooling, which is x equal to self dot pool of x. Next, I have to flatten the tensor using x dot view. So I'm going to say x equal to x dot view and pass it -1 comma 32 times same number as before, 32 times 15 times 15. So this will flatten the tensor. Next, I am going to call x equal to f dot ReLU self dot fc1 of x. So here I'm passing the data through fully connected layers of fc1, and next I'm going to do the same thing for fc2, where I'm going to say self dot fc2 of x. So these last two lines passes the data through fully connected layers of fc1 comma fc2. So next thing is I have to mention, I'll say print PyTorch CNN model is ready. Let's see if it gives me an error. I'm going to run this. And as you see here, first it says TensorFlow CNN model is ready because I've not commented that. And then it says PyTorch CNN model is ready. So that's what we were expecting. So in this particular exercise, we did the visualization where we understand the structure and labels of the Cypher 10 dataset. Then we did pixel exploration, where we gain insights into the numerical representation of the image. We displayed the image sizes and things here, right here. And then we did the environment setup for both TensorFlow and PyTorch for CNN development, which we'll be using quite a lot in the next few days. So stay tuned. So just to go over some of the outcomes from today, we understood the basic architecture and components of CNNs. We learned why CNNs are superior to fully connected networks for image data, and we gained hands-on experience visualizing and exploring image datasets. And we developed some foundational skills for building CNNs in both TensorFlow and PyTorch. So if you have any questions or had any issues or errors, let me know in the messages and I'll get back to you. Welcome to day 2, convolutional layers and filters. Today, we're going to jump into understanding convolutional operations, filters, and feature maps. So what is convolutional operation? A convolution is a mathematical operation where a small matrix, which is a kernel or a filter, slides over the input image to extract features like edges, textures, or patterns. Some of the key concepts include, we have the kernel or the filter, which is a small matrix, example 3 by 3, used to extract features. Here, each element of the kernel is a weight learned during training. Next, we have feature map, the output of a convolutional operation, which highlights the specific patterns detected by the filter. Then we have channels. For RGB images, convolution processes each color channel separately and combines the results. Let's go over some of the concepts of kernel size, stride, and padding. So as per kernel size goes, the dimension of the filter example can be 3 by 3 or 5 by 5. Smaller kernels capture finer details, whereas larger kernels detect broader features. We have stride, which defines the step size of the filter as it slides across the input. Larger strides reduces the feature map size, improving computation efficiency, whereas smaller strides retain more detail but increase the computation, as you can make sense. Padding adds extra pixels around the input to control the size of the output. A valid padding is no padding, the feature map shrinks. Same padding adds enough padding to keep the output size equal to the input size. Next, let's talk about visualizing how convolution extracts features by edge detection. Kernels like Sobel or Privet highlight edges in images. Feature extraction. Initial layers focus on edges, deeper layers capture abstract patterns in this particular case. So with this in mind, let's jump into our hands-on exercise where our objective is to understand convolution operations by implementing and visualizing their effects using TensorFlow and PyTorch. So first, let's go ahead and start with a new file, save it as day2_ex. Now first let's go ahead and first we have to visualize the effects of convolution on an image. So I'm going to go ahead and import matplotlib as .pyplot as plt. Then I'm going to import numpy as np, and then from skipy dot nd image I am going to import convolve. That's what I need. So these three libraries, let's talk about them. So the matplotlib pyplot as plot imports the matplotlib.pyplot library, which is used for creating visualizations like plots and images. NumPy imports the NumPy library, which is essential for numerical computations and handling arrays. That's what we'll be doing. And the last line from skipy.endImage import convolve imports the convolve from function from the skipy library to perform convolution operations on images. So now let's go ahead. Our next step is to load a sample grayscale image. Now to do that, I can just say image equal to np.random.rand 10,10. So this, what does this do? This, I mean, you can replace this with your tensor image if you have one, but this line generates a 10 by 10 random grayscale image, values between 0 and 1 to simulate an example of an image. So I'm going to go ahead and print this image. Let's look at how it looks like. I'm going to go ahead, open this and say Python day2ex. And there you go. That's our image from 0 to 1. It had created an image for us with it's a grayscale image. I mean, I can't see it, but we can print that image using matplotlib. So what we're going to do next is we are going to visualize the effects of convolution on an image. So I have matplotlib.pyplot as plt. I have numpy. I have skipy import convolve. I already created an image. I'm going to comment this line out, and next I am going to say define convolution kernels. Now these are the filters that I was talking about. So what we are going to do here is we're going to create an edge detection kernel. So edge detection kernel by using np.array, and inside this again I'm going to go over this line by line. So first I need -1, -1, -1. Next I am gonna create another something similar. So I am going to copy this, paste it 3 by 3. So -1, I'm gonna set this as 8, -1, -1, -1. So this edge detection kernel is a 3 by 3 kernel filter used for detecting edges in the image by emphasizing high contrast area. So as you can see here, since I've selected -1, you can probably see how it automatically shows you that it is an edge detection kernel. Next, I'm going to create a blur kernel, blur_kernel equal to np.array, again something similar, 1, 1, 1, 1, 1, 1, too many commas, and third one 1, 1, 1. Pretty straightforward, right? So this is my blur kernel. Again, I'll have to divide by 9 for this is normalizing for our averaging. So this is a 3 by 3 kernel used for blurring the image by averaging the pixel values in a neighborhood. That's why it's /9. It normalizes the kernel so that the sum of all the elements equals 1, ensuring the brightness remains consistent. So that's how you create a blur kernel. Next, Let's go ahead and apply convolution. Move it up. I'm going to say apply convolution. Now first I'm going to say edge detected underscore image equal to convolve. I will use that function that we've imported, and inside that I'll pass the image and I'll pass the edge detection kernel. Same thing I'm going to do for blurred image. I'm going to say convolve and I'll pass the image and the blur kernel. So in this line, what we are doing is this line kind of applies the convolve image kernel, applies the convolution operation on the image using the specified kernel. So first we are doing the edge detection image. So that kind of contains the result of an edge detection, and blurred image contains the result of the blur image. So once we have that, next thing I'm going to go ahead and visualize the original and filtered image. So let's display how they look like. So for that I'm going to use again fig axis equal to plot dot sub plots. If you remember this from the yesterday's video, we kind of created something like this where I specified finally the fig size equal to 12 comma 4. If you don't remember, this what it does is the plot dot subplot creates a figure with 1 row and 3 columns for side-by-side visualization of the images. And the fixed size 12 by 12,4 sets the size of the figure to 12 inches wide and 4 inches tall. Next, I am going to create my axis of 0 dot IMShow, pass the image, and CMap equal to grayscale. So this one along with the next one, let's create the second one and then I'll explain, go over it. Dot set underscore title. This is my original image. So now probably you got some idea. What this does is this displays the original image on the first subplot with the grayscale color map. So it takes the image and shows it in the first axis over there. Next, in my second axis, so in my second image that I'm going to show is IMShow edge detected image CMap. I'm going to use the same code, so why not? The only difference is this will change to 1 set. This will edge detected. Next, you know what I'm going to do. This is for the next image where IMShow the blurred image CMap equal to gray, set title equal to blurred, and then I'll say plt dot show. Now if you have not already figured out what I'm doing here, on my line number 31 and 32 I am displaying the edge detected image on the second subplot. That's why axis of 1, and on 33 and 34 I'm displaying the blurred image on the third subplot and show the final entire image here on the plot. So I'm going to go to my terminal, clear it out, run it again, and as you can see, this was the initial image that was created. This is the edge detected image, which is much similar, but if you see, there are some pixels which are a little different color because it detected an edge around there and smoothened that. And then this is my blurred image. Based on this image, it blurred it to make sure that it looks blurred consistent. So this is how you can actually take an image and then detect edges on them and also blur the images using this code. Our next step is to implement convolution in TensorFlow. So let's go ahead and I'm going to keep this code at the bottom. I'll say import TensorFlow as TF, and then I am going to create a sample input tensor and pass batch size and height, width, and the channels here. So to do that, I'm going to say image underscore tensor equal to TF dot random dot normal and pass it all the parameters 1 comma 10 comma 10 comma 1. So this is a random 10 by 10 grayscale image. So this tf dot random normal creates a random 10 by 10 grayscale, 10 by 10 because I specified grayscale image tensor with a batch size of 1 and the channel of 1. So that's what I'm doing here. Next, let's go ahead and define a convolutional layer. To do that, I'm going to say conv of conv layer equal to tf dot keras dot layers dot conv 2D. So that will create my convolution 2D. Here I am going to set my filters equal to 1. I will set my kernel size equal to 3 by 3. Always make sure that you don't add spaces here. 3 by 3. Next, this is my kernel size. Next, strides equal to 1 comma 1. Next, I have padding. These are the different parameters that we spoke about during the actual the presentation. This is my padding type is same. So what I'm doing here is I'm calling this conv2D, which defines a 2D convolutional layer in TensorFlow. I'm passing filters equal to 1, which specifies the number of output channels or filters. Kernel size is 3 by 3, which defines the size of the convolutional kernel. And strides 1 by 1 specifies the step size of the convolution. And when I say padding equal to same, I'm ensuring the output size matches the input size by padding the borders. Now, if I want to get the output tensor, so this is where I'm applying the convolution. So tensor equal to conv underscore layer. So this is my conv layer, and I'm passing the image tensor that I've created here. So what this does is this applies the convolution layer to the image tensor. Now let's go ahead and print. First, I want to print the original shape of how it looks like. Image tensor dot shape, and then I am going to say output shape. That will be the output tensor dot shape. So that's how we do it and how to implement it in TensorFlow. Now I can also, let's go ahead and I'm going to remove this plot and just run this. Looks like I have a typo here. Yes, kernel size. There you go. Did I save it? I'll run it again. And there you go. We have the original shape 1, 10, 1, and output shape is exactly same 1, 10, 1. Just the contents might have shaped because we have added the convolutional layer on top of it. Now let's go ahead and implement convolution in a PyTorch. Now if you want to display the image, you can always use this similar code and plot that image out, original image and the actual image, original image and the output image. Now for PyTorch, I'm going to say import torch. Next, I want to import torch.nn as nn because that's the torch's main library. And then first I'll create a sample input tensor with my same batch size, something similar that we did with TensorFlow channels, height and width. This is the format in which you specify. So I'm going to say image underscore tensor equal to torch, image underscore tensor equal to torch dot randn 1 comma 1 comma 10 comma 10. Again, you have to follow the same order. Batch size, channels go first, height and width go next, as compared to in TensorFlow it's batch size, height, width and channels. Next, now that I have my image, let's go ahead and define a convolutional layer. Again, I'm gonna not go over everything because it's almost same. Conv layer equal to nn dot conv 2d, and this 2d needs parameters, which is in channels, how many input channels are there, 1, how many output channels are there, I want the same number of channels. Next I need to give the kernel size. Kernel size I've used 3 by 3, so here we just specify 3, and then stride is 1 by 1 as you just specify 1, and padding equal to same is 1. So there you go, we have the entire function written here. Conv2d, there's some error, yes, comma, perfect. So now my convolution layer is, now we go ahead and apply the convolution. It's almost similar where you say output tensor equal to conv underscore layer and pass it the image tensor. Again, I think I've used the same naming, so I'm going to call it image tensor underscore pytorch pt, torch dot random con underscore pt, and output tensor pt, conv layer pt, tensor pt. So everything I'm adding pt to it just so that it makes it simple to remember. F, I'm going to say original shape is image tensor pt dot shape, and output shape is output tensor pt dot shape. Go back, clear it out, run it again. So first one was TensorFlow, the second one is PyTorch. If you see, input and outputs are same. If you just want to display these images, that's where you'll probably see a better display, but I would not go into details of those because it's almost same as what we did earlier. But what we can do is we can experiment with different kernel sizes, strides, and padding. So do that. Let me show you one example in TensorFlow example where my convolution layer underscore large kernel equal to tf dot kernel dot layers dot conv 2d. Just make sure you don't do typos. Filters equal to 1. I will say kernel underscore size equal to, so I'm increasing from 3 by 3 to 5 by 5 in this case. Strides, I'm going to use this same, strides equal to 1 comma 1. Next is padding, I'll keep it same as input. So this is what we have specified earlier. Okay, now next step is, let's say output large underscore kernel equal to conv layer large kernel and pass it the image tensor, and I can print this out. Print f of large kernel output shape is output large kernel dot shape. Next, if I want to do the same thing for PyTorch, since I'm doing it in TensorFlow, why not also do it for PyTorch? Here's an example. I'm going to say conv underscore layer underscore stride underscore 2 equal to nn. I think the name gave away what I'm trying to do here. Dot conv 2d, and here, oops, not, it's conv 2d. You have to remember there are different functions in TensorFlow versus in PyTorch. In channels equal to 1, out channels equal to 1, kernel size equal to, I'm going to keep the kernel size same in this one, but as you saw from the name, I'm going to change the stride equal to 2, and I'm going to keep the padding equal to 1. Now you can, as I mentioned, you can try different combinations. Next I'm going to do is let's say output underscore stride underscore 2 equal to conv underscore layer stride 2, pass the image tensor pt, That's the PyTorch one. And then I'm going to say print f of stride output shape is output stride 2 dot shape. Perfect. So I have that. Let's go ahead and run this. Clear this out. I could have kept it so you can compare side by side. Oh, I think it was Keras. I've used kernel. Yep, Keras, and that's why we got that error. I hope that was the only error. Let's clear it out. Run it again. Output shape, input now original shape for torch size, torch, and then here is my large kernel, and with that the data that I'm getting out. Stride output, I'm getting half the value of the input because it strides twice the amount, so it skips one, so that's why it's smaller output shape. So I hope you were able to follow along and get this working. Now, just to summarize, we understood the role of convolutional operations, filters, and features maps in CNNs. We learned the effect of kernel size, stride, and padding on image processing. We gained some hands-on experience with TensorFlow and PyTorch for implementing these convolutional layers and developed intuition for choosing hyperparameters for convolutional operations. I hope you were able to follow along. If you had any problems or if you have any questions, do let me know in the messages and I'll get back to you. Day 3, pooling layers and dimensionality reduction. Today, let's look at in depth both of these features. First, let's start with introduction to pooling layers. Now, what are pooling layers? Pooling layers are used to reduce the dimensions of feature maps while retaining the most important information. They help make the network computationally efficient and robust to variations in the input. Now let's look at the different types of pooling. We have max pooling, which we already used. This selects the maximum value for each region of the input feature map, and it captures the strongest activations, which are the features. Then we have the average pooling, which computes the average value for each region of the input feature map and provides a more generalized summary of features. What is the role of pooling in reducing dimensionality? Now, in dimensionality reduction, pooling reduces the spatial dimensions, height, and width of feature maps, resulting in fewer parameters and faster computations. As per robustness, it makes the model invariant to small translations or distortions in the input image. Let's talk about combining convolution and pooling layers. Pooling layers typically follow convolutional layers to downsample the feature maps. This combination helps extract hierarchical features. Early layers focus on simple features, example edges, and deeper layer capture complex patterns, example objects. Now, with this in mind, let's go ahead and jump into our hands-on exercise where the objective is to implement max pooling and average pooling layers on feature maps and observe their effects on size and representation. And just FYI, we are going to use colorful images this time. So first, let's go ahead, create a new file, save it as day3 underscore ex.py. And here, we'll start with importing our libraries. Our first library that we're going to import is import numpy as np, which is importing the numpy library for array manipulations. Next, import matplotlib.pyplot as plt. This is again, matplotlib is for visualizing the feature maps. Next, from skipy.ndimage, I am going to import maximum underscore filter and uniform underscore filter. So here we are importing maximum filter for max pooling and uniform filter for average pooling from the skipy library. Next, let's go ahead and create a sample feature map. I'm going to say feature underscore map equal to np dot array, and I'm going to make a random array here manually, of course, without using the random function. So 1, 2, 3, 0. Next, I'll use 4, 5, 6, 1. Next, I will use 7, 8, 9, 2. Just when you know that you can guess what I'm typing next, I change 0, 1, 2, 3. There you go. Now, this feature map that I've created, it defines a 2D array feature map as a sample feature set. It's 4 by 4 here. That's what I've used here. Now, next, let's go ahead and create our max pooling, which is 2 by 2, 2x2. Let's say max underscore pooled equal to, I'm going to use my maximum filter that I've downloaded or imported. Feature map is what I'm going to pass it. Size equal to 2 and mode equal to constant. Here I'm performing max pooling with a 2 by 2 kernel size, and each region in the feature map is replaced with its maximum value. So that's what happens here, and I'm going to use next one, which is our average pooling, which is also, I'm going to do it 2 by 2. So for that, the code goes avg underscore pooled, that is my variable name, and I'm going to use my uniform filter, pass it the feature map. I'm going to pass the size, as I mentioned, is 2 by 2. So specify that 2 and mode equal to constant. So here is where I perform average pooling with a 2 by 2 kernel size, and each region is replaced with the average of its values. So now that is done, let's go ahead and plot this out. Plot. Again, I'm not going to go over this because we, I think, went a couple of days with the explanation of this. I'm going to directly go and subplot or plot my subplots, which are my images 1, 3, fig size. This is the dimensions width. I'm going to have 3 images in one row, and then my figure size is 12, 4. That's all I'm going to tell you now, because I think you know what I'm working on. Now, for each and every images, axis of 0, I am going to say I am show the feature map, and cmap equal to, I will use viridis, viridis for this particular case, axis of 0. I am going to set the title, as this is my original feature map. Now I'm going to copy these for my second image and my third image and say 1 and 1 and 2 and 2. I am sure this one should be the max pooled, and this one should be the average pooled, and I'll keep everything else except for this one, is called max pooled, and this one is called average pooled. Perfect. So I have that, and then I will say just show this figure. That's it. Can go ahead and run it. I can say python day3 underscore ex.py. Looks like I have said subplot, but it's actually subplots. So sometimes you should use help from the autocomplete. This is axis 3. Did I? Oh, yeah. Again, one more typo. Run it again. And there you go. We have our 3 images, which is the original feature map that we created based on the numbers. You can probably see 1, 2. So that's why the reason we have colored is because we have used the viridis, and that makes it colorful. Max pooled, and this is average pooled. We have 3 different images based on max pooled and average pooled. So perfect. Our next step is to implement the pooling layers in TensorFlow. So how would we do this in TensorFlow? I'm going to comment this out, and in TensorFlow first I need to import TensorFlow. I've been doing some typos, so I need to be extra careful, so I'm going to go a little bit slow and import TensorFlow STF. First step, I'm going to say create a sample input tensor, which is 1 by 4 by 4 by, even in my comments. I don't want to do any typos. This is for batch size. As you know, in TensorFlow we have batch size, then we have height, then we have width, and then finally the channels. So to display this, I am going to say input underscore tensor equal to tf dot constant and pass it feature map dot reshape and pass it those values 1 by 4 by 4 by 1 for batch size, for height, width, and channels. And then I'm going to say dtype equal to tf dot float 32 because that's what TensorFlow wants. Again, what I've done here is I've converted the feature map into a 4D tensor with dimensions of batch size, height, width, and channels. Now I am going to do the max pooling on this, max pooling on that by creating a variable first, max pool equal to tf dot keras. I have to be careful what I type here. Dot layers dot max pooling 2D. Perfect. And here I'm going to give a, okay, I don't think it knows my pool size. Pool size equal to 2 by 2. That's what I'll specify. Next, I need to give stride, as you remember from the previous days. Strides again, 2. And then padding equal to, I'll say valid padding. Perfect. So that's my max pool variable. Now I need to get my maxed pooled tensor. To do that, I'm going to say max underscore pool and pass it the input tensor. So first, as on line number 36, we are defining a 2 by 2 max pooling layer with strides of 2. Then we are saying max pool tensor where we apply the pooling to the input tensor that we have. Now next, do the same thing for average pooling. For that, I'm going to say avg underscore pool equal to tf dot keras dot layer dot average pooling 2D. In this case, I'm going to specify the same values. Pool size equal to 2 by 2, strides equal to 2, and padding equal to valid. And then I'll say average pooled tensor equal to max underscore pool and pass the input tensor to that. So there you go. Oh, sorry, not max. Average underscore pool and pass the input tensor to that. So here what we are doing is we defined a 2 by 2 average pooling layer with strides of 2, and then we applied the average pooling to the input tensor. Now let's go ahead and print these out to see how it looks like. Say f of max pooled tensor equal to, I'll move it to next line, and inside there I'll say tf dot squeeze, call the squeeze function, and pass it the max pooled tensor dot numpy. There you go. That will give me my max pooled tensor. For my average pooled tensor, I'm going to say tf dot squeezed average pooled tensor dot numpy. Perfect. So that will give me my average pooled tensor. Now if I want to do this similar thing in PyTorch, again I'm going to do this and then we can see both the results. Torch, I'm going to go ahead and say print /n /n /n. So this is the difference. Torch, and then import torch dot nn as nn. Next I am going to create a sample input tensor. Again, this we need batch size. Next we need channels, which will say 1 by 1, and then height is 4 and width is again 4. So this is the pattern for PyTorch. So you have to remember this. That's why I kind of keep on repeating these things. Input tensor equal to torch of tensor. Now here I need to give the feature map first. So I'm going to give feature map. Next time I need to give d type equal to torch format dot float of 32. Next I'm going to say dot unsqueeze. There you go, unsqueeze function, and that is 0 dot unsqueeze again of 0. So that's my input tensor. What I'm doing here is we are converting the feature map to a 4D tensor with dimensions of batch size, channels, height, and width, and then we have to unsqueeze it twice here. So next thing that I want to do is max pooling. Now for max pooling, I'm going to say max underscore pool equal to nn dot max pool, and I need 2D. So for that, and then I'll give the kernel size of 2 by 2. Strides, I will give of 2. Here it's stride, not strides. So just be careful. Here is strides and here is strides. So that's why it sometimes gets confusing. Max underscore pooled underscore tensor equal to max underscore pool, and I'll pass the input tensor to it. Next, I'm going to do average pooling. For that, I'll say avg underscore pool. Now it's self-explanatory. I don't have to go over these lines. It's similar to what we did for TensorFlow. Kernel size equal to 2 and stride equal to 2. Now I'm going to say average underscore pool. So I use this PyTorch quite a lot. That's why it's much more faster for me to type these. Average underscore pool, and also Visual Studio kind of helps a little bit. Input tensor is what I pass. Now I need to pass, I need to print these things out. Let's say max pooled tensor here is not TF, but I'll get rid of all these. In here it's max underscore pooled tensor dot squeeze. Why doesn't it auto complete? Max pooled tensor, that's the name, okay, squeeze dot numpy. Okay, if it doesn't want to, that's fine. And for my average, I am going to say average pooled tensor dot squeeze dot numpy. So this looks fine, no typos, I hope. And let's go ahead and see if this displays properly. Close this out from before, clear this out, and run it again. And there you go. We have the max pool tensor using TensorFlow, our max pool tensor and average pool tensor. And then we have using PyTorch our max pool tensor, almost same, and the average pool tensor, exactly same, but the frameworks that we use are different. Now, if you want to combine the convolution and pooling layers, let's look at an example using TensorFlow for that. I'm just going to do it for both TensorFlow and PyTorch. So let's start with TensorFlow example. Example where first I'm going to create model underscore TF equal to TF dot keras dot sequential, and in here let's go ahead and give the different layers. Again, it will give me a warning here, so I'll probably try to show you how you can change this because we have used it a couple of times before and I don't like to see warnings. 2D, I pass 32, my 3 by 3 kernel, my activation equal to ReLU, my input shape. Now again, here instead of giving the input shape in this particular line, usually what we used to do was we would say input underscore shape equal to 32 by 32 by 3, and that would be my first layer. But what I'm going to do in this particular case is here my first item I'll say tf dot keras dot input layer in this case, and for that I will say shape equal to 32 by 32 by 3. So when I do this, I don't have to do this here. It becomes pretty straightforward and it doesn't give me a warning or error because of this. Again, not done it right. Okay, now it's right. So give the shape first, so input shape first, and then you add your convolutional layer on top of that. Next is all the same. So I'm going to say tf dot keras dot layers, and this time I'm going to use a layer of max pooling 2D, and that I will say it's 2 by 2. Next I'm going to say tf dot keras dot layers dot conv 2D, again add a convolution conv, make sure that no typos, 64 this time, and 3 by 3, my kernel size and activation equal to again relu. Now for the final layer I'm going to say tf dot keras dot layers dot average pooling 2D. This time I'll set 2 comma 2 same. So that's my entire model tf. Now if I want to do this in PyTorch, the way to do it is PyTorch example, create class simple CNN, and inside that I'm going to pass the torch dot nn dot module. Oops. And inside my class I'll define the initializer method, which is self, and here I will first call the super, same as before where you call the simple CNN and then self, and then call the initializer method of the super underscore underscore. Perfect. Next you say, oops, see typos. Next I will say self dot conv 1 equal to, in this particular case I'll say nn dot conv, I'll use the 2D, same as what we do in TensorFlow. I want to do exactly same, 3 by 3, 32 channels kernel size equal to kernel size equal to 3. So that's 3 by 3. So that's there. Self dot, next I'm going to use the pool 1 equal to, in this particular case, nn dot max pool 2D 2 comma 2, make sure the same as what we have above. Next I want to created a convolutional 2, which is nn dot conv 2D, and inside this I'll pass 32 comma 64 comma kernel size equal to 3. Next I'll use self dot pool 2 this time, nn dot, this time is my average pool, so average pool 2D 2 comma 2. Perfect. So that's my initializer method. Now my forward class, forward function is self comma x is the inputs that it take, x equal to torch dot relu first is what I'm going to use, and say self dot conv 1 of x, again same as what we did here. Next I'm going to say x equal to self dot pool 1 of x, so I'm going to apply the pool 1. Next I am going to say torch dot relu, and then pass self dot conv 2 that we created x, so that's the next one. And then finally the average pooling, so I'm going to say x equal to self dot pool 2 or 2x, and then that's where we return the x. Again, if you run this, it should not give you any errors, but just to be on the safer side, I want to make sure that there's no typos or errors. And first pool, second, and then no errors. Or usually what happens is, as I mentioned earlier, whatever we were doing input shape equal to here, When we put it there, it gives you that warning, but this is the best practice that you should follow. Give the input shape first, then call contour2D. But having that here doesn't cause any harm, it's just better practice. So just to recap, today we learned the purpose and functionality of pooling layers in CNNs. We understood the trade-offs between max pooling and average pooling. We developed some practical skills for implementing pooling layers in TensorFlow and PyTorch, and we gained an intuition for how pooling reduces computation and enhances feature extraction. If you had any issues or problems while implementing this or have any questions, let me know in the messages and I'll get back to you. Day 4, Building CNN Architecture with Keras and TensorFlow. Today, we're going to jump into building a CNN architecture in Keras. Now, steps to build a CNN includes first building a convolutional layers which extract features from the input images. Next, pooling layers where we downsample feature maps to reduce dimensions and retain key features. Next, dense, which is fully connected layers, combine features for final predictions. Now the basic CNN architecture here is the input layer goes to the convolutional layer, goes to the activation, goes to pooling, then fully connected layer, and you get the output layer. Repeat the convolution and pooling layers for deeper networks. Next, let's talk about compiling, training, and evaluating a CNN. Now the steps involved here is first you compile the model where you define loss, optimizer, and metrics. Next, example loss functions include categorical cross entropy, which is for multi-class classification, and example optimizers are ADAM, which is efficient optimization for large networks, and example metrics can be accuracy. Now, next step is to train the model, where we call model.fit with training data, validation data, epochs, and batch size. And finally, we evaluate the model, where we use model.evaluate with test data to calculate the metrics. Next, let's go over introduction to popular CNN architectures. We have LeeNet, one of the earliest CNNs for handwritten digit classifications. Example is MNIST. We have AlexNet, which revolutionized deep learning for image classification in 2012. It was introduced ReLU activation and dropout for regularization. Then we have VGG, which uses deep networks with small filters, mostly 3 by 3, and it's known for its simplicity and effectiveness. Now, with all this information, let's get on with our hands-on exercise where the objective is to build, train, and evaluate a CNN for image classification on the MNIST or Cipher-10 dataset using Keras and TensorFlow. So for this example, let's start with Cipher-10. So first step, let's go ahead and create a new file, save it as day4_ex.py file. Now here, I'm going to first import all my libraries and go for tensorflow.keras.datasets import Cipher-10. Now this imports the Cipher-10 dataset, which consists of 60,000 32 by 32 color images in 10 classes, where we'll be dividing it 50,000 for training and 10,000 for testing samples. Next, we're gonna import from TensorFlow, I think I got the spelling right, .keras.utils. I am importing to categorical. So this imports a utility to convert integer labels to one hot encoded labels. Next, I am going to import TensorFlow itself as TF. Perfect. So I have all my imports ready here. Our next step is to load Cipher-10 dataset. To do that, I'm going to say x_train, y_train, and x_test, y_test equal to Cipher-10 dot load underscore data. So I have my data loaded here. So this loads the data set and splits it into training, which is xtrain and ytrain, and testing into xtest, ytest sets. Xtrain and xtest uh, contain image data, while ytrain and ytest contain the corresponding labels for those images. Next step is to normalize the data. Here I'm going to take the xtrain data first, and I will run a function called as type float 32 divide by 255.0. This converts the image data to a 32-bit floating point number for compatibility with TensorFlow models, and when I divide it by 255.0, it normalizes the pixel values from 0 to 255 to 0 to 1 to improve model convergence during the training process. So I'm going to do that same thing for x underscore test equal to x underscore test as type float 32 divide by 255.0. So now once the data is normalized, let's go ahead and do one hot encode the labels. Like to put this in here. Perfect. So for ytrain, I'm going to say 2 underscore categorical and pass it y underscore train and 10 different categories. So I'm going to do that. I'm going to go back here and do the same thing with y test. So this again converts the integer labels which we have as 0 to 9 to one hot encoding format. For example, label for 3 will become 001 0000 because it will kind of label the third element in the list as 1. And same thing for the rest of them. So now let's go ahead and print the dataset shapes. So I'm going to go ahead and say print training data shape x underscore train dot shape, and then I'll say label shapes y underscore train dot shape. Same thing I'll do for test data shape x test y test. Save it and then run it once. I'm going to say python day4 ex.py. I'll run it. It might take some time to get the cipher data. And here we go. We have 50,000, 32, 32, 3, and label shapes are 50,000 by 10. And same thing for test data. We have 10,000 instead of 50,000 because 20% of the data, and label shapes is 10,000 by 10. So perfect. So we have our data ready. Now let's go ahead and build a CNN architecture. So for that, first I'm going to go into TensorFlow dot keras dot models. I will import something that you're familiar with, sequential. Next I'm going to go to TensorFlow dot keras dot layers and import all the different layers that I need. Convolution 2D, so I don't have to write the full length, only the name is function is good enough. Max pooling 2D, I need flatten, I need dense, and the last one is dropout. Perfect. So I have all my functions available and ready. So next step, once we have everything, now I'm going to go ahead and build the CNN model. Now I'm going to say model equal to sequential, and here pass the parameters conv conv 2D, and then I'll pass 32 comma 3 comma 3. Now 32 are the 32 filters of size 3 by 3, and then I need activation equal to ReLU, and my input shape equal to 32 comma 32 comma 3. Next layer is max pooling 2D, where I'm going to say 2 comma 2. So the first line adds a convolution layer with 32 layers of size, 32 filters of size 3 by C. It adds ReLU activation and input shape of 32 by 32 by 3, which is the image size and RGB channels. Next, max pooling 2D 22 adds a 2 by 2 max pooling layer to reduce the spatial dimensions. Our next one is again conv 2D, and this time I'm going to say 64 comma 64 filters 3 by 3 and activation equal to ReLU. Our next layer after this is again max pooling 2D with 2 comma 2. Our next after that is to flatten it. This flattens the 2D features map into a 1D array for fully connected layers. Now once that is ready, so I can just say use dense 128 comma activation equal to ReLU. This creates that fully connected layer with 128 units and ReLU activation. And I'll use dropout next. Drop out. This adds dropout regularization. I'm going to say with 50% dropout rate to prevent the overfitting part. And finally, I'm going to create the output layer with 10 units, one for each class, and softmax activation for classification that can be done using dense. You can say 10 comma activation equal to softmax. Perfect. So let's look at it. It all looks good. Perfect. Now let's go ahead and as usual display the model summary. So I can just say model summary. This will display my model architecture of how it looks like, of what all different table it has. Next thing that I want to do is compile the model. Now to compile the model, I'm going to call model.compile and pass it optimizer of Adam. I will give the loss as a categorical underscore cross entropy, and then metrics that I'm interested in is equal to accuracy. So that's good. That will compile. Next step is to train the model. So I'm going to go here and say train the model. Now in training process, all I have to do is like create a history equal to model dot fit, and inside this I'll pass x underscore train, I'll pass y underscore train, I will say how many epochs I want, epochs equal to 10, I will give a batch size of 64, and then I'll say validation underscore split equal to 0.2. So they should work perfectly. Next step is to evaluate the model. So I will say evaluate the test data set. For this, I can say evaluate on the test data set, not the test data set, on the test data set. I say test of loss, and I need test of accuracy equal to model dot evaluate. So that will evaluate and give me back based on x test and y test. Next, I can go ahead and print f of test accuracy is test accuracy of 0.4f. Perfect. So this will print my accuracy. Next step is to visualize the training process. For that, of course, I need to import matplotlib. I'm going to just do it here so I don't lose the frame. PyPlot as plt. Next step, I will plot accuracy, and I'll probably and plot loss here. do it separately. I'll do it once and then copy paste, and since most of the code is same, I'm going to say plot. In this case, I have the history dot history of accuracy, comma, label equal to training accuracy. Next, I'm going to say plt dot plot history dot history of. Next, I'm going to use value of accuracy, and for this I'll give a label of validation accuracy. So I have my accuracy and my validation accuracy both displayed here. Next, I'm going to say plt dot title model accuracy, and then I'll give x label. I'll give for this its epochs of how many cycles I ran, which is 10 in this case. Y label, I will pass the accuracy. So that's what my plot will look like. Plot dot legend, since we already gave the labels, why not plot dot show? Perfect. Can use the same thing, and also plot loss. Here history dot history loss, and I'm going to call this training loss, and history dot history validation loss, I'll say validation loss, and instead of model accuracy, model loss epochs, and this is loss, and perfect. So I'll have two different plots displayed one at a time. I'm going to go ahead and clear it out and run this thing. And there you go, we have our model architecture, CN model architecture displayed here. Data shape, this we already saw earlier, and this error is same as where I do not pass the input shape first. I have to pass input shape first, but this is just a warning, so you can ignore that. I have my model architecture here, and now it's running for 10 epochs. So I'm going to give it some time and come back to this. So it looks like it ran for the 10 different epochs, and then it gave me a final test accuracy of 0.6674. Here is my graph for training accuracy and validation accuracy. Looks good to me. Next, if you look at the loss versus training loss and validation loss, looks good here too. And if I close this, I have the data displayed here after each and every epoch of what the accuracy and loss was, and final loss and accuracy, and that's what was plotted. So I hope you were able to follow along and build this thing. If you have any questions, do let me know. And just to summarize, today we went into and learned how to build and train a CNN using Keras. We understood the structure and components of a CNN. We gained hands-on experience working with the Cypher 10 dataset, and we developed skills on evaluating and analyzing CNN performance metrics. So if you had any questions or had any issues, let me know and I'll get back to you. Day 5. Building CNN architectures with PyTorch. Today, we'll start with building CNN architecture in PyTorch using the NN module. The key steps here are: first, we will define a module where we will use torch.nn.module to build CNN layers like convolutional, pooling, and fully connected layers. Then we'll do a forward pass where we will define how the input flows through the layers to produce the output. And then finally, model summary will inspect the structure and learnable parameters. Next, we'll do training and evaluation of the CNN in PyTorch. In training, we will perform forward and backward passes, calculate loss, and update weights using an optimizer. Then for evaluation, we'll test the model on unseen data and compute metrics like accuracy and loss. Finally, we'll be experimenting with CNN model design and tuning hyperparameters. The different experimentation areas that we'll pick is layer depth. We'll add or remove some convolutional and pooling layers to observe the impact. We'll change the filter side. We experiment with kernel sizes, example 3 by 3 or 5 by 5. Learning rate. We'll adjust the learning rate to improve convergence, speed, and accuracy. So with all this, let's jump into our hands-on exercise where the objective is to build, train, evaluate, and experiment with CNNs for Cipher 10 classification using PyTorch. So step 1 is to load and pre-process the dataset. So I'm going to go ahead, create a new file, Python, save this file as day5 underscore ex.py. Also, you probably saw in my folder, I already have the Cipher data downloaded from before. So I have that available so it doesn't have to download again. Close this. Now go back to my code. First, let's go ahead and import Torch. We're gonna, from Torch Vision, I am going to import datasets and transforms. Next, from torch.utils.data, I will import the data loader. So once that is done, I'm going to go ahead and first let's go ahead and define the transformations. So I'm going to say define transformations. Now to do this, I'm going to say transform equal to transforms, which we have imported, dot compose, and my transformations can be added here. Well, I'll say transforms dot to tensor. So that's the first step. Next, I am going to say transforms dot normalize, and to this I'll give my normalization list 0.5 comma 0.5 comma 0.5 to 0.5 0.5 and 0.5. Perfect. So this is my transformation here available to use in the process when we load the data. So which is next, let's go ahead and load Cipher -10 dataset. Now to load that, I am going to say train dataset equal to datasets dot Cipher 10, the directory which I've already created, /data, and I'm going to say this is training true, this is download is true. So this will run first time, and since it's already downloaded, it's not going to download anything anymore. Transform equal to transform. So I'll pass that. Next, I'm going to do the same thing for my testing data set, where I'm going to say test dataset Cipher data training equal to false, because this is my testing data set. Download true, transform. Perfect. So I have my data sets available. Now let's go ahead and create the data loaders. So now to create the data loaders, first I'm going to create the train loader equal to data loader, and to that it needs the training data set. We give the training data set. I'll give a batch size. Now in this play part, I'll give the batch size of 64, and I'll say shuffle equal to true for training data set. For testing loader, not data set, loader. So for testing loader, I am going to give the test data set batch size equal to 64, and I don't want to shuffle it, so I'm going to false this shuffle here. So next, I'm going to go ahead and print as usual our training data size is equal to length of train underscore dataset, and then for my test dataset, length of test underscore dataset. Perfect. So I have my data. Now next step is to define a CNN architecture. So I am going to move it all the way up. If you want to see this running, I can quickly run it. I'm going to say Python day5 files already downloaded. Since we have downloaded, if you delete those files, you'll probably see it downloading. Training data size 50,000, testing data size 10,000. So everything is good. Let's go ahead and clear it out, and let's work on defining a CNN architecture. So now to define a CNN architecture, first I will create a, or let's say define a CNN model. Also, I need some imports, so I'm going to go up here, and I'm going to import torch.nn as nn. So this is the module that we need. Again, for functional, I'll say torch.nn.functional. From functional, I'll get f. So this is required. Now in here, I'm going to say class CNN, and inside this, I'm going to need the nn.module. First thing that we do is we define the initializer. Function __ self. Next, I'm going to say super CNN, comma, self, and then call the initializer for the super class. Perfect. Now that is done. Now let's start with the layers. So first is convolutional layer 1 equal to nn dot conv 2d. Get some values 3, 6, and 5. Next, I'll say self dot pool equal to nn dot max pool 2d of 2 by 2. Next, I'll say self dot, I'm going to give another convolutional layer, convolute equal to nn dot conv 2d 6, 16 by 5. Next, I will create an fc1 self dot fc1 equal to, which is a linear model, so I'm going to say linear, and pass it 16 times 5 times 5 and 120. Next, I'm going to create fc2 equal to nn dot linear, and this one I'll give 120 by 84, and finally fc3 equal to nn dot linear and give it 84 by 10. Perfect. We got dot. So that's our CNN class. Next, let's create the forward class or forward function. Forward function needs self and x. That's it. And here I'm going to say x equal to self dot pool and pass it. I want to pass ReLU as activation and pass self dot con1 of x. Perfect. Next, I'm going to create another pool, self dot pool towards ReLU con x of 2. Perfect. Next, I'm going to say x equal to x dot. Let's create the view. X dot view is -1 comma 16 times 5 times 5. So I have my view for x. Next, x equal to torch dot ReLU, another ReLU activated for fc1. Perfect. And of course, I'll pass value of x. And now for fc2, pass value of x, and then x equal to self dot fc3, value of x. So this runs to each and every layer, and we have our forward propagation done here. Next, let's go ahead and outside this, let's create the model. So it's a model equal to CNN, and I'm going to print the model. Perfect. So that takes care of defining a CNN architecture. So let's go ahead and check it out. I'm going to clear it out. Run Python day5 ex.py, and there you go. We have our CNN model with all the different layers displayed here perfectly. As we mentioned, we wanted 3, 6, kernel size of 5 by 5, then kernel size of 2 by stride of 2. That's what we specified. So it kind of created everything for us. It's much more easier than TensorFlow. So it was easy to code this. Next step is to define the loss function and the optimizer. So for that, I am going to import torch.optim as optim. Perfect. So I have that. Now I'm going to go down here, and first let's go ahead and define the loss function and optimizer. Spread is two steps. Criterion equal to nn dot cross entropy. That's the loss function that I want to use. And then for optimizer, I will say I want to use optim dot atom and model dot parameters is what I need to pass to this. And then I need a learning rate. I'll set it to 0.001. Perfect. So that should take care of it. Now let's go ahead and train the model. Now to train the model, let's create a training loop. So I will create a function. I'm going to call it train model, and it will take a bunch of different parameters. First, the model itself. Then it needs the train loader. I have that. I need the criterion. I need optimizer, and I need to know how many epochs we want to run it for. If they've not specified any epochs, I'll just run it for 10. Now I'll say model dot train. So this puts it in train mode. And now for epoch, in range of epochs, so it will run for 10 times if not specified exactly. And here I'm going to say initialize a running loss of 0.0. And then for images and labels in our train loader, I'm going to run a loop where it will go through each and every image. First, I'll start with the zero gradient. So this will zero out the optimizer gradient. So I'm going to say optimizer dot zero underscore grad. So this will zero out that. So next I'll do forward pass, and this will happen again and again. So outputs equal to model images. That's set to the outputs. Next I'm going to say loss equal to criterion, and then I'll pass outputs. This is to the cross entropy. I'll pass outputs and labels. Next I'm going to do a backward pass and optimize. This time I'm going to say loss dot backward, and then optimizer. I'll step up, say step, go to the next step, so that take care of that. And then at the end of it, I'm going to say running loss increment with the loss dot current item. So it will print that. I can print this for every epoch. I can say epoch is epoch, whatever the current epoch is, because it starts from probably 0, so I'm epoch plus 1, and the loss is running loss divided by length of train underscore loader. That will be my running loss, or that will be my loss here, F. So that will be displayed. Perfect. So I have that. Now I can get out of here and train the model, call the train model function. Now, do we have all the parameters? We do have the model. We have created the model right above here. And did we call it model? Yes, model equal to CNN. That's what we created. Then if you see here, it actually keeps it. That's perfect. I have the train loader. So I'm going to give that. I have the criterion. I'm going to give that. I have the optimizer. I'll give that. And epochs, I'll leave it as default to 10. So that's good enough for me. Next, before even running this, let's go ahead and write the evaluation code. So I'm going to say evaluation loop, and then I'm going to create a function called as evaluate model, and I'll pass model, and I need the test loader for it because that's where the test data is. So now first I'll have to put the model in evaluation mode. So model.eval, this will be put the model in evaluation mode. I'm going to say correct equal to 0, create to total equal to 0, and now I will loop through with torch dot no grad. Starting with that, I will go over each and every images and labels in my test loader, and I'll set the outputs equal to model images. Then I don't need the first parameter of torch.max, so predicts. So second one is predicted values. I will take that from torch.max outputs comma 1. So this will give me the predicted values. Now that I have that, I'm going to increment total equal to labels dot size of 0, and I'm going to say correct plus equal to, if it's correct or not. For that I can check if predicted equal to labels. So if it's same, then I'm going to sum it where the item. Perfect. So I have that. So now I can go ahead and print it outside, where I can say f test accuracy and percentage. So I'm going to multiply by 100 times whatever the correct is, divide by total, and I want to see only 2 decimal places, so let's say 98.5 or 48.5, whatever it is, percentage. Perfect. So let's go ahead and evaluate the model. Say model comma, oops, and I need the test loader, give test loader. Perfect. So now let's go ahead, clear it out and run this. Now that it's ready, it's going to train the model. It will do one epoch at a time, and it should show me as soon as it completes the first epoch, and then it will show me the loss for the second epoch. So I'm going to give it some time and wait for it. I think I gave the semicolon instead of colon, but I'll wait for it for a little while and then continue. So it took a couple of minutes, and it got us through all the 10 epochs and gave us the loss. As you can see, loss is reducing as in when the epochs increase, which means more epochs you have, less loss you'll have. And the test accuracy is 63.25%. That's what is displayed. Perfect. So that's the end of our of this code. But again, the next step is we want to experiment with CNN design and hyperparameters. So if you want to modify the architecture, for example, if you want to add more convolutional layers or change the number of filters, we can go to our model. So if you want to add another layer in here, you can add another layer and then kind of call them from here. Another option is you can adjust the learning rate. So we have a current learning rate. I'm going to reduce the epoch to 1 just now, keep it as it is. And learning rate, if you want to change it to either add an additional 0 or reduce a 0, you can try with this, or you can even try to test with SGD or RMS pop for your optimizer, where we have optimizer Adam. So instead of this, I'm gonna comment this out, and I can say optim dot SGD, and I'll pass it model dot parameters. That's what it needs, and it needs a learning rate LR equal to, I'll say for this one 0.01, and I can say momentum is another thing that it needs. I can specify that as 0.9. That's how I can create this, and I make sure that when I'm training it, it's added as that optimizer here. Perfect. And this is how you can try with different hyperparameters, and of course it will run fine, but I don't want to run through the entire thing, so I'm going to just quickly show you They'll run through it. It will give you the data. It will run through the epochs with the new values and then you can compare it with the previous one and see how well you have done. So as you can see, it's running through the new optimizer and probably will have some different values, not much, because every optimizer does work in a different format. Anyways, so I hope you were able to get through this particular day and implement this. If you had any problems or issues, let me know in the messages and I'll get back to you. And just to summarize, today we learned how to build CNN architectures using PyTorch. We understood the training and evaluation workflow in PyTorch. We developed skills in experimenting with model designs and hyperparameters, and we gained some practical experience with Cypher 10 dataset for image classifications. So again, if you had any issues, let me know. If you have any questions about what we did today, let me know in the messages and I'll get back to you. Day 6, regularization and data augmentation for CNNs. Today we are going to look at overfitting in CNNs and methods to prevent it. Now, what is overfitting? Overfitting occurs when a model performs well on the training data but fails to generalize to the unseen data. In CNNs, overfitting is common due to the large number of parameters in deep networks. Now, the methods to prevent overfitting include: we have dropout, which randomly sets a fraction of neurons to 0 during training. It prevents co-adaptation of neurons and is controlled by a dropout rate. Example can be 0.5. Next, we have batch normalization, which normalizes the input of each layer to stabilize training. It reduces internal covariate shift and allows higher learning rates. Your data augmentation increases dataset size artificially by applying transformations to images. Examples can be rotation, flipping, scaling, cropping, brightness adjustment. Let's go into the introduction to data augmentation techniques. Some of the common techniques are, as I mentioned earlier, rotation, which rotates the image by a specified angle range, example minus 30 degrees to 30 degrees. Flipping, it horizontally or vertically flips the image. Scaling, it resizes the image by zooming in or out. Cropping, extracts random portions of the image. Let's talk about implementing regularization and data augmentation in CNN training. Now, why use both? Regularization reduces the complexity of the model, whereas data augmentation increases the diversity of the training data, improving the generalization. So, with this in mind, let's jump into our hands-on exercise where we will be applying dropout, batch normalization, and data augmentation to improve CNN performance. So I'm going to start with a new file, Python file, save it as day6_ex.py, and here let's start with importing TensorFlow as TF. All the libraries that I need here is from TensorFlow.keras. I need to import layers and models. Next, from TensorFlow.keras.datasets, I need to import Cypher 10. Next, from TensorFlow.preprocessing.image, I will import image data generator. Next, I'm gonna to plot stuff, I will import matplotlib.pyplot as plt. So okay, once I have that, next step is to load and pre-process the Cypher 10 data. So first, let's go ahead and load the Cypher 10 dataset. To do that, I'm going to create x_train, y_train, comma x_test, y_test, and this I'll get from cipher10 dot load underscore data. Perfect. Once I have the data, let's go ahead and normalize pixel values to the range 0 to 1. So currently they are in from 0 to 255. I'm gonna normalize them from that to 0 to 1. So I'm gonna say x train equal to x underscore train dot as type needs the type of float 32 divide by 255.0. Same thing I'll do for x test as type floated to 255. Perfect. Now for the features or the labels, I'm going to say one hot encode the labels. So for that I need ytrain equal to tf dot keras dot utils dot to underscore categorical and I pass y underscore train comma 10. Same thing I'll do for test y test tf test comma 10. So perfect. So we got everything, whatever the numbers were there, they're all into zeros and ones into a list of items from 0 to 1. So for example, 3 is decoded as or encoded as 0 comma 0 comma 0 comma 1 comma 0 comma 0 comma 0. So for the 10 of them, they're kind of the right index is picked for that particular item. So 0 to 9 we have items, and that's how it will pick. Next, let's go ahead and apply data augmentation. So do that. I'm going to say data gen equal to image data generator. I've already imported that. And here I'm going to do some random rotation. So I'm going to say rotation underscore range is equal to 15 degrees. Next, I can say width shift range can be from 0.1. This will do the horizontal shift. Next, I can say height shift underscore range equal to 0.1. Again, this do a vertical shift. And then I have horizontal flip equal to true. So this will do horizontal flipping of the image and create new images or data set for us. Now I'm going to say fit the generator to training data. That I can do by saying data gen dot fit to my training data, which is x underscore train. Perfect. So that once that is done, our next option is to build the CNN model with dropout and batch normalization. I'm going to scroll up a little bit here and then create a function, call it def create model, and in here I will say model equal to models dot sequential. It's the one that I need. Now first thing is, let's add the convolutional layer 1, but before that let's give that input shape. So I'm going to say model dot add, and I'm going to say layers dot input, and the input shape that I give is 32 comma 32 by 3 classes. Next thing that I can do is now I can give the convolutional layer add layers dot conv 2d 32 filters and 3 by 3 and activation equal to relu, and I don't need the input shape because I've already given that, so this is good. Model dot add, next one I'll give a layer for batch normalization, so that is batch normalization. Perfect, so that's done. Next, I don't have to add commas because this is not inside particular instance. I can just say keep on saying model dot add. Next one I want to add again a convolutional 2D. I would say convolutional 2D 32 3 by 3 activation equal to ReLU. Next, I'm going to again do batch normalization. Next, I'm going to add max pooling. So I'll copy this and say, instead of this, I'll say max pooling 2D, and that needs 2 by 2. Perfect. So that's closes this. Is it all closed? Yeah, perfect. So I have 3 brackets, 2 brackets in front. Perfect. Next one, I want to do model dot add. I want to add the dropout layer here. So I can say layers dot dropout, and that is drop out, and I can give a value of 0.25, which is 25%. Next, I'll create another convolutional layer. So I'm going to say model dot add. So what I'm going to do is I'm going to copy this entire thing for the second layer. Model dot add. I don't have to add this input. Convolutional 2D 64 by 3 by 3 activation equal to ReLU batch normalization. Again, I'll say 64 3 by 3 activation ReLU batch normalization layers max pooling 2D and then dropout of 25. Perfect. Next, so I'm going to kind of mention here that this is convolutional layer 1 and this is our convolutional layer 2. Now I will create a fully connected layers. To do that, I'm going to say model dot add. I'll have to first add the flatten. So I'm going to say layers dot flatten. Next, I'm going to say model dot add, and this time I'm going to add a dense layer 512 comma activation equal to ReLU. Next one, I'll add the batch normalization to this. Batch normalization. Next, I'm going to add a dropout of 0.5. Next, I'm going to create another dense, which is the final output layer, dense with 10 different classes, and activation I'll use softmax. See, activation is all spelling is right. And then finally, I will return the model from here. So that kind of builds my model. Now that my model is ready, let's go ahead and compile this model. To do that, first get the model. I'll say model equal to create model. This will create our model. And then I'll say model dot compile, and I'll have to specify optimizer equal to, I am using Adam. I will say loss equal to, I will create the categorical underscore cross entropy. Next, I will say the metric that I'm interested in is accuracy. Perfect. So that will compile my model. Now that it's compiled, let's go ahead and train the model using the augmented data generator. Now to do that, I'm going to say create a parameter history equal to model.fit. The reason I'm doing it is so I can plot these data in a little while. Datagen dot flow, I'll call x underscore train comma y underscore train, and I'll say batch underscore size equal to 64. Next, I'm going to say number of epochs that I want to run it for is 20. It's going to take forever to run this, but I will take that chance so I can get some good data out from here, or get good model out of here. Y underscore test, my validation data comes from there, and then I'll say steps per epoch equal to x underscore train dot shape of 0 slash 64. So this is steps per epoch that I want. Next, let's go ahead and evaluate the model. So based on the test data that we have, I can say test loss, uh, comma, test accuracy equal to model dot evaluate, and I'll pass it x underscore test, y underscore test, and verbose equal to 2. Next, I'm going to go ahead and say print test accuracy is test underscore accuracy point 2 f. So that will display my accuracy. Now let's go ahead and visualize I want to do everything together because it's going to take forever to run this code. So let's go ahead and visualize the training and validation accuracy. So I'm going to say plot dot plot history dot history of accuracy, comma, I can say label equal to training accuracy. Next, I'm going to plot. Now that I have accuracy, next is validation accuracy. So I'm going to say validation accuracy, and this is validation accuracy. Let's move it up. So I have that. Next, I need to get the X label. So I'm going to say plt dot X label. I will specify that that's epochs, and my Y label, that will be my accuracy. Next, I'm gonna give a title, and that title will be training and validation accuracy. Next, let's show the legend, and then show the plot. And again, for my loss, I'm going to copy this, paste it here, say loss. This is training loss. This is validation loss. So this is validation loss, epochs, accuracy. No, this is loss, training and validation. So looks like I have everything here that I need. Hopefully there's no typos, but we'll come to know. So I'm going to go ahead and run this code. I'm going to say Python day 6 and run it. As you can see, probably it will take some time to start up because Cypher data is pretty, and as it looks like I have some error here, layers input. Oh, I forgot to mention shape. So I have to go here and say shape equal to, that's how you specify layers.input, shape equal 32 by 3. So let's go ahead and run it again. Let's clear it out, run it again, and it ran. It gave some warning about the PyData set, which is not something that I'm using, but it's a built-in function. But it's running our epoch 1, and it's going to run until 20. So I'm going to go ahead and pause it a little bit, pause here, and then come back and start recording once it's completed. So it took some time, but here it went through all the 20 epochs. There were some errors in between where it ran out of memory, but again, we have our graph here which shows the training and validation accuracy. As you can see, as and when we train more, the accuracy is increasing. Similarly, we have our training and validation loss, where depending on how much training we do, it kind of keeps in reducing the loss. So there you go, perfectly trained, perfectly. And that's our project, where today we learned and understood how dropout and batch normalization prevents overfitting in CNNs. We learned to apply data augmentation techniques to enhance model generalization. We gained practical experience implementing regularization and augmentation in TensorFlow, and we developed intuition for experimenting with regularization rates and augmentation strategies. I hope you were able to follow along. If you have any questions or had any issues while implementing this, let me know and I'll get back to you. Day 7, CNN project. Image classification on Fashion MNIST or Cypher 10 dataset. So first, let's look at applying CNN architecture on a larger dataset. Now, why larger datasets? Larger datasets like Cypher10 or Fashion MNIST represent more realistic and diverse challenges compared to toy datasets like MNIST. They require deeper architectures, careful regularization, and augmentation for optimal performance. Next, experimenting with architecture design, regularization, and augmentation. Now, some of the key techniques to improve this performance is first, architecture modifications. Add more convolutional layers or change your kernel sizes. Use more filters in deeper layers to capture complex features. Regularization. Apply dropout in dense layers and batch normalization in convolutional layers. Prevent overfitting in deeper models. Data augmentation. Use techniques like random flipping, cropping, and rotation to improve generalization. Let's talk about analyzing model performance and tuning. So, the evaluation metrics that we use are accuracy, which is for overall classification correctness. You have loss, which measures the difference between predictions and ground truth. Confusion matrix, which highlights misclassified classes for deeper insights. So, with all this in mind, let's jump into our hands on exercise where we will be building, training, and optimizing a CNN for, in this case, we'll use Cypher 10 image classification and experimenting with regularization and data augmentation to achieve the best performance. And I would recommend you try out to work with the Fashion MNIST dataset to do the same. So first step is to load and prepare the dataset. So I'm going to go ahead, create a new file, save as day7 underscore ex.py. And as you can see, I already have the data downloaded, so I don't have to download again. In here, first I'll start with importing torch. Next, from torch vision, I will import the data sets and transforms. Next, from torch dot utils dot data, I will import data loader. There you go, I have that. Next, let's go ahead and define transformations with data augmentation. So for that, I'm going to say transform underscore train equal to transforms, and here I'm going to compose, and my data set that I want here is, first I will say transforms dot random horizontal flip. Okay, I think I'll have to random horizontal flip. Next one, I'm going to say transforms dot random crop, and this time my crop will be 32 by padding equal to 4. Next, I'm going to say transforms dot to tensor. So it doesn't show up, so I will to tensor. I think I misspelled, that's why. This makes sense. Next, I will say transforms dot normalize, and this time I'll give some parameters 0.5, 0.5, 0.5, and 0.5, 0.5, 0.5. Perfect. So I have my data set here, my transform here perfectly created. Let me cross check one more time. Random horizontal flip, transform.random crop, 32 padding. So given additional data augmentation here. Now let's go ahead and create another transform test. Transforms dot compose, and this one I will create let's say transforms dot to tensor. So this is for my test data set. That's why it's called that. And I need normalize because I need to normalize the data too. I'll give the same values. Perfect. Now next step is to load the cipher-10 data set. To do that, I'm going to say train data set equal to data sets dot cipher 10. Similarly, you can use fashion mnist also, that is available. So I'm going to use cipher 10 right now. The data where I want to save it equal to dot slash data, which I already have it, so I don't have it will not download again. Train equal to true, download equal to true, and transform equal to, I already created the transform train, so I'm going to use that transform. Where is it? Transform train. Perfect. Copy that. I'm going to use the same copy paste, and instead of train I'll say test cipher train equal to false, download true, and then this is again test. So is it not transform test? Oh, it's transforms. That's why it was causing. Let me fix that. Transform train and transform test. So perfect. So I have both of them. Now that I have my data set, next thing to do is get the loaders. So I'm going to say train loader equal to data loader and pass it the train data set. Say batch size equal to, I'll say 64, and I'll say shuffle equal to, since it's training, I'll say true. But for the test loader, data loader, I'll give the test data set 64 shuffle equal to false. I don't want that to be shuffled. Perfect. So I have my data set here, my loaders here. Next, let's print it. Print f of training data size. Just to check the size, I am going to say length of train data set. Same thing. Test data set. I'll say test data set, length of test data set. Perfect. Now I have that. Next step is to define the CNN architecture. So this time I'm going to call it the enhanced CNN. Also, I need some more imports. So I'm going to say import torch.nn as nn and import torch.nn.functional as f. So with that, let's go ahead and let's create our class which is enhanced CNN, not the usual CNN that we work on. And n.module is what I'll pass as a parameter to this. I'm going to create the initializer method as usual, init underscore underscore. You can kind of copy paste this from one of the previous projects if you want to do it faster. But again, I like to practice, as I say always. That makes you better in coding. Init underscore underscore call the, so this will call a super method. Next, I'll give my first convolutional layer conv1 equal to nn dot conv2d, and then to pass it parameters 3, 6, and 5 are standard numbers. Next, I'm going to say self dot bn1. This is our batch normalization. So I'm going to call say nn dot batch normalization 2d, and I'll pass the value 6. Next is my second convolutional layer conv2 equal to, in this case I'll say nn dot conv2d and pass 6, 16, 5 based on the previous layer. Next one is bn2 equal to nn dot batch normalization 2d, and this time I'll pass 16 based on the previous layer. Next, I'll create my pool equal to nn dot max pool 2d 2 by 2, self dot dropout equal to dot dropout, and this I'll give 50%, so 0.5. Next, let's calculate the size of the output from the convolutional layers dynamically. That I can do by saying self dot underscore calculate underscore conv underscore output, which will be another function that I'll write. This will be helpful to kind of pass it to our FC1, where I can say self dot FC1 equal to NN dot linear, and I'll pass self dot conv underscore output underscore size comma 120. Before we used to like assign it, but we are calculating it just so that it's it's generated dynamically. Next, FC2 equal to NN dot linear, and this time I am going to assign this 120 comma 84 based on the previous input. Self dot FC3 is equal to NN dot linear 84 comma 10 based on the previous input. This is my final layer for 10 classes. Now let's go ahead and define that class to calculate the convolutional output. So for this, I am going to pass the parameter of self, and here I'm going to create a dummy input tensor with the same size as the input images first. So I'm going to say dummy underscore tensor, dummy underscore input equal to torch dot zeros with 1 comma 3 comma 32 comma 32. So that's the entire batch size, channels, and height and width. Now with torch dot no grad, I will produce the output, which is self dot pool of f dot ReLU, self dot bn2 is the next one, with self dot conv2 with f dot ReLU with self dot bn1. It kind of becomes too complicated depending on how many layers we have. Conv1 with dummy input in there. So let's make sure that all these brackets are properly closed. As output equal to self dot pool f dot, based on the data here, ReLU self dot bn2 con2 ReLU self bn1 con1 of dummy input. Looks fine to me. Let's see if there's any issues. We'll get an error. Convolution output size equal to output dot numal. That's the function that we call to get the values. So we have that. Next thing is, let's create the function, the forward function, which takes self and the value of x. So for this, I'm going to go ahead and first say x equal to f dot ReLU of self dot bn1 of self dot conv1 of x. That will give me my x equal to self dot pool. Next is the pool part, where we have f dot ReLU of self dot bn2 of self dot conv2 of x. That's my second. Next is x dot view. This is for flattening the tensor dynamically. I'm going to use x dot size of 0 comma -1. Perfect. Next I'll say x equal to f dot value of self dot fc1 of x. Now once I have that, I can use the dropout next. X self dot dropout of x. Next I'm going to say x equal to f dot value of self dot fc2 of x. Next I'll say x equal to self dot fc3 of x. That's my output layer, and that's what I'll return back, x. So I have all of them based on this here. Hopefully, if not, I'll come back once the error shows up. So next I'm going to say model equal to our enhanced CNN model. Let's implement that and then print this model out. Now I should not get any errors, but I can check quickly. Python day7 ex.py. Let's see. Oh, I think I spelled zeros wrong, and that is right here, zeros. Let's go ahead, clear this out, run it again. It says output is not defined. Look, okay, equal to, so that's where I'm defining output. Perfect. So let's go ahead one more time. Let's hope there's no more typos. And there you go, we have our enhanced model displayed, and it ran through the entire thing and printed the model. Perfect. Our next step is to train the model. So let's go ahead above here and let's import torch.optim as optim. Once that is done, I'm going to come down here. After I print the model, I'm going to go ahead and define the loss function and optimizer first. Define loss function and optimizer. To do that, I'll say criterion equal to nn dot cross entropy loss. That's what I need. Next, I'm going to say optimizer equal to optim dot, I'm going to use Adam optimizer, and I'll pass it model dot parameters, and it needs the learning rate. I'll give 0.001. So I have my ready. Next, I'm going to create a training underscore loss list, empty list. Here, let's move it all the way to the top. Now let's create our training loop. So training loop. Inside my training loops, look, first let's define the function train model, and this model I'll pass model. I'll pass the train underscore loader. I will pass the criterion. I will pass the optimizer, and epochs I can set it to 20. Again, it's going to take a lot of time, but I'll take the risk. Model dot train, which starts our training the model steps, and here I am going to say for. Here looks like, since I again used dash, that's why it was giving me an error. Now going through all the images and labels in train loader, there's the first step. Oh, before that, let's run for each and every epoch. So I'm going to say for epoch in range of epochs, I am going to say running loss equal to 0.0. I'll initialize at 0.0. Then I'm going to go over each and every image and label in train loader. I'm going to say optimizer dot 0 underscore grad. So I'm going to zero out the gradients. I'm going to say output equal to, or outputs equal to, again, model dot or model of images. Next, I need the loss is criterion, and I'll pass outputs and labels to it. Next, I need to step, we want to go backwards, so I'm going to say loss backward, so backward propagation after that, and then I'll say optimizer, I will go step up. That's it. Next, I'm going to increment the running loss after all my steps are done here. So loss dot item, that's my loss. Next, I'm going to go outside and say epoch loss. I think that's what we had. That was what we need is running loss divided by length of our train loader, which is the reason I'm doing that is I can get my training loss dot append. I can append it in there. That's why I created that. I can also print it out like how I did last time, where it will show me every single time which epoch it is, and inside that epoch, since it starts with 0, I'll say epoch that loss is epoch loss with only 4 decimal places. Perfect. So that's done. Now I'll go ahead and call the train model function and pass all the things that it needs. I have model, I have train underscore loader, I have the criterion, I have the optimizer, and I'm not going to give epochs because by default it's 20, so I'll keep that 20. Next step is to evaluation of this loop. Write the evaluation loop for this model. So I'm going to go ahead and write that function evaluate underscore model. For this it needs model and test loader, and I'll say model dot eval. So it starts the evaluation process and set correct equal to 0, and what was the other one, total equal to 0. These are two parameters that we initialize, and we will increment or decrement depending on the data that we get with torch dot no grad. So we'll start with empty grad, and then for images and labels, now this time in test loader. So I'll take each and every one and then check for the outputs equal to model images. So this will give me the outputs of those. I don't need the first parameter of this, but I need the second one, which is predicted. So I'm going to say torch dot max of outputs comma 1. So that will give me the predicted values. I'll say total plus equal to labels dot size of 0. So that will give me the total increment, and correct increment will be predicted is equal to labels. If it's equal to labels, what I'm going to do, sum of item, that's what I'll do. So that will give me increment my corrects. Next, go outside and print my test accuracy. Test accuracy is, I want it in percentage, so 100 times of correct. Did I spell correct wrong? Nope. Correct divided by total 0.2f percentage. Okay, so that is good. Now let's go ahead and evaluate our model, and I'll pass it model and test loader. That's all it needs. Perfect. Now if you want to plot this, we'll have to first import matplotlib as pyplot as plt. I usually like to put my imports up, but for this I'm just going to keep it here and make it simple plot. So first I'll say plot training. Now we'll take the training loss and I'll use the label equal to training loss. Next, plot dot title, I'll create the, call it loss curve. Next, I want to give the x label, which is epochs, which is 20 in our case, and then plot dot y label, which is loss in our case. Next, I'll say plot dot legend, Perfect. And then plot dot show. Perfect. So that kind of completes our entire exercise. I hope you were able to follow along. And if not, just pause it wherever you can and go through it. That's what I would say. Next, now let's go ahead and run this. I'm going to go here, clear it out. It's going to take some time because I have 20 epochs to run through. I have the data. Okay, it looks like there is some, instead of ReLU, I have said rel. So let's fix all these things. F.ReLU, where is F.rel? Here. Perfect. Clear it out. Let's see if there's any more errors. I like to do one error at a time, even if it shows me 20 errors. But as long as it shows me that it's going through epoch 1, I think that's probably the start of it. And that's what I'm waiting for. Since the data size is big and it's going through that entire data set and testing it out, the epoch will take some time to show up. But this delay kind of gives me, as you say, as I said, if more and more time it takes, that means it's working. There's no error. So that's good. So I'm going to stop here for a little while and come back once it's completed. So here you go. After the 10 epochs that we went through, it reduced the loss. As in, you can see it, test accuracy is 62.25, and you see the loss curve here keeps on going down as and when the epochs increase. So this is good sign. I'll close this up, and this is our data. If you had something similar, that's good. If not, let me know, and I can help you out on how to fix that. So just to recap, this week on week 10, on our day 7, we gained hands-on experience building and optimizing CNNs from practical datasets. We understood the importance of regularization and augmentation in improving the model generalization, and developed skills in analyzing and tuning CNN performance, and prepare for real-world scenarios requiring robust model training and evaluation based on the dataset that we have seen. So I hope this was helpful. If you have any questions or had any issues, let me know in the messages and I'll get back to you.